Okay, welcome to day two of the conference. First speaker today is Leonid Levitov, and we'll have an extra long lunch break upstairs. And last thing, if you have any questions, concerns, hotel or Wi-Fi, whatever, you can just email me. I'll check my email and respond it. That way we don't have to waste time on announcements. Please go ahead.
Yeah, good morning. Yeah, thank you for having me here and having this opportunity to speak. So the work I'm going to talk about is the recent work we've been doing, the interest is in spin-ordered phases in bands with Berry curvature, generally speaking. So that these are the first two papers, and then I'll talk about that first, and then at the end we'll talk about more recent work going on now. So the question is to understand spin chirality and the role of spin chirality. Spin chirality in correlated electron systems, and chirality is something that appears in many different contexts. This is a quick reminder of different meanings of chirality that we are aware of. So first of all, chirality in general is a phenomenon which is not identical to its mirror image, as in this chiral molecule. Then another way we think about chirality helicity is when we have some correlation between particle spin and particle propagation direction, and that's how it appears in particle physics, and also will be useful and important to us in this talk. Then another quantity which is called chirality, also useful to introduce and use, is when you have a spin order in which spins are not collinear and not anti-collinear nor planar, but instead they're doing something like what's shown in the picture, so that their triple vector product is positive or negative, depending on the sign of chirality, and but non-zero. So any questions? Let me know. We can stop and discuss. Okay, good. So the reason chirality is interesting, actually, many reasons, different for different people. So first of all, it's interesting quantity that often appears in magnetism, and in magnetism there are staggered spin phases in which spins are formed some kind of helical structure. So there is both broken spin rotation symmetry and there is a chirality, and so that's how it appeared first a long time ago in theory of magnetic dielectrics. Then also there are more exotic phases in which time reverse was broken and chirality is non-zero, but spin rotation symmetry isn't broken. And so the point here is that this quantity is a scalar under spin rotation. So you can have, in principle, time reversal can be broken, and you can have this quantity which is non-zero without breaking spin rotation symmetry. So these are kind of two ways this quantity appears. But then why is it interesting? Why people care? And there are many people who care about chirality, all for different reasons. There are maybe two main reasons we should I should mention here. One is that if you have spin texture or spin order with chirality, and then there are some carriers present in the system, and the carriers are coupled carrier spins are coupled to these spins in a texture by some kind of exchange interaction, then texture is known to generate a geometric magnetic field, or the Zuda magnetic field, which arises in this way when a carrier is moving through a texture, and its spin is following local spin orientation of the texture, the wave function will pick up a Berry phase due to spin rotation, and that Berry phase will be very much like Aharonov-Bohm phase, and its curl will be a magnetic field that will produce a Lorentz force and or geometric Lorentz force, and then one can have a Hall effect without external magnetic field being applied, and there have been a lot of work on that and a lot of interest in that, chiral spin texture as a source of anomalous Hall effect, i.e. Hall effect without magnetic field, yeah, so then the interesting thing about this effect, which I should mention here because it will come up a little later, is that this geometric magnetic field, I mean, arises in a completely conventional way, just like Berry phase and textbook, but it has a sign opposite for different spin orientations, and that's clear from this picture. If you have carrier spin like shown by this black arrow, it picks up one Berry phase of its solid angle, which is shown here, and if it's the opposite sign, picks up an opposite Berry phase, so magnetic field, geometric magnetic field for spin up and spin down is the opposite sign, and so that's one way that magnetic field is chiral. It has opposite signs for opposite spin orientations. Right. Then okay, so then that's the reason chirality is interesting. Number one. Then the other reason I want to mention is that chirality is an interesting spin order that can be studied independently of magnetism or together with magnetism, and there are interesting properties of chiral order that various people have looked at, and there are many people who worked on it, and many more than this list, and I think some people in the audience who also work mentioned, but there's a really long list of papers. So out of what I said, I mean, most of these papers are interested in geometric magnetic field as a source of quantum Hall effect, but then some are also interested in chiral order per se. So this paper, for instance, also the last paper, is concerned with, so this was a theoretical proposal, and this is an experimental paper where it claims that they observed an order in which chirality is non-zero, but spin polarization is absent. So these are two themes in the literature that pretty actively studied. So so that's like the historical review. If you have any questions, let me just speak up. So now, as far as I'm concerned, my interest in chirality came from two sides. A few years ago, 5 years ago or something, we became interested in the question of itinerant magnetism. If you have bent electrons and then exchange interaction, and from exchange interaction you get spin polarized. And the question was, what happens if this is itinerant magnetism in a band with Berry curvature? In a band with Berry curvature, carriers have orbital magnetization, so there are orbital currents in the ground state due to Berry curvature, not due to magnetic field. There is no magnetic field, but due to the behavior of the wave functions in a band. And so it was interesting to understand what's new about magnetism in this problem. So this was motivated by ongoing experiments in topological bands in graphene, but no, it's an interesting problem on its own right. So so this is a quick summary of what these papers show. So first of all, I mean, if you do ordinary mean field calculation, doing Harvard-Sirtanovich decomposition of factoring of chain interaction, introducing order parameter, but allowing order parameter to twist so that you're not, we're not constraining the system to be uniformly polarized, but allowing polarization vector to twist, and then derive the energy as a function of that twisting order parameter. Then you discover, after doing some interesting algebra, discover that in addition to all the usual things we know about the stiffness term and the interaction that wants to align spins, make them locally parallel to each other, there is also a new interaction which we can call chiral interaction, that looks as follows. It's a product of chirality. That's this triple product of spins in a spin texture. So there's a continuum version of that vector product. Chirality, which is the density of the geometric magnetic field multiplied by the orbital magnetization of the system due to Berry curvature. So this quantity, I mean, derived microscopically, but it's interesting for two reasons. First of all, the coefficient here is geometric. I mean, it follows from Berry phase and flux quantization. Second, this quantity is a spin-orbit interaction arising without microscopic spin-orbit interaction, because this quantity is an orbital quantity, orbital magnetization. This quantity is a spin property. It's a property of spins. So it's a spin-orbit interaction, synthetic or emergent spin-orbit interaction that arises due to exchange. And so, I mean, so different origins from microscopic spin-orbit interaction can be big, and it can lead to interesting effects. The reason it leads to interesting effects, because if you ask whether that free energy that we derived tells spins to be all aligned parallel to each other or favors twisting state, then you see right away that this term that depends on chirality favors twisting, because chirality is minimized by spins which are in a texture state, and then this term, of course, wants spins to be aligned parallel to each other. Now, both terms are second-order ingredients, so they compete equally, and just game of numbers, whether that number stiffness is greater than that number.
Context is constant, right? In this free
M
is not
so M, yeah,
it's
so
constant.
M, let's take it as constant, but if we think about specific realization, so specific realization would be as follows. Imagine graphene band, and in graphene band there are two valleys. Each of them has its own M opposite signs, because Berry curvature is opposite. But now, if you have a valley polarized order in which all carriers are polarized in one valley, not in the other valley, and such phases are now observed, by various experiments. Then there will be M, which depends only on the Berry phase in the valley in which electrons, which holds electrons, and then the value of M will be tunable. In principle, will be tunable by Fermi energy. It doesn't depend on Fermi energy that much, but
what I meant
it's
for
tunable.
the purposes of this model, M is just a parameter, right?
M is a parameter, but
But you don't need a
it's
parameter.
important whether it's zero or non-zero and how you tune it.
Right.
Yeah.
Then I'm confused, because I thought I took that first one to be a kind of a local coupling between M, which could be spatially. So I thought that M was just curl of J.
Yeah, so this, it does, so this is intentional, it does look like electromagnetic coupling of magnetization to magnetic field, but so this interaction has the same form, but this magnetic field is a magnetic field that exists in the absence of external magnetic
No, I'm
field.
happy with the magnetic field, the M, can it be spatially modulated?
It can.
But in terms of electron properties, okay, I wasn't thinking about values, but if it was just current, would it be a curl of J, just the usual sort of a?
Yeah. So
Okay.
it's orbital magnetization of the ground state, but if your ground state inhomogeneous, then M will be higher here and lower elsewhere. So M in principle is,
So M is independent on S, right?
yeah, kind of independent of us, because you can have, so M is tunable by Fermi energy, basically. If you Fermi energy is fixed, then M is constant, but B is still tunable because your spins can twist. Yeah, so.
Then you will get a Skirmion texture.
Yeah. You get, so if this is large, you get all spins aligned. If this is larger, you get Skirmion texture. So in that system, it's tunable, and nothing surprising about the properties of Skirmion texture. Is so far nothing surprising, but it's interesting that in the problem you have these two phases, and you can tune from one to another, and it's accessible in experiments. So I think that's interesting. But anyway, before we get to Skirmion texture, let me just show you the something else. So if you start with the boarding state in which your spins are all parallel, then this quantity is zero on average, but it's there in the Hamiltonian, it's there in the free energy, and you can work out the collective modes in this state, and you just do the usual collective mode calculation. Discover that in that state you get magnons, and the magnons are pretty much identical to what they are without this chiral interaction in the bulk, but in addition there is a chiral edge mode, magnon edge mode that propagates along the edge in one direction or the opposite direction, depending on the sign of M. And so that's interesting.
Why the magnons have a gap?
Oh, the gap, sorry, the gap was just, I copied it from a paper, and then in the paper, besides these terms, there's also a Zeeman magnetic field that opens the gap. If you get rid of Zeeman field, then the gap will be zero. Then basically the upper branch and the lower branch will join. Yeah, anyway, so then you can build a phase diagram, and phase diagram, as we said already, will have two phases, uniformly polarized, and the texture, Skirmion texture phase, and then in Skirmion texture, one has all these, in principle, one has all these effects that people predicted for Skirmion textures.
Yeah, so B is topological, but E has E is proportional to the interactions. It says M dot B, so that suggests that it's universal. The form of coupling between orbital and spin texture, is that because it comes from exchange effects?
Yeah, that's what
That should
you
be
derive. That's
proportional
what
to
you
the
derive
interaction.
if you do that Harbert-Stratanovich with twisting texture. You can also motivate it phenomenologically, saying that there is orbital magnetization of carriers.
No, I'm happy with the form. I'm just concerned that the magnitude of the coupling should be interaction dependent. Okay, maybe
Okay, so interaction. Okay, so it turns out that in a low temperature limit where the fluctuations are weak, you get a universal. So you get, the reason it's universal is basically because M dot B is the M dot B. M dot B is the usual magnetization to external magnetic field coupling.
Right.
So you reproduce that when you do calculation, you reproduce that. But then in the process, you discover what B is and what's the right scale for B.
Okay.
And so you derive that number. Yeah. Anyway, so that's just see.
You have probably 15 more, 10, 15 more minutes.
Yeah, good. So then let me mention one more thing on this topic, and then one more topic briefly. Yeah, so then one can ask, is there anything interesting about electrons that electrons do in the presence of that spin texture? You know, there are obviously, you know, magnetic field, even if it's emergent, will create Landau levels, and one can look at how these Landau levels will change properties of electrons. They will create magnetic bands of some kind. That has been studied. I mean, magnetic bands in the presence of spin textures are well known and quite well understood. But the interesting question that we found amusing to think about is superconductivity. So suppose these electrons have some superconducting pairing, as electrons on graphene often do, and we are yeah. So magnetic bands, and these magnetic bands are basically broad Landau levels, and one can ask, suppose there is pairing interaction, what will superconductivity do in this situation? So this happens to be an interesting problem because this magnetic field that you have here is of opposite sign for spin up and spin down electrons, and because of that, it is not producing a pair breaking effect. So this the biggest effect that you usually have in superconductor when you apply magnetic field, that you suppress superconductivity because of pair breaking. And here it doesn't happen because Cooper pairs, which are spin up and spin down electrons, paired together, they see a zero net. Their center of mass will see a zero net magnetic field, and as a result, the leading effect, pair breaking effect, will be absent. However, because the density of states will have structure enhancement because of the magnetic bands or Landau levels, then superconductivity will also be enhanced, and so it's interesting to look into that, and you see that indeed there are.
Is it opposite Meissner effect, like?
I was saying, can we have random behavior or something? Yeah, maybe. So random behavior is something that actually, so there is some history of that. I mean, people thought about superconductivity in the presence of quantizing ordinary magnetic fields. So there have been papers predicting some random behavior. Maybe let's leave it for question. No, I'm not sure it's related, but maybe random behavior in principle, at least if you trust literature, some nice papers on that. But how much this is relevant to this problem, and how much it's true for the actual problem of superconductivity in the presence of magnetic field, and we can not related to my story. Let's wait with that. Okay, good. So that's, I think, is not. All right, good. So then in the last 5 minutes, let me talk about something that kind of followed from this work, but I think is a new story. So given what we see, also given all this literature on spin chirality, where people see that spin chirality is ubiquitous and appears in many different contexts, one can ask a general question. One can ask, what does it take to have spin chirality from symmetry point of view? Do you need to fine-tune interactions? Do you need to do anything complicated? It turns out that you don't. If you just assume that you have a system in which time reversal is broken and inversion symmetry is broken somehow, but you don't need spin rotation symmetry to be broken. then that by symmetry requirements, that's allowed to have spin chirality, and then of course we believe in symmetry, so we expect that anything that is allowed to happen by symmetry should actually happen. So that's point number one. And point two is that these conditions, broken PNT, they are identical to the symmetry requirements for the Berry phase to exist, either Berry phase in K space or in position space. And so based on symmetry, you expect that whenever you, no. Thank you. Yeah, you expect that whenever you have P broken and T broken, so the Berry phase is allowed to exist, you simultaneously can have spin chirality and have it independent of whether there is or there is no any kind of spin interaction in the problem. You can have a Hamiltonian that totally spin independent, no spin orbit interaction, no Zeeman interaction, no any kind of spin independent interaction, and nevertheless, surprising, but that's what symmetry predicts. You expect to have chirality, spin chirality, and that's basically the observation. And then to being surprised, trying to understand how it works, we looked at it more closely for several different cases, and I'll show a list on the next page. But basically, spin polarization not required, magnetism not required, spin orbit interaction not required. All that's required is particles having spin and being in this state with broken PNT symmetry, and then you get spin chiralities. So there are pretty many, a wide class of systems where this can happen, I mean, you can do microscopic calculation, and I don't want to talk about it in detail, but basically take spin density and make mixed vector product, which is an SV2 scalar, then use diagonetics to calculate the average. You see two contributions from the new functions going between 3 points clockwise and counterclockwise, and then when time was unbroken, they time reversal unbroken, these two contributions cancel. If time reversal is broken, then one of them dominates, and then in this way you get non-zero 3-point spin correlator. And one can test this idea in various cases, which where by symmetry requirements spin chirality is allowed. For K-space Berry curvature, I mean, we did calculation for Haldane model, which is basically graphing with broken time reversal achieved by applying some standard magnetic field. You can also take ordinary electron band with no Berry curvature parabolic dispersion, but apply magnetic field, and again, no Zeeman coupling, no spin orbit coupling. So orbital magnetic field just introduces orbital magnetization, and that orbital magnetization is sufficient to generate spin chirality. Then you can also look at a superconductor, which is in a superconducting state in which phase winds around the Fermi surface clockwise or counterclockwise, and so in this case the time reversal is broken spontaneously. And still, in all these cases, you see spin chirality, and the general. I'm not going to talk about calculation. It's in this paper, but just to explain the general reason this happens. I mean, it's useful to mention the following. So there is this identity for three spin 1/2 variables that actually has been known before, and probably was first introduced in this paper by when will check on Z, or maybe earlier than that, but I mean, it's a very simple IDENSI, you can check it, you know, while listening, on the, just write it on a piece of paper, and you'll see that triple spin product is a sum of permutation operators of spin variables, one clockwise, the other counterclockwise, and so this is, on the one hand, this is mathematical identity, on the other hand, if you now read it right to left, you see that, let's say, if your system has vorticity or have some field which is steering or using steering, so that this kind of permutation is given preference to this one, then that will, you can forget about the second one, and you see that this will generate a spin parallelcy in a more pedestrian way, or in a more simple way. We all know that if you, let's say, you have Fermi statistics, pair correlations produce local spin correlation, which is with particles with equal spins avoid each other, particle opposite spins don't avoid each other, and as a result, when particles flow by, there are spin correlations, and the spin correlations basis for RQQI interaction and magnetism and many other things we know. So what this is an extension of that to the problems with broken time reversal symmetry, because in this case, not only you get pair spin correlations out of Fermi statistics, you also get three spin correlations, and these three spin correlations, yeah, just like pair correlations, they don't break spin rotation symmetry. Spin rotation symmetry remains unbroken, but you get spin chirality type contribution to the spin correlation when your time reversal symmetry is broken. And so that's basically, you should shut up. Yeah, take too long. Yeah, so this is basically the main interesting thing that happens here, and you know, one can look at many different cases and see many can do calculation. Let's not talk about that. I mean, one can think about how chirality can be measured. Let's not skip that. Then another interesting thing that we found and we're studying now is the spatial patterns of chirality. Let's say if you take these 3 points that where we measure spin polarization and, you know, let them vary in space, then how will, if these 2 points are fixed, how spin chirality will depend on position of the third point. And so these are, you know, naively would expect that this will be some kind of extension of Friedel oscillations, and there will be some two impurity Friedel oscillations, and there is indeed a contribution like that, but it's more interesting than that. And if you, let's say, if you take the example of a superconductor where time reversal is broken spontaneously by going in superconducting state with Cooper pairs being, you know, P or D or something like that, then in addition to these Friedel oscillations that I just shown you, I will try to flip pages because it's too slow, you get some new kind of interference pattern. You get interference pattern in chirality dependence on one of the points that has that looks like young interference fringes from two sources. You can see this by naked eye, and that's coming from interfering contributions of particles and holes. So there is in that superconducting problem, besides ordinary Friedel oscillations that you also see if you zoom in, there are these interference fringes on a larger scale that are a result of, schematically, it's a result of shown here. There's a particle hole conversion that happens by itself on a superconductor because quasi-particles are superpositions of electrons and holes, and then on that loop there is a particle hole interference that gives rise to these fringes. Yeah. So anyway, so I think that's good. So this is what we're looking at now, and anyone interested, happy to talk about that afterwards. So thank you.
Thanks. We have some questions. We should probably move on, and unless there are super burning questions.
I just want to understand, from, which, parameters you build, pseudoscalar. I mean, you have three coordinates, you have, let's say, magnetic field, but how symmetrically I can, write high is proportional to what?
So let's say, I mean, take the simplest example, take no Berry phase, just ordinary parabolic band of electrons, magnetic field applied. Then the spin chirality will be function of distance, will be decaying with distance, and the value will be proportional to, I mean, will be proportional to applied magnetic field, will be proportional to parameter.
But magnetic field is vector, so I need another normal vector to calculate the scalar product.
No, so this is a 2D problem. So in 2D problem, magnetic field is perpendicular to the plane of motion, and particles are moving in planes. So it's a transverse field component.
It's perpendicular to the plane of 1 and 2, right?
Yeah.
Okay, so in 3D, this is that doesn't exist.
Okay, in 3D, there is a 3D extension of chirality that we can talk about later. But in 2D, which is simpler and also relevant for various systems, it's a scalar.
And if you break your time reversal by random magnetic field, not by uniform, you will have random chirality.
Yeah. Yeah, maybe a quick answer to a question about what happens in 3D. So in 3D, there was a good picture at the beginning. Okay, so in 3D, if you have 3 points in 3D space, chirality will be the spin vector triple product, but as a vector, it will be pointing normal to the plane of the triangle. So you can think of it as a vector like that. I mean, not completely true. There will be other contributions, but a zeroed answer is that it will be normal to the face of the triangle. All right,
Okay.
done.
All right, that's fine for now, So for all future speakers, just to make sure, so try to go to the website. I assume you're on Wi-Fi. Click the Zoom link and be on Zoom, because the idea is that you don't plug in, you just be on Zoom.
What shall I do?
I'll do it for you. Are you online?
Yes, just.
Very easy. If you go to the website. I learned this in Germany last summer, that just don't have to mess with plugs or anything. Zoom works. Okay, about Germany. Where? No, we don't want this. Okay. Continue. Fine. Just share your screen. Let's start. Okay. This one?
Yes.
Okay, share. Oh, yeah, okay.
Yeah.
That's it? Oh, wait, let's close, let me help you close this stuff. Want to go
Full screen is here.
Okay, good. Oh, it's F5. No, back. Okay, very good. All right, how far are we?
Okay, good morning. Thank you very much for inviting me. And what I'm going to present is the paper which Emil Yuspashan did with some of my help. And after we made some calculations, experimentalists from originally from Russia, but now working in China, contacted us, and we actually started to collaborate. And also former Emil student Aniket Petra was helpful in on some stages of the paper. So what I want to discuss is actually the story which emerged pretty recently, and at least in this picture, it looks like a revolution, because what is plotted here, here it is year of discovery, and here is temperature of the superconducting transition, as and in 80s, early 80s, as you may remember, for some of us may remember that there was a very big deal with cuprates, and it was called high temperature superconductivity. And recently, almost together with COVID, there appeared another set of materials with much higher transition temperature, and now it's not even very convenient to call cuprates high temperature superconductors. However, it was not as a big deal as cuprates, in spite of the fact that there was so dramatic increase in transition temperature, because what happens in these materials, which are called hydrates, is the fact that all this can be observed only at high pressure. So to give you a little bit of the history of the problem, it started by a paper of Widner and Heitington, who claimed that under strong enough pressure, one can get hydrogen, which would be metallic, and they strongly underestimated the pressure needed. They thought it would be about 25 gigapascal. It was, as people believe now, about 500. To tell you the truth, it's nobody still reliably observed this metallic hydrogen, but this story still had development, initiated to some extent by a paper of Neil Ashcroft, who claimed that if we would have this metallic hydrogen, it would be really great, because its transition to superconductivity temperature would be huge, and this indeed is correct. Now people believe that it would be much higher than the room temperature. And this initiated a lot of experimental activity, but for a while the goal was not reached. And then there appeared another direction of this research, connected with the idea that this pressure needed to get metallic hydrogen is too high. It's not even very clear how to reach it. However, you can share the burden of creating high pressure with chemistry. In other words, if you make systems with large percentage of atoms being hydrogen, but with small addition of other atoms, you can reduce the pressure needed for getting a stable metallic and then superconducting state to the values which are already standard in a well-equipped lab. So we're speaking, roughly speaking, about this type of lattices where green balls are hydrogens and there are other balls. In this particular example, it is lanthanum. And indeed, you can get materials which around 150, 200 gigapascal demonstrate superconductivity at temperatures up to 250 Kelvin. And this is something that community agrees upon. Now, to demonstrate how it looks in reality, I show this picture, and I have to admit that when I was not in this field, I thought that you need pressure to press this material towards superconductivity. In fact, it's not the case because if you start with high pressure and then keep reducing it, transition temperature actually increases. But what happens is that at certain critical pressure, system starts to become unstable. What experimentalists tell that this lattice start to lose hydrogen. So in other words, couples of hydrogen get together, form a molecule and fly away. And as a result, the transition temperature drops dramatically, and nobody really could explain me what kind of material we have here, if it's indeed something interesting to study it, but not just some kind of
What do you mean
trash.
by that? I mean, you melt crystal, I mean, you increase pressure and you change lattice, what means unstable? You
Unstable
break
means
lattice?
it loses hydrogen, so this lattice is unstable.
It's not the ground state.
And then what it is,
Nobody knows what was the ground. state.
yes, so
Okay.
I asked, try to convince them, and maybe they will do it, is to look for hysteresis, so increase pressure from this point up and see what we have. But I mean, it's not always that experimentalist follows your.
Particularly when they want to increase something.
But so in the structure on the left, that's the high TC,
Yes.
but what is the difference between that and low TC? Like, so what,
No, there is nothing like low TC. There is nothing like crystal made from lanthanum and hydrogen. What you get phase separation. I don't know. Maybe there is
So-
some kind another stable concentration.
is already metallic hydrogen or not? Is it,
No, this system is metallic.
it is metallic?
But it's not
But
hydrogen.
if you take away lanthanum, it will blow up.
No, I understand.
So, yeah, actually, I want to clarify this. So going back to Ashcroft's idea, the idea is that if hydrogen atoms are the phonons that are mediating, because it's light,
Yes.
TC will be high. So I think Ashcroft didn't think of actually like the lattice where this could realize, yeah, I was just thinking. Whereas this is a real lattice where the hydrogen the hydrogen phonons are the ones mediating. Is that basically the physical? Okay.
Yeah.
It doesn't matter where the electrons come from, actually,
I see.
right? It's the phonons.
Yeah.
And if I remember, Aramitz, who died recently, he was very heavily influenced by some DFT calculations of phonon band structure and how to make this stuff.
I will speak.
Yeah, okay, sorry. I'm just trying to connect.
Okay, so now what I want to do, I want to, put aside for a short while experiment and remind what happens when you start to try to understand what is the limit for transition temperature. Is there any fundamental limit? And one of the important papers in this direction was paper of Phil Anderson together with Marvin Cohen, who I don't want to discuss what they did, but there was an ingenious idea that indeed the transition temperature is limited by lattice instability, which takes place when coupling between electrons and phonons becomes too strong. Now, very quickly, everybody who is not in this particular field calls theory of superconductivity is BCS theory. And indeed, you have the equation for delta. Parameters that are involved here are the bifrequency and coupling constant, BCS constant. But what is important to mention is that it's not its model, it's not a quantitative theory, because there is no way to kind of independently determine or calculate these parameters over d, omega d and lambda. The only quantitative relation that BCS theory gives is a relation between TC and delta, which experimentally is qualitatively okay, but not at all exact. And also, what people understood very quickly, even before BCS theory, is that there is isotope effect. So if you substitute atoms of your lattice by their isotopes, which should not change any chemistry, it will still change transition temperature, and it was considered to be evidence for the electron phonon nature of the superconductivity. And indeed, interaction between electrons and phonons, as we know, is a good fraction of condensed matter theory. And what would be nice to, if not to calculate, at least connect the parameters that you can measure by different experiments with the what these parameters would predict for the superconductivity. Okay, now there are several approaches to the electron-phonon interaction. In principle, you can try to write Hamiltonian. The simplest Hamiltonian is probably Holstein Hamiltonian, which involves interaction between electrons and Einstein phonons, which are basically oscillators living on each lattice ion. This is the interaction, and you can make more linear Hamiltonian where your phonons have photon dispersion law, and you have usually fermion-boson interaction of these particles. And in particular, the bimodal is when you substitute linear dispersion law to the Froelich-Hamilton. Now, the real theory of interaction between electrons and phonons was developed by Arkady Migdal. He thought he calculated everything and was surprised that he cannot get idea of where superconductivity comes from, but it was before BCS. He did not know about Cooper phenomena, but as soon as it became known, Gerasim Eliashberg actually extended Migdal's theory for the superconductivity, and this is resulted in what we know now as Migdal-Eliashberg theory. And there are two important things to take into account. One is that effective interaction between electrons, which is mediated by phonons, is retarded, and that's why uh, usual thermoliquid ideas are not directly applicable. And second, which is important to understand, that we have to take into account effect of phonons on electrons, but we don't need to normalize phonons by I will tell a little bit more about it in a second, but just steps how we derive these Migdal-Eliashberg equations. You basically take the Lagrangian in imaginary time that corresponds to Holstein, for example, Hamiltonian. You can do the same for Fröhlich. And what you are doing, first step is to integrate out these phonons, this excess. You can do it because it is quadratic. You end up for fermion interaction. Then you split this in usual way by Hubbard-Stratanovich fields, and then in an effective theory that involves this Hubbard-Stratanovich fields are nothing but normal and anomalous self-images, you find the stationary point, and this stationary point is Migdal-Eliashberg theory, and you can formally demonstrate that fluctuations near the stationary point actually can be neglected when Fermi energy is much bigger than all other energy parameters in the problem.
Can you elaborate?
Yeah.
Say why do electrons not be normalized to phonons?
Mhm.
I mean, the
Yeah.
whole definition of phonons, you do the Born-Oppenheimer and you derive the elasticity and
Mhm.
from the electron. So how
Yeah.
is it not? How is it
No, the reason is the following, that in contrast with usual, let's say, electrodynamics, when you have electrons and you have photons, and electrons exist without photons and photons without electrons, phonons are already the objects that appear on the top of the particular lattice structure, and electrons take important part in formatting this lattice. And that's why if you take your Hamiltonian seriously and try to renormalize the everything using usual field theoretical approach, you can start double counting certain contributions.
They're already, you're saying the definition of phonons already came from.
Yes, yes, and I will give you a simple example, which for the reason that I don't understand took people some time to resolve. But the point is indeed that if we want to connect properties of, let's say, superconductivity with another experimental data, like measurement of certain characteristics of phonons, these phonons are already renormalized by electrons. Okay.
Can you say that this renormalization comes from high energy, electron high energy?
Yes, but what I guess I want to tell is that if you are doing numerics for electron-phonon interaction, start with ions and electrons, and try to get your lattice and your phonons, but not consider this Hamiltonian as as a starting point, because this all the
It's already effective.
yeah.
No
But
lattice without
but-
electrons.
But how does the field theory know? Like if you formally just compute corrections to the photon spectrum, you will have correction from.
Yes,
from which
yes,
you have-
yes,
So
yes.
you're supposed to throw those out, or what are you?
Look, give me a couple of biographs and I will return to this questions later. Okay, so the question is, can we just extend this theory to arbitrarily strong electrophonon count. And this is what we will have if we indeed would naively start with, let's say, Hall-Stein Hamiltonian with zero strength shape spring, and then what we will get here also should be zero, and here zero. Sorry, we will get certain effective retarded interaction between electrons, and frequency will be determined by this k, this frequency, and you can introduce dimensionless coupling constant, which is g squared divided by omega z. And if indeed you will try, let's say, RPA renormalization of the phonons, putting all these loops as it is prescribed, what we will get that we'll get that effective lambda, which involves renormalized omega, will be equal to lambda naught divided by 1 minus 2 lambda naught, which means that lambda naught in this Hamiltonian cannot be bigger than 1/2, because then lambda diverges. However, the question that we want to address is not about lambda naught, because nobody can measure it, nobody knows anything about it. The question is there any restriction on lambda? Because when lambda naught approaches to 1/2, lambda goes to infinity, and the question is whether lambda can be arbitrary. Yes?
So this kind of singularity that you observed, is this the same one that I would have had in Pyros instability?
It's all the same. It's just RPA, which is always like that.
But in 1D, it will just always be basically any lambda will lead to instability.
Yeah. Yeah, but we're not about
But then
one.
instability does happen at K Fermi, and then it just, lattice deforms and opens up the gap. So how can you approach transition if you throw away momentum? Like this theory, Migdal-Eliasberg, has two bad features. First, it ignores Coulomb and it replaces it with magic
No.
number.
Yeah.
Okay, fine.
Yeah.
So and then it pretends that there is no space. Right? So, but is it really kosher to do that if you know?
Again, give me 5 minutes.
Okay.
But also,
He has 5 minutes.
Yeah.
Already.
He literally has 5 minutes.
I mean, if lambda is infinity, the scale is omega d pi. So how, so I don't understand if, you're bounded by omega d pi, right? Which is-
I don't know what is omega d pi. Right now, I don't know anything. I have my phonons. If you want Debye model, it's Debye model, but let me be more generic. Again, I need some time to go through it, but how it's really described. What's going on?
You read that one?
Okay. What is important to understand that in the limit of strong coupling, when our lambda is large, and this is only normalized lambda, so I don't have to do this, everything becomes universal, because remember, effective interaction was omega square plus this, but if omega m minus omega m is much bigger, I just forget about characteristics of phonons, and my interaction is universal. And for this interaction, it's well known from 70s that transition temperature is proportional to square root of lambda and to the frequency. And these are two independent parameters, so lambda can be arbitrarily big, omega is independent. Just you see that what happens is a strong coupling has nothing to do with the weak coupling and all these BCS formulas. But what is more important for us now is that it looks like this formula can be extended to arbitrary large lambda and give us unbounded TC.
So could I understand it simply that asymptotics at small lambda is this exponential
Yes,
law and at large lambda is the square root?
Yes.
It's just two limits, okay?
Yes. but at large, at small lambda, you need again this omega. Okay. So the question is, can TC and lambda be arbitrarily big, and whether Migdal-Ashberg theory predicts it. And I have to be quick. So if you ask later, I will tell you some details of the calculation, but this is expression of the specific heat, which can be expressed in terms of d gamma function and its derivative, and this is something that was probably obtained already by Prange and Kaganov, but in this work of Lee and Reiner, it has exactly the same form. And what we, together with Emil, we found a way of considering reformulating this theory in which this equation appears quite directly. But I'm afraid that there will be no time for me to elaborate. So what I want to tell that this equation is correct in general if lambda is much bigger, or in the limit lambda to infinity, but for Holstein-Hamiltonian, it is indeed correct as long as system is in the normal state. Now the question, why do I need to speak about specific heat? And the answer is here. I don't know why previously it was not mentioned, but it turns out that specific heat at a small enough lambda has this interesting peak and then goes to certain value when temperature increases. But what happens when lambda exceeds certain limit, which is about 3.7, it looks like there appears an interval of temperatures where specific heat is, I'm really sorry, when it is negative. And negative specific heat is a catastrophe because it means that system is unstable. And
So this is in a normal state, right?
this is in a normal state at temperatures above, above transition temperature. So when you start cooling your system from high temperatures, you
When is the transition temperature?
Yeah.
Oh.
Okay. Now one argument against it was that it's only electronic specific heat, and phonons also have their specific heat, which is much bigger, and that's why total specific heat is also positive. That's why it's maybe not important, but we had to do some calculations based on analysis of Boltzmann equations, and the conclusion is that actually in this case the usually stable state when temperatures of electrons and phonons are the same is unstable. It is stationary point because collision integral that is proportional to this well-known combination of fermionic and bosonic distribution function is indeed vanishing. However, the sign is pathological, and because of that, this system is unstable, electrons increase their temperatures and photons.
Jefferson, I don't understand. If it vanishes. would it
Every
also-
small fluctuation, it's unstable
It's
stationary
clear,
point.
it goes from lattice to
Yeah,
electrons,
yeah.
because one has a negative
Yeah,
specific sure. It's unstable, breaking into two
Okay,
different
so
temperatures.
this is indeed the reality, and we can consider the limits on the transition that is imposed by this instability. Now, to start with, when you go in a old reviews which contain values for lambda, you will find that in conventional superconductors, there are some compounds based on lead, where it is close to 3, but never exceed this value. And what our experimental collaborator Dmitry Semenyuk did, he analyzed all the data for hybrids, and indeed there is nothing with lambda bigger than 3.9 observed. There are one or two compounds that are theoretically predicted to have lambda bigger, but it looks like they do not exist in reality. Now, let me try to answer the questions about the generic case. So there is important characteristic that appeared already in the paper of Eliashberg, which is known as Eliashberg function, and it is basically photon density of states weighted with the coupling constant. So indeed, there is space, there is Q, and you have to sum over Q. And this is a function. So for whole-state Hamiltonian, it would be delta function. For Debye model, it is quadratic, but in general, it's something like that. And if you compare it with Eliashberg functions that are known for conventional materials, this is for, let's say, for zinc, it's more or less of the same type of function. God knows where there are acoustic phonons or optic or whatever, but what you can see is that, so this is about 40 terahertz for frequency, and this is about 4 terahertz. So basically in hybrids, the characteristic frequencies are about 10 times bigger. And since TC is proportional to frequency of the phonons, this 10 times bigger would give you, instead of 2 Kelvin, 20 Kelvin, but it's still unclear how it gives you 200. So it's not only large omega, as Neil Ashcroft mentioned, but also strong coupling. Yeah, yeah,
If
sure.
you compare it with real materials, so it's not just one phonon branch. There are
Yes.
base phonons.
It's all phonons. You sum
So you-
over all phonons.
So you throw all the phonons
Yes.
and actually calculate the truth.
Yeah, yeah.
And how do you know, like, all the coupling and everything? Like, you keep-
Oh, no. This is another story I forgot to tell. There is a way to measure the Eliashberg function experimentally using tunneling data. It actually started in Kharkov by Janssen, and then it is now quite developed and widely used. What is the name of this gentleman from PNL whom I was talking about, this HGC staff who was doing this?
Kabozevich?
Yeah, probably. So you can just measure. Idea is pretty simple. Original idea of Janssen. I don't know details of modern, but original idea is that if you make a microcontact, so kind of barrier, small hole, you can study IV characteristic of the current through this hole. And in second derivative, you start to feel of the IV characteristic, you start to feel the effects of emitting or absorbing the phone. And it connects coupling constants and so on, and you get pictures for the second derivative, which basically give you the. But at the same time, people, some of the things that I'm showing here is a result of numerics, and this is standard numerics where almost everybody here understands more than I do. Okay. So if you will try to formulate the stability condition in the form of the in terms of Ellsberg function, what you will get is that this convolution that we call psi of the Ellsberg function with this function that I previously called H. I'm really sorry for that, but it is the same combination of the gamma functions. This convolution should be smaller than 1. And I want to emphasize the fact that it is condition of absolute instability. In fact, as we know, for example, if it would be usual first order phase transition, it can happen before one of the phases completely loses its stability. So it's basically necessary condition for stability, but by no means sufficient.
A silly question. What is the small parameter of the theories if lambda is large?
Well, the only parameter is whatever you want divided by Fermi energy.
Fermi energy is large, yeah.
The ratio of masses,
Yeah.
the
Yeah.
mass of electron over the mass.
If you want.
It's the same small parameter.
Yeah. Now, this is what people show us how Ellsberg function evolves as a function of pressure. So this is high pressure, this is low pressure. And indeed, you see that when you reduce the pressure, the characteristic frequency slightly decreases, which is bad for the superconductivity. But what happens is that there is a peak at low temperatures, which is dramatically increasing, and it is not impossible that this peak is responsible for both high temperature increase of the transition temperature and losing of the stability. And this is lanthanum deuterium-10, this is lanthanum H10. Indeed, we have some isotope effect, but this property of this big peak is increased. Now, what maybe I will accelerate a little bit. So what about our?
Can you finish in a couple of minutes?
Yes, yes, yeah. Yes. So if you will calculate this value of psi for different materials at the stability point, you will see that it never goes close to 1, but it is kind of concentrating near the near 0.5. And this is how it looks graphically. So all these materials have much higher psi, so they are close to instability, but nothing with psi above, strongly above 0.5 was not really observed as a stable material. Although if we would keep the energy, keep the system stable and keep at the same time reduce pressure, we will get much higher transition temperature and probably can go to the room temperature. Now, a little bit of speculation that indeed everybody recalls spirals transition because the way what electrons want and they use it if they have enough electron phonon coupling, they want to organize a gap on the Fermi level because then you push some of the states down in energy and reduce the total energy of the system. And one of the ways is to make an insulator change the lattice structure that will give you a band insulator. But another thing is that going to superconducting state also means that you have a gap in the on the Fermi level. And then the following idea appears. Let me show it on the cartoon. Let's do the following. So this is a cartoon of, I showed you transition temperature increases, but then system breaks down. So let's at high pressure pull your system to a superconducting state and then reduce the pressure already in this superconducting state, and then let's see at which temperature it will disappear. And it looks like if we are correct, superconductivity actually can enhance stability of the system, and we can get into superconducting state with temperatures already higher than what we can get in normal protocol. And it looks completely like fantasy, but there is a paper done in Dallas in the group of Paul Chu about different materials, ferrum selam, where what you normally have is transition temperature about 10 Kelvin, but under the pressure it goes up to 40 Kelvin. But what they demonstrated, if they will take the state of high pressure and then reduce the pressure down to ambient pressure, then system will still remain in this state with high transition temperature, and what is claimed in the paper that it survives for at least about a week. So this metastable superconductivity can be in fact stable enough. And these are my conclusion, but also I was afraid that I will not have enough time, but following Emil's suggestion, I want you to give you the answer to the question, what is actually the limit of high temperature of transition temperature. And the answer, let me skip all these arguments because if you want, I can repeat them, but this is the statement that if you indeed believe that critical psi is 0.5, not 1, then transition temperature can be estimated at 600 Kelvin divided by square root of atomic number of the lattice sites. And this only means that everything but hydrogen are not good for this, and for room temperature superconductivity. And second, if indeed we use hydrogen or deuterium, then high temperature superconductivity is not impossible. The problem is how to make the system stable. Thank you very much, and sorry for the language.
I thought there was miscommunication, that's why I haven't heard you speak in a long time, so it's partly insulting, okay.
Can you explain what controls the crossover between the BCS exponentially weak coupling and the square root of lambda coupling? What energy scale?
No, usually BCS equation appears when transition temperature is much smaller than characteristic Fourier temperature.
Right,
Like TC is smaller than
right.
omega. We are now speaking about situations when it is at least of the same order, is not bigger. And then, of course, all this.
So this is the retardation effect, so they,
It is a retardation effect, but also by construction, BCS is a weak coupling theory. It is, we neglect all high order renormalization.
but it's still, Fermi energy is still large, you still degenerate, it's still.
Yes, yes,
degenerate
yes,
pairing.
yeah.
It's not like a molecular pair.
No, no, but formally, when you consider BCS model, so this
Yeah.
two particles are so four particle interaction, but only this particular one. Then, in order to get this equation, you need also to assume that it is in a certain sense weak. Because if it is strong, you will get some strange peaks and all this stuff.
Algebra is also weak in the sense of Fermi energy, it's also still weak.
No, no, again, it's matter of definition, but this lambda G divided by omega square is not small. Yeah.
I have a question about the 0.5. So the 0.5 radical lambda appears at the basic level of RBA. If you start including corrections, it will get.
No, no,
Well, I mean, Chubukov, Gibbels, and they've been, doing it.
no,
So,
no, psi, no, 0.5 and lambda 0.5, completely.
okay, okay, I thought it was the same thing, but
Not
I'm
at all.
talking about lambda zero,
Yes.
1 minus 2 lambda zero. So this thing, is artifact of your approximation. Your
Not even an
material.
artifact. I agree with you. I agree
Like
with you.
RBA.
Lambda zero is not physical object because itself is not observable. There
But
is
no,
no,
we're showing this plot, which is experimental plot, heuristic plot, where there were like kind of materials that something would happen. around
yeah,
0.5.
but-
What is actually 0.5?
no, there is parameter psi, which is determined from the Leibniz function. So it's not, it's based on the Leibniz function. And this condition can be correct or not correct, even when lambda naught is smaller than 1/2. I mean, it has nothing to do with this condition. What lambda naught tells you is basically that lambda can change from 0 to infinity. And what we're telling you that it's probably limited, and depending on the spectrum, limit is either 3.9 or maybe slightly different, but there is this psi which is, yeah.
Quick question. So your theory seems to be translationally invariant to effective action. So if we take into account the lattice, will there be some change in numbers?
I don't think so, because formally this is taken into account when you take into account all branches of form. If it would be,
But what about electrons? Because now your Fermi surface is not kind of sphere with some.
I don't think it will change anything. As we know, there is
Some number can change some number.
no, everything goes.
No, the structure of the theory will be the same, but the bottom line.
What I want to tell is that everything that you want to know about a particular spectrum of electrons and phonons goes into effective coupling quantum, and in the long run is only taken into account by Leibniz function, which knows about the electron phonon
Yeah,
coupling.
I'm not questioning the applicability of electric theory, about the final answer. You wrote the final prediction for the maximum. Will this number?
Yes,
change?
I think it will change. I think the asymmetry will change it somewhat. I mean, but still you'll have some upper bound.
Okay.
That's what I.
Good. Last question.
Yeah. Can I apply this theory to other systems, operates?
Okay, first of all, tell me if superconductivity incorporates is phonon based or not. If yes, then be my friend and go ahead. But if not, this
So let's say it's phonon. What would, has anyone did this analysis?
I think people did. I simply don't know the result.
What does it predict?
Uh,
I guess not.
Again, different people will tell me different things, but I'm not an expert. There were,
Okay,
So I can say something. So
yeah, he's actually getting the next talk, maybe that's.
oxygen is the lightest element in cuprates. And so if you use A equals 16, you'll get a number that is above all current, highest theses for cuprates. So empirically it works for cuprates, but of course, I mean, we don't claim the theory is applicable for cuprates because we don't know if it's, the same mechanism.
Okay,
Thank you.
all right. Good.
That was S-way, right? That was S-way.
This was S-way, yes. Also, this was S-way, yes.
Okay, Emil, you promised to do it in 25 minutes.
I didn't promise. I'll
You
try.
promised to try.
Yes.
Yeah, let's try to stick to the schedule. That way we don't have too short of a lunch. Is everything okay? You're not sharing.
Yeah, I'm just. I think I have to make this close. Wait, oh. Okay, so Vadim, disappeared, so I'll be the chair also.
Good chair.
Okay, so, so I'm going to talk about also about superconductivity, but, about something different. So we learned, early on that superconductivity is a macroscopic quantum phenomenon. But on the other hand, theory of superconductivity is a mean field theory. And mean field approximation, combined with Ehrenfest theorem, imply that the theory is classical, in fact. So if mean field is exact, then superconductivity is a purely classical phenomenon. So the question, is this true? And is mean field exact for a macroscopic superconductor? So, I will just do weak coupling theory, BCS theory. So, here you have a BCS Hamiltonian that describes, pairing in some arbitrary single particle potential. So you have, the single particle term and then the interaction that takes, a time reverse pair of electrons from level K and, to level J. So if the single particle potential, has some additional symmetry, so for example, is translationally invariant, then you'll have, also a momentum quantum number. And then this will be, time reverse pair will have, opposite momenta, and this will be like, P minus P, Q minus Q that you might be more familiar with. So here, K and J are energy labels. So singly occupied levels decouple, the interaction doesn't see them. And for the remaining levels, you can map exactly the system to a spin 1/2 Hamiltonian. So, here is the mapping. Spin lowering operator is pair annihilation operator, spin raising is pair creation, and the Z component of spin is related to the occupancy. So these red arrows here show the spin, and then this becomes a spin 1/2 Hamiltonian, the BCS Hamiltonian. So let's look at the equations of motion, at the exact Heisenberg equations of motion for this Hamiltonian, because the commutation relations for spin, as you do commutation relations and Poisson brackets for angular momentum have the same form. This also has a form of a spin precessing in the collective field created by other spins, but here all this, things L per, which is the xy component of the total angular momentum, these all things are operators here. So now the mean field approximation consists in replacing the total spin with its expectation value, which I'll call capital L. So if you do this in the equation of motion, it becomes linear in the operators. And if you take one more average of this equation, before that, let me say that this means that spins decouple, individual spins evolve not independently, but in their own magnetic field. So which means that it's a product of spin 1/2 wave function. So the wave function of the mean field wave function is then of this product form. So if you take one more average, then you see that the expectation values of the spin 1/2 behave as classical angular momenta or classical spins. So if I denote capital Sj as the expectation value of little sj, then I have this classical Hamiltonian, equipped with classical angular momentum Poisson brackets, and equations of motion for this Hamiltonian are exactly these equations of motion. Okay. So now, what is the status of this approximation? So Anderson argued early on that mean field is exact for the BCS model because it's exact for models with infinite range of interactions, specifically because L here is a sum of large number of spin 1/2. Its quantum fluctuations should be negligible as long as the expectation value is macroscopically large. And this is the case for low energy states, but for highly excited states, macroscopic number of excitations, the expectation of L is of order 1, and mean field in principle breaks down or can break down. So, and there is a rigorous proof of this because the BCS Hamiltonian is Bethe-Ansatz solvable. And so Richardson proved that mean field is exact for low energy states starting from Bethe-Ansatz solution. And then all observable equilibrium properties of superconductors, such as excitation spectrum, Josephson effect, topological properties, let's say of P waves, P plus IP superconductors, are low energy, and they can be obtained entirely from this classical spin angular momentum Hamiltonian. So therefore, you don't need any quantum mechanics to actually describe at least low energy equilibrium superconductivity. So it admits a fully classical description.
Sorry, Emil, but this is only true if you don't have single particle excitation. So this is artifact of your model if you wrote in step 1.
No.
The moment you write like momentum, 3 momenta in your interaction, you will have non-integrable system with quasi-particles and all that stuff, and none of this is going to fly.
So
like real superconductors. Is it not true?
I mean, for real superconductors, for low energy, the Hamiltonian, this third momentum is irrelevant. Becomes irrelevant, right? So the mean field still works. We know that BCS mean field is still good, right?
So as long as there are no fermions, you're fine. As long as there is an excitation, a fermionic excitation. Well, this theory doesn't have process. You can break up a Cooper.
Yeah, it doesn't have.
But
But this is the BCS theory.
Any real Hamiltonian, of course, does have it.
Yeah.
So
okay, but the approximation where you don't have them, is good in certain cases.
Yeah.
Right? So and I'm talking about those cases.
Okay.
Imagine there is your classical, there are no fermions, no nothing. There's still superconductivity. It's a phenomenon, just it exists as a phenomenon. In the classical world, H bar exactly equal to 0, identical.
Charge matter wave couples.
Exactly, that's what I'm saying. So it's just fermions.
Yes, Brookman-Down.
So it's bar 0.
Okay. So, but, in the past 15 years, far from equilibrium, BCS dynamics has been observed in a number of systems, like in cold Fermi gases, in cavity QED, and in terahertz pump-probed superconducting niobium films. And this triggered a large number of papers in this area. And by far from equilibrium BCS dynamics, I mean coherent dynamics with the BCS Hamiltonian. So, but all these papers, which come basically like at least once a week, they do mean field. But on the other hand, far from equilibrium, in principle, highly excited states contribute to the dynamics, for which mean field is invalid. So previously we talked about equilibrium, but now we can ask, does mean field break down far from equilibrium, or is it still valid? So we are interested here in a unitary evolution with the BCS Hamiltonian, and the natural way to initiate such an evolution, for example, in ultra-cold fermions, is to drive the system by making the superconducting coupling vary in time. Then we will have to solve for the dynamics of this time-dependent quantum, spin 1/2 Hamiltonian. Yes.
So, I mean, it can break down in two ways. That approximation you made for the BCS Hamiltonian, replacing by averages breaks down. That's what you're considering. But BCS model itself, where you have to go to non-zero Cooper pairs and non-zero momentum, can break down.
Yeah, absolutely.
So-
So
so you're
here
all
I'm looking
first effect.
within the model. Yeah,
Okay.
so I have this model, and there is a mean field approximation for that model,
Right.
which makes it classical. So I'm looking whether, when quantum sort of effects in this model are important or not.
But do you understand the second set of effects, whether they may become important at the same time as your effects?
They can become, important also in certain circumstances, but not for a bulk, superconductor.
But Cooper pairs are final momentum, why can't they not be
Not-
outsiders?
They can, but it's a much slower process that occurs at much later times. That is, it's like the characteristic rate for that is like delta squared divided by Fermi energy, while the characteristic scale for this kind of dynamics is 1/delta. So as long as the Fermi energy is much larger, this is something that will take place much later. But in principle, here I'm looking at this model. Okay,
Right.
so
No,
this
I
is
understand.
a model study, that I want to focus on. So what do we need to determine if mean field is exact? Okay, so we would need to solve the non-stationary Schrödinger equation for this quantum time-dependent BCS Hamiltonian exactly. And then we'll also need to solve the corresponding classical, equations of motion, the classical version. From the classical version, knowing the expectation values of spins, we can reconstruct the mean field wave function, and then we need to compare the quantum and exact mean field wave function. Okay, so quite clearly, this is generally an impossible task, both numerically and analytically, for an interacting many-body quantum system, even when the underlying time-independent model is integrable. Normally that wouldn't help you too. And here is why. Here is why it doesn't help you. So let's look at any like conventionally integrable model. So for example, like a poster child of integral models, one-dimensional Hubbard model. So this is a tight binding model plus on-site Coulomb interaction, but I'm just using this as an example because I had slides with Hubbard model. I can use, for example, XXZ or BCS, any other integrable model. So there is a parameter here, U. So what Bethe-Ansatz solution gives me, it gives me the eigenvalues and eigenstates, for any U, right? And also exact eigenvalues and eigenstates. And also another signature of this kind of time-independent integrability is that you have in principle infinite sequence of integrals of motion that depend on this U. So in the case of the Hubbard model, they are polynomial in U. So the first one like the Hamiltonian is linear in U, then you get quadratic, etc. So they all commute between themselves, and they commute with Hubbard Hamiltonian. So classically, if there is a natural classical limit and integrability, this commutation property persists in this limit, which is true for BCS but not XXZ or Hubbard, then you'll get classical integrability semi-class on the mean field level. Then mean field dynamics is going to be integrable in the classical sense, in the Liouville-Arnold sense. And there are many more powerful tools in classical integrability than there are in quantum. So you can use this extensively, and we use this extensively to predict the mean field dynamics of BCS superconductors, let's say after a quantum quench. So if you do a quantum quench, and after quench your interruption is time independent, and you can use this. But now we want to do something different. So now, what we want to do is we want to make this interaction U in the Hubbard model, or G in the BCS model, a function of time. So in general, as soon as you make it a function of time, this breaks integrability. So for example, if I look at the time derivative of one of the previous integrals, so it still commutes with the Hamiltonian, so this term is zero, but this term is non-zero because U depends on time. So you lose all the integrals immediately.
Only adiabatic invariant survives, right? Exponentially, if you slowly change it.
Yeah, if you slowly change it for a classical system, but I'm not even changing it slowly. So here I'm considering changing it fast. I mean, not necessarily fast, but not at any non-adiabatic. Okay. So also the Bethe-Ansatz solution is not particularly helpful because even though the eigenstates of the stationary Schrödinger equation, now they are, exactly adiabatic eigenstates. And but the system can tunnel between them. So you can write your wave function, let's say, in this basis of Bethe-Ansatz states, but that's doesn't help you. It's just rewriting the non-stationary Schrödinger equation in terms of these coefficients an. So the problem is that these coefficients are going to be time dependent and are going to have their own non-trivial dynamics, which is the Landau-Zinner tunneling between adiabatic states. So you have here this Landau-Zinner dynamics on top of the exact solution of the stationary Schrödinger equation. So the question, in other words, is can we make parameters of integrable model, like U in this case, time dependent without breaking the integrability, in a sense that the non-stationary Schrödinger equation is exactly solvable. So in other words, can we have integrable Landau-Zinner dynamics? And the answer is that yes, we can, at least for some models and certain time dependencies. So in particular, the BCS Hamiltonian is special. So here are the integrals of motion for the BCS Hamiltonian. So I rewrote the coupling constant G as 1/2b for convenience. So this is the BCS Hamiltonian here. So they all commute with each other and they commute with the Hamiltonian. So the BCS integrals of motion are, these Hamiltonian that are known as Godin magnets, and they are not just any round-of-mill, integrals of motion. They have some, special features. So in particular, they determine endpoint correlation functions, which is here considered as a function of these epsilons in SU2 Vesurino-Witten conformal field theory through n compatible equations of evolution type, like this kind of equation. So now these epsilons are considered like complex parameters, and you can show that all these equations known as Knižnjik-Zamolodchikov equations, they are compatible. So you have a unique solution for all of them. So in the original Knižnjik-Zamolodchikov equation, actually this boundary term is absent, and but I mean, you can show that you can add it as well. And then it turns out that the evolution of the wave function, of the correlation function, which now depends on this additional parameter B, is governed by the BCS Hamiltonian. So this equation is also compatible with this set of equations.
Okay, it's some
Means it's highly degenerate.
dialogue.
Somebody's asking a question?
So let's take, then this equation, and let's, for example, take B equal to nu t. Then, this equation is going to become, nu will cancel on the left-hand side, and it's going to become non-station Schrödinger equation for the BCS Hamiltonian with superconducting interaction inversely proportional to time. And in principle, I mean, this kind of time dependence is natural for ultra-cold Fermi gases, where the interaction strength is inversely proportional to the distance to the Feshbach resonance. And if you are far enough from the resonance, then this model will be applicable. So in principle, you can try to engineer this kind of time dependence in cold gases. And then a natural problem in this context is to start in the ground state at t equals 0 plus. That means like very large coupling strengths. And in that case, the ground state is a state with a maximum number of the maximum total spin, which is going to be n half if I have n spin 1/2, and a certain z component which corresponds to fermion number. So we now evolve the system to infinity and determine the asymptotic wave function. Okay, and so we will use this many-body Landau-Zina type problem to test the accuracy of the mean field approximation in this model far from equilibrium. Okay, so here is basically how we solve this. So there is a general formal solution of Nizhny-Zamolodchikov equations in terms of m-fold, where m is a number of Cooper pairs, contour integral over off-shell beta ansatz states. So this was developed originally by Babujan, and then Babujan and Kitaev, as well as these people, extended this to include the magnetic field B. And then, according to what I told you, this gives us automatically solution of the non-stationary Schrödinger equation for the BCS Hamiltonian with coupling inversely proportional to time. But the solution is, horrendously complicated. But it turns out that asymptotically at large times, this integral, like this multi-dimensional contour integral localizes to the stationary points of the Yang-Yang action. And basically this allows us to solve the problem exactly for spin 1/2. And then we separately solve it for when spin goes to infinity. This gives us a classical solution. And so now we can realize this program, and we can compare exact quantum solution with a classical solution. So here is the exact quantum solution. I emphasize that this is exact for any number of spins, any number of single particle levels, and arbitrary number of fermion pairs. So here, this alpha is just fermion occupancy basis, you could say. So alphas, they label doubly occupied states. The remaining states are empty. So, for example, if the first state is doubly occupied, the second is empty, and the third is doubly occupied, then alpha 1 is 1, alpha 2 is 3. So here you have the product over alphas. The time dependence is kind of trivial. It's because at large time it's controlled by this term. Then you have phases that depend on single particle energy, and the probability of having a given state is controlled by this thing, e2 minus pi alpha over nu, which does not depend on epsilons, on energy. And here is exact mean field answer. So this is an answer, explicit answer for this Bogolyubov amplitudes UK and VK. So the magnitudes are in terms of this zeta k, which again only depends on the order of the level. So energy levels are arranged in the ascending order. So this just zeta k only depends on this, on the order of the level. And again, you have some phase that depends on epsilon. So this gives, like similar probabilities because of this term, zeta k over 2, e2 minus zeta k over 2, to the classical solution. But here, in the mean field wave function, total particle number obviously is not fixed, but more non-trivially, the phases turn out to be different. So, at large time, the interaction vanishes, and so you have this non-interacting, Hamiltonian, and generally you can write, solution of the non-stationary Schrödinger equation in this form, where E is just the energy of the levels that you occupy. So all non-trivial, history of the evolution is in these coefficients C and K, and which determine the Landau-Wiener transition probabilities to different states at large times. So now, if we take the classical solution and we take the quantum solution in thermodynamic limit, for both of them, these transition probabilities have this form. Some normalization constant times e2 minus pi over nu. Nu is the effective rate with which you change the coupling constant, k minus mu. So now, as an aside, this probability, notice, it's independent of epsilon k. So you can take any epsilon k you want. You can take them all to be very close, or you can take one to be, a billion times larger than the other, than others, and still you'll have this probability. And so this is one of characteristic features of, this kind of time dependent integrability. So in this type of integrability, you don't have integrals of motion. So it's integrability without integrals of motion. So you can ask what are its signatures, and this is one of the signatures. Yes?
Yeah, why is it linear in K, the K minus mu? Why isn't it epsilon general dispersion? Or what?
Why?
Yeah.
So
This is Landau's Wiener formula.
this is not Landau-Wiener formula. This is Landau-Wiener formula is for two-level system. Here I have
generalization for this problem. Or?
But K minus mu is your kinetic energy, right?
no, K minus mu is not the kinetic energy is epsilon K.
Well, that's what I'm after.
Yeah, so
It's just some non-trivial result that I.
it's a
could not
non-trivial
get.
result. Yes, it's a non-trivial result. I can explain, but it's a feature of this, integrable of kinesiological equation.
But is the physics of a multi-level Landau-Wiener generalization? Or?
Yes, the physics is of multi-level integrable Landau-Wiener generalization. And another way of saying this is that at large times the system thermalizes, but not with this Hamiltonian, but with the Hamiltonian where your energies are just linear in K. So it's not a thermal state, but it's an emergent generalized Gibbs state, where of this form, where this beta k are like this.
I see. Okay.
And this is non-trivial because generally, like if I write a general wave function like this, I will have 2 to the n parameters, but I can determine all of them in terms of n, these inverse temperatures. And also it's an emergent generalized Gibbs because at finite times you don't have integrals of motion, and they only emerge at t infinity where the system becomes trivially integrable.
Thank you.
So now we can prove that mean field is exact for local observables in the thermodynamic limit. So, a most general operator with non-zero expectation value, I can write, as product, a sum of products actually. But it's enough to consider this kind of product of these operators OK, which are either pair creation, annihilation, or occupancy operators. So we say that this O is local if the number of operators little n that it involves is much smaller than capital N, so that when n over n goes to 0 in the n to infinity level. So in that case, you can show rigorously that the expectation value of this O in the exact mean field wave function, and you have, in the exact quantum wave function with m pairs, and you have to take m plus l pairs here, because this all can in principle change the number of pairs, is equal to its mean field expectation value, which is in n to infinity limit only, which is a product of this individual expectation values, which we know exactly, and explicitly I showed you formulas for this UT and VT in previous slides, and correction to mean field are of order n over n. So for local operators, that is a product of only a finite number of fermionic creation and relation operators, mean field is exact. But it breaks down for global measures, for things that involve, like a large number of, levels. Like one, obvious example is entanglement. So the mean field wave function is unentangled, but the actual, wave function of the system is entangled, and this entanglement actually grows, in time and saturates at the value of order log n. So this, plot is for n to infinity, and then it saturates at order log n. A more non-trivial example is Loschmidt echo, return amplitude. So now you can do a classical mean field analysis, like doing classical mean field dynamics for this Loschmidt echo, and you will find numerous singularities as dynamical quantum phase transitions in the Z. Just singularities of the Z for quench dynamics of S-wave superconductors and none for P-wave. But if you do a more accurate quantum analysis, you actually find that there are no singularities for S-wave and periodic singularities for the topological P-wave for the evolution when you, start from a quantum critical point, separating trivial and non-trivial topological phases. So the real quantum answer is completely different from the classical, just even not qualitatively close. Again, because this Loschmidt echo is a global measure. It involves a large number of levels. And a more specific reason in this case why mean field breaks down is that because while it determines the bulk of the time-dependent system wave functions, there are corrections over order 1 over n, while the Loschmidt echo is determined by exponentially small tails of this wave function, which are not accurately captured by mean field. So, this is the last slide, and here is conclusion taken from our paper, as nicely formulated by Jet. So that generally, what this tells us that mean field theories are able to capture the order parameter and other local observables, but the entanglement and many particle structure of the quantum state are out of reach. And therefore, the success of mean field theories, we saw today, it basically relies on the order parameter being a classical object, like local operator. So here are my collaborators on the main part of this project. So Jet Pixley, who is giving a talk later today, my colleague at Rutgers, and two of Jet's students, Aidan started as a student with me, but then continued with Jet, and Angun is now at Los Alamos, but he was Jet's student. Thank you very much. Good question.
Is it possible to understand in simple terms why linear ramp is special? What helps? How it helps?
So for generic time dependence, it's not integrable. There's like a measure 0 of time dependencies for which it's integrable, and 1 over t is one of them. The coupling you change is 1 over nu t, so it's like 1 over t. The coupling is not linear. So why? So it's like asking why this is integrable and this is not integrable. And I don't know the answer to that. So from the structure of Newton's homological equations, it comes naturally because these go down magnets are linear in this B. But, but, you know, like physically,
So the reason I ask, let me just say one sentence. The reason I ask is that there are these old papers we wrote on how fermions are excited by driving them by some kind of perturbation, how you minimize noise by optimizing the perturbation, create pulses, minimal noise pulses, all these papers from 15 years, 20 years ago. And so when we did this optimization, we found that linear time dependence is what minimizes noise.
I see.
We don't know why, but that's what we observed and what people then realized experimentally. So is there any evolution of what's going on?
So, linear time dependence in what?
Okay, so our Hamiltonian wasn't your Hamiltonian, but there was something in the Hamiltonian, some term in the Hamiltonian varying that we used to create pulses, and that term, in order to get minimal noise pulses, had to vary linearly. We didn't get, we show that time, any other time dependence gives,
I mean, it sounds like shortcuts to adiabaticity before the name was.
Hmm?
It sounds like when you try to find shortcut to adiabaticity, you try not to excite the system too much. It sounds like you were doing this before this was.
yeah, but then also when you find that linear time dependence as an optimal solution, then it's also measurable and all of that. So, I mean, anyone, you know, any English that besides.
I mean, I have to think about it. No, I don't know. I mean, but let me just say that time dependence in this case is, you know, 1 over t. So it's inversely proportional. The Hamiltonian is inversely proportional to time. So
Yeah.
it might be special in some sense, you know, but I doubt there is a physical reason like that. I mean, but I don't know.
Yeah, I think Tigran was there first.
Yeah, maybe along the same lines. If you look at the time dependence of the Hamiltonian from the point of view of Benjamin Witten, Victor and I, and also Babujan and I, we have the papers showing that if you add a conserved quantity to the Hamiltonian with actually arbitrary time dependent coefficients.
Yeah, that's trivial.
Well, I
Trivial integrable.
come back to this, you will get some time dependence in the formula here. I guess this is like, you can generate very ugly terms, time dependent terms.
You could, I mean, if you take B, some arbitrary function of time, I mean, then you'll get like B dot here, you'll get a more general Hamiltonian. But this is not like adding an integral of motion to the Hamiltonian. This is
Not to this one, so that was Benjamin Witten.
Okay.
Yeah, I mean,
Actually, we have to move because we're gonna run.
Maybe this is like a pretty example of that sort.
I don't think so.
Because if you do just arbitrarily, you will generate many terms in this one.
Leah, quickly.
Yeah, I just wanted to ask that form, not sure your formula for the probability.
Yes.
transition That looks like Landau, Zeno kind of.
Yes,
But with
yes.
linear K, so, you know, you get it from integrability, but you also get it from mean, it agrees with the mean field in the large N limit.
Yes.
So
yes.
is there a way to understand, you have some understanding how that linear K emerges, why is it linear K? Linear K as opposed to a full spectrum in there?
You know, it's a feature of integrability somehow.
No, but it also comes from mean field.
But mean field is also integrable. Like mean field is a classical, but it's a classical integrable dynamics.
I see.
So I don't have a, you know, good explanation why it's, so K is the order of the level.
Yeah.
Yeah, so it's like kind of a, how to say this, like index, unfolds the levels in
Right.
some sense. Well, why it happens? I mean, I don't want to give you a bullshit answer. I don't
Okay,
know.
okay, so, okay, thank you.
Thanks for not giving me bullshit. I'm going to be more aggressive with timekeeping because I'm failing so far. So you good? I'm gonna try to, he's now off. I was disconnecting him. Can you cancel and try again? What? Okay. What? Yes, okay. Allow, yeah, no, sorry. Okay, all right, try to 25 minutes. Yes.
Okay, hello everyone, I'm Quinchen, and now I'm a associate professor at the Institute of Theoretical Physics at the Chinese Academy of Science. So firstly, I would like to thank the organizers for the opportunity to share with you about our recent progress. So basically, we have been trying to decode the structure of two electron correlations, particularly in simple metals. So although they are simple metal, but the two electron correlations has a very rich structure, and so far it has been challenging. Okay, so these are my collaborators, Gabi, Christian, Andy, Nikolai, Boris, and Eugene, and a group of talented students. So we all work together to decode this difficult problem. And basically our ultimate goal is to understand how two electrons interact at and below the Fermi scale. Okay, so mathematically it's characterized by the vortex function, the 4-point vortex function, which is about the how two electrons scatters with each other. And in the past decades, we have witnessed tremendous success to understand the one electron property in real materials. So basically, they are the electronic structure theories like density functional theory, HW approximations, and etc. And however, our knowledge about how two electrons interact with each other has been limited. And I would say this will be the next big question for ab initio methods for material science. And part of the reason why this is difficult, okay, so there are basically two reasons. One is that this structure, this object has a very rich structure. It has a different type of singularities in different limits. And secondly, we still do not have a good numerical technique to compute this quantity, even for the simplest many electron problem, basically the electron gas problem. And it has so basically it's associated with a couple of fundamental problems in ab initio methods of material science. So one is basically the Coulomb pseudopotential problem in the algebra equation. So we know that the superconductivity in simple metals are described by electron phonon BCS theory. However, many of these simple metals like alkali metal, alkali earth metal, and some of the post-transition metals develop superconductivity at a quite low temperature. So many metals like aluminum, lithium, they develop at or below the 1 Kelvin range. So they develop TC at a pretty low temperature, not because electron phonon coupling are particularly weak. Actually, it's because electron phonon coupling is balanced by the Coulomb repulsion between the group pairs. So, and because cancellation, significant cancellation between this attraction and the repulsion, so the net attraction is pretty small. So, now, thanks to the electronic structure theory people developed in past decades, we have pretty good method to calculate the electron phonon attraction lambda. So with this, basically with this chain method. However, up to date, we still do not have a good technique to compute the Coulomb pair repulsions. So this is what Victor mentioned, the magic number, mu star. So and then for this kind of simple metals with low TC, it turns out the existing techniques will lead to orders of magnitude errors. So for aluminum, it will be 100% error, and for lithium, it will be 3 orders magnitude of error. Okay.
That's a good question here. So, well, if you're interested specifically in superconductivity, why don't you just write phonons plus Coulomb and solve honestly the algebra equation? Why do you have to invent this mu star business?
Yes. So basically, there is the reason for that. So in real material calculation, you cannot. It's up to date. Like it's still very challenging to solve the whole beta split equation with all frame space and momentum included. Okay.
There is no smooth
But
parameter.
It's a very challenging. No, yeah, it's supposed to be that, to do that. Yes, hopefully after we have a quantum computer, maybe we can do it, but with classical computers nowadays, it's impossible. And secondly, I will show you later, so basically, at least like what people hopes for is basically you do not need to solve the beta split equation. If you know this mu star, you can solve a downfolded equation with a frame seed, one frame seed only variable.
But I'm sorry, the problem is just solving the integral equation or what? Like, you can solve it, right? Like,
Yeah,
one
yeah,
plus
yeah,
plus
yeah.
too long
Yeah,
and try to
yeah,
solve
yeah.
effectively.
But then
on the
the
left.
challenge is how to solve it, like in
Like,
set
make
up
it
of real
serious, come
materials.
We need to solve serious of that.
Yeah, I will come to this. Yes, yes, I will come to this part. So, yeah, maybe you can see, you will see this, it's a low temperature superconductor, right? It's nowadays like the trend, the fashion is a high TC problems. So they are pretty low temperature, but actually these are the superconductors with the real applications. So for example, people use a transition edge sensor, like to detect the gravity, dark matter. And these materials utilize a superconductor with TC at 100 millikelvin. So if you use a current existing technique to predict TC for those materials, you can easily result it with order of magnitude error. And on the other hand, like the aluminum will be the basically is the material people used for superconducting qubits, and then the error will be 100%. So for those kind of materials, it's unfortunate we cannot predict the most basic property like TC. Okay, and then there are second challenge caused by the two electron correlation. So basically, we know in real materials, the electron has a two phase. Some electron is like itinerant; they behave like an inhomogeneous electron gas, and some electrons are basically confined in a core state or like a semi-core state, and they describe by different models. So if we want to derive the effect model for semi-core electrons, we have to learn how to integrate out the itinerant electrons. And to integrate out these itinerant electrons, we have to understand the how 2 electrons, 3 electrons, 4 electrons scatter with each other in the inhomogeneous electron gas problem. So basically, this will be what people calling downfolding problem. And to develop the control the downfolding technique, we have to know all those correlation functions. And so far, the most successful technique to compute the to solve the electron gas problem will be the variational and the diffusion quantum Monte Carlo technique. So, however, this method have a difficulty to solve to compute 2 electron correlations. So basically, to compute the 2 electron correlation functions, you have to create a hole and put a particle. And this has to be an eigenstate. So it's not just it doesn't work if you just create a hole and a particle. You have to allow it to evolve into a state of quasi-particles. And it turns out it's very difficult to construct the accurate wave function on that for this kind of state. So far, there are no reliable calculations based on these techniques in 3D and 2D. Okay, so a couple years ago, Christian and I developed a technique to solve electron gas based on a diagrammatic technique. So the overall idea is to predictively renormalize the Coulomb interaction with a power series of Yukawa interaction. So this one over Q square behavior expanded as a power series of the Yukawa interaction. And then firstly, it cures about the IR divergence in the problem. Secondly, by tuning this lambda, we can optimize the convergence property of the power series. So with the optimized lambda, the power series quickly converges with the orders. And thanks to the diagrammatic Monte Carlo techniques developed by Nikolai Prokofiev and Boris Sovisnov, we can compute the power series up to order 6. And combined with optimized choice of lambda, we can converge with a high accuracy. So this is a comparison with the correlation function measured, calculated with the quantum two or three order of magnitude more accuracy than the existing one. And then more importantly, it gives us a process access to the correlation functions, which are very difficult to compute with quantum Monte Carlo. And then we have been developed these techniques for many years, and we developed many tools. And it turns out what we developed has a one-to-one correspondence to the tech stack people develop for modeling the big neural networks. So for example, to treat the Feynman diagrams, actually we translate it into a gigantic computational graph, and then we utilize the compression algorithm people developed in the machine learning community to compress it to a small one, so we can compute it extremely fast. And then to implement the renormalization, which is a very important technique for us to introduce counter terms. We utilize a Taylor mode automatic differentiation algorithm people developed in machine learning technique community. And by combining those techniques, we can boost the efficiency of computing high order Feynman diagrams 1 million times. And then in the end, we needed to use advanced Monte Carlo technique to compute the integrals. And then nowadays, like with the help of machine learning packages, framework people developed, we can basically do it on the GPU very efficiently. And we can do important sampling with more advanced ansatz based on normalizing flow neural network. Okay, so then I will talk about the first application. So basically trying to quantify the magic number mu star in simple metal. So to be on the safe side, we start from the scratch. So we start with the electron ion problem, then integrate out the electrons, obtain a model for the phonon, and then we try to integrate out the fast electron above the omega d. So at the beginning, we naively thought this will be easy and we should be able to derive the algebra equation from first principle. However, we find that this is not that trivial. So it turns out the Coulomb interaction, although it's we always say it's a screen, but actually it's dynamic screen. That means at a high frequency in the long wavelength limit, it's actually only partially screened with a long wavelength Coulomb interaction. And this guy caused some problem. So in 1980s, Richard and Shan investigated the uniform electron gas problem within the random phase approximation, and they found this term could result in extremely low TC, even without the existence of phonon. Okay, and of course you can see their calculation is biased because they completely dropped the vertex pressure, and then last year, so basically we worked we push their calculation to an extremely high density limit so that the vertex pressure can be dropped, and eventually we find extremely low temperature TC, like down to 10 to the minus 200. So the physics is there. So that means this Coulomb repulsion, dynamic Coulomb repulsion, actually enhance the superconductivity. Okay, so back in 1960s, Tomachev and Anderson and Maury, they basically proposed to approximate this complicated Coulomb repulsion with a constant superpotential. But this analysis just shows maybe this is there more about that. And this is exactly what Ashcraft proposed in 1997. So basically, because of this structure, he proposed you have to keep all the momentum and the frequency details in the problem, and so you have to solve the beta spita equation as it is. So basically, you have to treat the electron phonon and the electron interaction on the equal footing. Okay. Of course, this is very challenging. So we still, if possible, we would like to understand when and why this breaks down. So it takes us a summer basically to understand how this unfolding is possible. So eventually we find if a system has a sufficiently hard plasma mode, so basically if the plasma mode is larger than the Fermi energy, then the faster electrons above the Debye frequency will be decoupled from the low slow electrons, and it's possible to downfold the original beta-theta equation, very complicated one with a frequency and momentum details, downfolded to a simple algebraic equation with one frequency. Okay, so this form is sufficiently simple, then so that you can solve it even for real materials. Okay, and
Sorry,
yes,
what is omega C?
omega C is 10% of EF. So basically, this is a scale below which you have a well-defined quasi-particle with a linearized dispersion. Okay, so it's from the surface where the rotation symmetry is 10% of EF. Okay, so we compare this downfolded electrical equation with the original equation. You can see for typical metals like aluminum, the accuracy is for TC is 0.02%, very accurate. Okay, but it doesn't always work. So it turns out if you compress aluminum with to be 10 times more dense, okay, then the plasma mode becomes soft, and then this small parameters start to break down, and this downfolded electrical equation also start to break down, so that the downfolded electrical equation compared to beta-theta equation could result in a 70% error. Okay, so the lesson we learn is that for all the metals on Earth, it's perfectly okay to use this downfolded electrical equation. However, for exotic metals like the metals on white dwarf, it's a million times more dense than the electron gas on electron. Yes, then the TC, to predict TC, you have to solve the beta-theta equation instead of the downfolded electrical equation. Okay, and then secondly, after we derive it, we find a rigorous definition for the mu star. So basically, to calculate it, you have you need to do it in two steps. You need to calculate the scattering amplitude in the Cooper channel. Then you need to rescale it rescale it to remove the temperature lock. Okay, and and based on this rigorous definition of mu star, we can utilize the diagrammatic Monte Carlo to compute the power series for gamma 4 and compute what is the magic number mu. Okay, so this is basically the power series to compute as a function of temperature and a function of orders. So this is the number for gamma 4. You can see each order develops a singularity, logarithmic singularity at a low temperature. So at the beginning, it looks like confusing. You cannot get meaningful information. Then basically we perform a rescaling by this rescaling relation. Immediately this rescaling will remove a low temperature divergence, and you can see this is order 1, 2, 3, 4, 5, 6, and then it has a will behave. Each order has will behave with zero temperature limit, and they converge at a sufficient high order. So this is the way we extract the view. And it turns out as a function of RS, it increased quickly. And compared to the random phase approximation, like the one Anderson originally used, we find it's enhanced by a couple of factors for the density of sodium and potassium. Okay? And for the case of aluminum, we find that this will shift the mu star from the magic number 0.1, which is a phenomenological value people use a lot in material science. We find that this die should be modified to 0.113. It's like 30% enhancement. It seems to be small. However, it pushes the TC 100% smaller. So now it's matched with the experiment. Okay, so based on this exercise, we find there are a couple of objects you can utilize to extract the TC. So, and this mu star is what is missing in the conventional theory. And we investigate a bunch of simple metals. So it actually fixes most of the problem, like the magnesium. People before never saw it. It becomes superconductor, but with conventional theory, it predicted around TC at 0.01 Kelvin. Now it's pushed to like extremely small. So this theory looks like gives quite reasonable predictions. Okay. Yeah.
So this mu star business. So
yeah,
when I looked into, maybe I'm wrong, but I wanted to trace where does the 0.1 kick comes from.
0.1, yeah.
And I
okay.
found that there's a 1975 paper,
Uh-huh.
Dimes, who's actually an experimentalist, and
Yeah.
Macmillan.
Yeah.
It's like 2-page paper,
Mhm.
and that's where they say 0.1, and everybody cites it since
Ah,
1975.
I see, I see.
So
Uh-huh.
where do you guys, I mean, since 1975, I assume there has been some progress in
Yes.
computers, right?
Yes,
So, like, is it really the best we have right now, the 0.1?
the best is 0.1 to 0.2. So then people pick one for a given material.
No, but for
Which is
example,
the
why
experiment.
0.1 and then no,
It's
no,
a
no.
logical number,
No,
now
it's
on
not.
computer.
No, it's not.
Yeah,
There's
it's
a
a-
paper which
yes,
everybody
yes.
says that 4,000 I just kept.
Yes.
Including
So-
yourself, which has 2 pages.
Yeah.
And this number, but both dimes, so it's an experiment.
Yes,
We're not doing the theory.
yes. So,
So like, and you guys keep citing it all the time. And that's the argument?
No, it's
Like,
a
what's
really phenomenological. So 0.1 to 0.2 is really phenomenological. So basically you list all the simple metals, you'll find it's between 0.1 and 0.2. So 0.1 is this curve, 0.2 is this curve. You can see indeed all simple metals are in this region.
Well,
Okay.
with your permission, can I give a very quick answer? Because as follows. First, you pretend or declare like Anderson model that Coulomb somehow magically gets screened to a short range interaction. And then you use Tolmachov, not with Coulomb, but with short range interaction. And this can produce something like 1.2. But you start with the bullshit, which is the replacement of long range interaction with something short range. So you derive something rigorously from kind of absolutely arbitrary presumption.
And you're okay with that?
No,
No,
That's the whole story.
It's about being not okay.
yes. And you can see, for simple metals, it's okay, but significantly enhanced compared to the Anderson's proposal for this original gas for the mu star. And then secondly, for white dwarf, those like extreme matter, it breaks down. So one-dimensional algebra equation breaks down for white dwarf or black dwarf, those extremely dense electron gas problem. Okay, that's the message. But for simple metals, you can use the downfolded one-dimensional algebra equation. This is perfectly okay. As long as you know this mu from first principle, this is okay. And it's possible, but it's very challenging, but it's possible to derive it. Okay, so then we can go beyond the Hoover channel. We can compute the scattering amplitude for all different angles. And then we can, for example, this provides us a way to compute the Landau parameters very accurately. So it turns out in the electron gas problem, when the correlation increases, the first Landau, the zeroth angular momentum Landau parameter is significantly enhanced. It can be even larger than -1, and the spin one is not that large, but it's still like significant. Okay? And this guy has a important consequence with Coulomb screening. So it turns out that the Coulomb screening, we know it's a screen, but actually it happens in 2 stages. So first, it's the Coulomb long-range Coulomb interaction is regularized by the Thomas Fermi screening length. And then secondly, the momentum dependence will be the Coulomb interaction momentum dependence will be further suppressed by the vortex correction. Here, the vortex correction manifests as the first Landau parameter. So basically, there is a critical density on this side. Coulomb interaction is a screen, but this guy remains on this side. Actually, it become a overscreen. Okay, and then there is a perfect screening point, which is at the density of cesium. So the electron gas actually is stable on both sides, but the ions could be it could be dangerous for ions. So maybe there will be like a structure transition or something at this point. And then the next, we can compute the scattering amplitude of the 2 electrons, and we can use this data to basically test the series of the electron-electron interaction. So actually, it's a tower of different series. So people started with the random phase approximation, and then people improved by adding the vortex correction with just a number. And then, people further argue, in addition to the charge interaction, there are spin-spin interaction. So they are different. It's a power of approximation of electron-electron interaction. So then we can compare all those conducts with our data. Turns out the best one is actually this. It's called the KO interaction, but you just keep the charge interaction, not the spin-spin interaction. I believe there is some reason for that, for not including the spin one. So basically, the argument is that the spin-spin interaction is dynamically generated from the exchange interaction of the dynamic screen Coulomb interaction. So if you further add the spin-spin interaction, it will be double counting the physics. Okay, so this will be the best. And then you can ask what will be the residue in beyond the KO interaction. So we can analyze it. Turns out the most of the contribution comes from these two terms. So it's still S wave. There are no, the P wave is tiny. And then if you combine those insights, actually you can write down an effective action for the electron gas problem. So usually we say electron gas is just has a dynamic screen Coulomb interaction, but because there are still residue, this residue actually is like the Hubbard short range interaction. So that means to understand the Coulomb gas problem, you actually need to add a local Hubbard coupling to your problem. This will extend your phase diagram of uniform electron gas with a new dimension. This dimension basically is if you turn off the Coulomb interaction, this dimension will be the physics of dilute Fermi gas. So if you turn off the local interaction, this excess will be the uniform electron gas. So then this model gives you an interpolation between two physics, basically dilute Fermi gas to the uniform electron gas. And we know in dilute Fermi gas, there are physics of unitary Fermi gas physics, basically the BCS-BEC crossover. So this physics will also develop in the electron liquid with a local interaction. So this will be basically the generic phase diagram for the electron liquid. So to summarize, so the point is the electron liquid can be regarded as a weakly coupled Fermi gas coupled with a plasma gas. Okay, and if we can write down effective action, and this effective action actually is different from what people have tried before, like Puchansky and Shankar, they construct a proposed effective action for the Fermi liquid, but their action first is not local, so the interaction is momentum and angle dependent, so it's very difficult to solve. And secondly, it's not UV complete. It only covers a thin shell near the Fermi surface, so it's very difficult to use their action for first principle calculation of lambda parameters, for example. And then thirdly, it's very difficult to incorporate the Coulomb interaction in their framework. So and now I believe we can overcome all these difficulties. And then with the effective action, we can define renormalization conditions for the lambda parameter and the emergent local interaction, and then we can derive RG flow for it. So you can see the RG flow is quite for this U is quite interesting. So it's actually first enhanced when you approach the Fermi surface, and then suppressed when you reach the Fermi surface. Okay, and the tree level of this series is already very accurate. So actually you can compare the leading order calculation with the exact calculation. For example, this will be the density correlation for different density, and this will be the leading order prediction with the calculation for the electron phonon coupling. So it's very accurate below the Fermi scale. So not just on the Fermi surface. It's actually accurate all the way from 0 to 2K. Okay. So, and in the end, this will be the conclusion of my talk. So basically, we have been working on two things. So first, we would like to develop an effective field theory for material science for electronic structure. And so far, we have been it's still work on progress. And secondly, we have been trying to develop a tech stack based on the AI tech stacks for solving electron field theory, which is very complicated to solve with the conventional quantum field theory techniques. Okay, thank you very much.
Everything is taken care of our lunch, so I'm picking it up. Any questions?
I mean, in this approach, do you compute the adapter function?
Yes, yes.
And so
It's a downfolded one. It's a downfolded one. So,
can you comment, I mean, how accurate it is?
the accuracy is roughly this. So for simple methods, the accuracy is roughly this.
Yeah, but I mean, do you compare like the adapter function with the experiment?
Oh,
What's the whole function?
actually, we can do a more systematic benchmark. So basically, we benchmark it with a beta split equation, with a keep the momentum and all momentum frequency details. We can benchmark it with that, and the accuracy is fantastic as long as you have this small packages.
Mhm. So this adapter functions, they show like, I mean, in all papers, so you would say they're accurate, or you can do it better?
If we use the mu star, like the first principle mu star, this should be accurate. Yes. Mhm. But on the other hand, it breaks down for very dense electron gas. This, I think this is something that people did appreciate. Hopefully we can investigate more carefully, like what will be the TC for white dwarf? Like sometimes, as if you wait for million years, they go down, become black dwarf. Eventually, maybe they become superconductor.
Okay, I think we overused our time. Thank you. Boris.
On Zoom. Just bring it in, right? Complete. Okay, we are in business, so thank you very much, the organizers, for having this nice event and for having me here. So, I will tell you a story about Borromean counterfluids. So, explanation of those two words. Counterfluids are superfluids of very special type when you have more than one component, to at least, and components cannot do anything separately. They are either behave like insulators or like normal fluids, but they can do counterflow, superfluid flow in opposite direction. Borromean stands for the number of components, 3 or more. So the whole business of doing Borromean as opposed to just counter fluids is that 3 or more is very different, qualitatively different from 2. So a motivating experiment, which is not just directly about counterfluids. It's this nice superconductor with very unusual properties, and kind of it's the group of Vadim Grinenko, experimental group by Vadim Grinenko, and many different authors, including Ilaria sitting in the audience, and Igor Babayev, my collaborator on this project. So what's special about this system and why counterfluidity matters? So this is a system with a superconductor with broken direversal symmetry and extremely unusual properties. Some people emphasize various properties like broken direversal symmetry persists at some high temperatures. They find it, people find it exciting, call it vestigious ordering. Meanwhile, for our purposes, the whole business will be that it's not just something vestigial, something which requires partial restoration of symmetry, something which can exist only at high enough temperatures, but something which can exist as the ground state. And even this case, superconductivity is broken direversal symmetry is quite interesting, because if I ask you a very simple question, if you have broken time reversal, which is broken Z2, how many domains can the system support? Your system, your answer will be 2. Yeah. So far so good, and it's the correct answer.
I have a question.
Okay, go ahead.
No, just, you're saying it pertains to broken time reversal, but you're in the field, what is it? What
Say
is
it again.
You're in the magnetic field?
That's a separate question because it's broken time reversal without any magnet.
Experimentally or theoretically?
Experimentally, but it was predicted theoretically about Yegor before the experiment discovered that.
So if you shut off the field,
I will explain the origin of broken time reversal.
but in zero field, you have the same
In
thing.
zero field, that's the point. Zero field, there is nothing to do with magnetic field. Broken time reversal, and it is special broken time, but I just want to emphasize the fact that if you are talking of generic time reversal, it's broken Z2. You break the Z2, you have 2 domains, right? You have 2 domains, you have a domain wall, just one.
Right.
Here you have 3 domain walls. And if there is a symmetry between components, all the 3 will be equivalent. Moreover, if you have kind of a composite domain wall, 1 and 2, in between, there will be a vortex-like structure. So kind of this generic classification in terms of time reversal, vestigial, blah, 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 it's kind of very superficial. I can't take you to the point. So let's forget about the system for a while. We will be back to it hopefully before the lunch. But there is yet another piece of inspiration recently, and I believe that we just said that a link to this preference. So experimentally, people, the group of generate fun, but the key person behind this experiment is Zhengsheng Yuan. So they realized, implemented kind of this state of 2 component counterflow. I must be fair, it's just six sites, so it's not very impressive, but it's very inspiring. Okay, so what's this scenario of superconductor fluidity? So there are actually 2 scenarios, and one of them was proposed by our organizer Anatoly and yours truly back in 2003, and independent, but kind of a very different scenario was proposed by Yegor almost simultaneously, but earlier than us. So let us start with our scenario because it's very visual. It's essentially what is called, what is known in condensed matter as super exchange. And you can think of just spin 1/2 physics, but think of bosons rather than fermions. So we have a lattice, and we have 2 types of bosons. The filling factor is 1, so you can have mod physics, 1 particle per time, but there are different colors, red and blue. And what can they do? We can have red and blue here, then red hops on top of blue, then blue hops back, and this is essentially a super exchange interaction. The spin language is just what stands behind Heisenberg monolith matter interference, but this is the system of bosons. And in terms of bosonic language, those guys can support counterflow. With Anatoly, we were not smart enough to understand that 3 is very different from 2. But this is common. Because whatever I just told you, it works for 3, 4, and whatever. You just need to have some commensurate filling factor, say total filling factor, say 1. Pairwise, guys can invoke, and essentially that's how you suppress the net flow because of modness, but counterflows are allowed.
Can I ask about this?
Oh, yes, sure.
So are there 2 phases here? So
It's
both
just-
phases you are insulating with respect to the total charge, but then there's an insulating and a superfluid counter phases, is that right? In other words,
the only order is the counterflow order. I will be discussing
Right.
in more detail.
but there's also, in this model, there's also a counterflow insulator?
No,
No, so it's always counterflow superfluid.
it's always counterflow superfluid, yeah. This model is very simple. Yeah.
Okay.
No other order. To have what we call Brownian insulator, you actually need at least 3 components with Josephson coupling between them. We will be talking about it. This model is very simple, just counterflow. Essentially, it maps on a single component system if you use spin language. Yeah. So the model itself is very simple. We will be talking more sophisticated models. But another scenario essentially involves proliferation of vortices. So suppose we have a stack of two-dimensional superconductors, academically speaking, two-dimensional superconductors only at zero temperature because a vortex costs a finite energy, as we know. But what's interesting is that if you have a stack of them, say 3, 2 is minimal number, then if you have a vortex in one layer, you're supposed to have a vortex in the second and the third layer. Otherwise, the energy of the vortex is not finite. And Yegor observed the following fact that if you obviously proliferate those guys, they cost you finite energy, you cannot unwind the relative phase difference, meaning that the guys in different layers can do counterflow. This is an order. That's yet another scenario. Finally, and this is sort of relevant to this system, think of just old good superconductor, but suppose that the superconductor consists of more than one component. We know that if you take a just single component superconductor, in the bulk it's an insulator. The term topological insulator would be applied to all good single component superconductor is a surface phenomenon. In the bulk, we know it's Anderson effect, also known as Higgs effect and high energy. In the bulk, there cannot be anything flow. But if you have two or more components, you can have neutral counterflows in the bulk of a superconductor. So
You need something like a Schmidt-Shot,
frankly, I don't know what.
normal and condensate and double component going in.
It's not normal. Those components are super normal.
No, but in
The right
usual
name-
superconductors, there is normal component and normal current,
you
supercurrent
are talking-
canceling each other.
It's like a counterflow. No, it's a different situation. The right name is Babayev. Yegor was the first, to the best of my knowledge, who was decomposing the modes in a two-component superconductor into a charge mode and a neutral mode. It's like you have two superconducting condensates, but you can have a current which is electrically neutral. It's a counterflow. So you have two electric currents, but the net electric current is 0. That's what I'm talking about. Net electric current is 0. Yes. Actually, we have 3 bands. Bands to the zero oxidation bands behave as independent components. To the next approximation, because internal Josephson coupling, their phases get locked. And in this case, they get locked in a very peculiar way. That's kind of the bottom line of the story. But let me just kind of introduce the terminology. So from now on, we can forget about quantum mechanics. We are talking of classical fields. We have a Hamiltonian, which has U1 cross U1 cross U1 and times symmetry. But for whatever reason, the orders, single component orders, are 0, but we have counterflow orders of the following structure. The means in terms of spin order of psi A, psi B conjugated of psi B dagger, if you want to think of the quantum system. Those guys are different from 0, meaning that those guys feature phases, those are relative phases, and the moment you have a phase, you can just wind it. That's actually the supercurrent state, counterflow supercurrent state, topologically protected. And kind of the very term Baromean superconductivity was coined by Yegor and his collaborators when they simulated, and it's an actual simulation by Roman Grotner of 3-component bosonic system. And essentially, they demonstrated that 3-component bosonic system in this regime, which I described in the regime of Mott insulator, supports this interesting state. And kind of they understood that 3 is different from 2, but not say completely, because obviously, if you have 3, you start thinking of the elementary modes. And kind of, a naive way of thinking of elementary modes is that just take any two and do counterflows. So say one flows to the right, two flows to the left. And then comes the question, when one flows to the right, two goes to the left, what does the third component? And my answer would be nothing. But you see, everything is ordered. And if one and two has the minimal twist to pi, you cannot split to pi into pi and pi. So something should happen with respect to the third component, as opposed to just two components. And that's essentially the difference. If you have just two components, it's just one phase which twists. If we have three or more, we need to take care on twists of all the phase. And immediately happens the following. If we have three or more, the elementary modes, when one component flows with respect to the other, or the other flows with respect to the one. So immediately we see that the counting will be different. If we have two, it's just one type of elementary vortices. If we have three or more, the number of elementary vortices or elementary supercurrent states is equal to the number of components, while the number of modes is n minus one, because the total flow is the rest. Kind of non-trivial behavior in terms of the elementary harmonic modes and topological defects. And that's what we want to understand. How come that the number of elementary vortices and the number of phonon nodes is different? And the guiding principle is the compact gauge invariance. So if you want to design a hydrodynamic Hamiltonian, that's what we've done with Yegor recently, or effective action, you just need to make sure that your Hamiltonian effective action features what we call compact gauge invariance. So compact gauge invariance is very simple. When we have gauge invariance, we just take some regular field and add it to the phase, which can be time dependent. In our case, the field cannot be time dependent, but compact as opposed to just gauge invariance, it can have vortices. So this guy can have vortices, meaning that you destroy all the topology in the single component set. And if your Hamiltonian features this property, then this is a symmetry. It's a local symmetry. Neutro's theorem immediately tells them that there will be constraint. And this is precisely the constraint which arrests the net flow. So the net flow is arrested thanks to Neutro's theorem and n minus one components. Just do elementary modes. But this guy does not change the counting of topological defects, as we will see, and actually explains how to properly count them. And back to counting topological defects. Meanwhile, let me give you a simplest example of harmonic hydrodynamic Hamiltonian. It's as simple as that. So ethers are just deviations from density from equilibrium values. Thetas are individual phases. So essentially, the idea is that you treat all the M components democratically, and the compact gauge invariance does the rest. So you treat them democratically. That's what produces exactly n vortices. But since the one mode is excluded by Newton's constraint, everything is fixed. So you write down the equations of motion. That's precisely what you get. You get the equations of motion in the form of continuity equations, but one of them, or if you kind of, or the system of those equations is not independent, there is a constraint that the net current is zero. Everything is there in terms of this business. You can generalize it. So essentially, the point is that you do not need to write anything specific. So if you write down the Hamiltonian, formally speaking, the conditions of compact gauge invariance are as follows. So in terms of the structure of the Hamiltonian, you would have phases, you would have placeholders for the phase gradients. If it's a basic U1 cross U1 cross U1 invariant Hamiltonian, you will not have this term, just this one. But if you introduce just some couplings between components, that you will get this term. But no matter whether it's the guy with the phases or just with the phase gradients, the condition of compact gauge invariant does the job. So essentially, the net flow will be arrested, and the rest correspond to counter groups. Now, how do we count topological defects? How do we introduce numbers which which are topological charges? So a very kind of intuitive way is that we introduce m charges for each component, but obviously it's a redundant description. And because of the compact gauge invariance, the redundancy of the description is all about modular arithmetic. So whatever is written here should be equivalent to the same string of numbers, provided we add or subtract any integer multiple of this guy. So that's how you can actually calculate classify the topological charges. Here are two characteristic examples. If we, for example, take 3 elementary vortices, they will be spatially separated, so there is no question that there are 3 separate vortices. From a distance, they will look like no vortices at all, and that topological charge will be 0. Or if you take, for example, 2 elementary vortices like that, from a distance, they will be equivalent to 1 elementary vortex, excuse me, to a topological charge like that or like that. So essentially, it's a principle of classification of topological charges. Now, if we go to finite temperatures, this is everything. Well, Yegor and his students, Alexander Bolok and Igor Timashuk. So essentially, the simplest Borromean version of the Klein model is the following model. When you have this combination of elements, you can firstly see that the feature compact gauge invariance. You can add a kind of any phase to any component locally to the side, nothing will change. The basic observable is component density matrix, so you can take some reference component, say component number n, do everything in terms of relative phases, and everything will be look like a single component density matrix, but in terms of relative phases. You can actually do high temperature expansion or equivalently just formulate the model. So we know that if you have Zweig-University class, it can be equivalently formulated as a loop of, as a guess of oriented loops. So for the Borromean representation, it exists, and essentially it's kind of very visual. So we do not have individual loops, but we have pairwise loops. So it's like for any pop, if you are talking of quantum system, or for any loop, if you are talking of just a temperature expansion of the Borromean XY model, or just model which formulated as the guess of loops microscopically, it's just one-to-one correspondence. That would be a typical configuration. And the beauty of this configuration is it can be efficiently sampled to the de Rham algorithm. And the statistics of those two ends just produces you the composite density matrix. So that's essentially what we were simulating, just to demonstrate how the theory works. And in 2D, everything is nice. We can do the theory of Brzezinski, Kosterlitz, Thouless type crystallization. It turns out that the renormalization group is exactly the same, despite the fact that we have different types of vortices. And we can compare simulations to some analytics because everything is under analytic control. In particular, for example, we can calculate the behavior of composite density matrix right at the critical point. So that's kind of convenient parameterization. So we introduce this factor in the denominator so that no matter how many components are there will be Nelson cosinus relation corresponding to this guy equals to over pi. We can calculate the single component, the composite density matrix, and we can find this relation. That's right. The Brzezinski-Kosterlitz critical point. There will be a power law behavior, the exponent, which depends on the number of components. You can just compare this analytic prediction with numerics. The agreement is just perfect. So just to demonstrate that the models work. And let us get back to the example. This is a simplest theoretical model of what we call Boromean insulator. So without this term, it's just a three-component bosonic model. But with this term, we have Josephson coupling between components, and we want this Josephson coupling to be frustrated. So if there were just two components, they would have to fix their relative phase at pi. But if there are three components, the best they can do is this picture. That's the best possible way to satisfy the frustration. And this is precisely, Jovan, this is precisely how the time, the time reversal gets broken. Because you see those are phases, but you have two options: red, blue, green, or red, green, blue.
Yeah.
So, and this is important. This is what produces this internal structure, which is sort of topological, because you see the order matters. The order matters, and
How do you get positive J plus J? How do you get positive J0? What's the argument for?
Experimentalists should figure it out. I just put it.
No, I understand. You can put that model down, but typically phases like to align, you know.
They do, but fortunately, in this magic compartment, they do not want to do that.
Okay. So you don't have a story about that?
Well, it's just experimental fact. How to implement it, I don't know. But it's an experimental fact. Precisely that. And this is just the model which can potentially be realized with boson, but actually in terms of simulation, you see, we cannot simulate this model as is because of the same problem. This guy creates the same problem, so maybe it's better to simulate it with diagrammatic multicolor with fermions. But with fermions, we need to make sure it's U1 cross U1 cross U1 rather than SU3. But okay, so essentially back to this system. So you see, well, they understand what's going on. So it's essentially, we can have ordered phase when those guys are like that. They have what is called quartic metal, or equivalent, we can call it Boromean metal, when those guys do have kind of call it topological orientation order, clockwise or anti-clockwise, and ultimately disordered phase. So this guy just corresponds to this phase. But the point of doing this bosonic Hamiltonian is precisely that this phase can be implemented as the ground state. You do not necessarily need finite temperature to create this. With bosons, this type of phase can be created as the ground state. So that's why this Hamiltonian is interesting and would be good to see implemented with autocode records.
So can you explain the left, the BTRS state is clear. How do you go to the quartic loop fluid, quartic metal? In terms of those pictures, you had that picture.
Oh, in terms of this picture, oh.
No, this one, yeah.
Yeah, very simple, because ordered means that all the arrows, say
Yeah,
all the
right,
red
yeah.
arrows look in one direction.
Okay.
Here those guys look in different directions, but the order is the order. Red, black, blue is there, red, black.
But
blue.
their chirality is the same, right?
Yes.
That in that picture, all four are the same, the same,
So you see, you have two options, red, black, blue, but you also have red, blue, black, and you have here just one option. That's broken time reversal.
so the quartic metal breaks time reversal, does it? Or not?
Of course,
Breaks time
that's
reversal.
that's the whole business about this phase.
And
Broken
then
time.
the higher up, it's just fully disordered.
Yes, it's just, yes, that's the point. But the point is that it breaks time reversal, but in a very peculiar way, which you will see on the next slide. Because you see now what is the origin of three domain modes rather than one. Because when you go from here to here, and kind of think classically about it, you're supposed to somehow do something. You can do this, but there are three other options. And if you have a symmetry between three components, all the three are equally good. Furthermore, if you combine two different dimensions, what you see in between is pretty much the vortex corresponding to the counterflow vortices which we discussed. So you see, if Josephson coupling between components is weak enough, you have mesoscopic physics, very reminiscent of counterflow vortices. So the weak Josephson coupling just tells you that, okay, there will be vortices, but there will also domain walls. That's the explanation. So those are my conclusions. So Borel counter fluids, which are n-1 Following modes, and elementary vortices for counter flow states. So we have long way description of the Lorentz states in terms of the Hamiltonian, and then Hamiltonian zero temperature or effective action and final temperature. And the bulk of the multiband superconductor behaves as a Brownian insulator. Thank you very much.
Yes, any questions?
I have a curiosity. So in the superconducting case, one of the ways to develop this case was to observe this spontaneous magnetic field that can emerge when you have these domain walls and reveal the structure of the free structure. What is the analog for this?
What is
The analog for this discrete case? Is there, some emerging structure that you can detect experimentally when there are?
You see, kind of when you have a superconductor. So the bottom line is the counterflow vortex. Whatever is your experimental technique to observe that there is a counterflow vortex. But in a superconductor, in addition to this fact that it's a counterflow, there will be some magnetic flux. Which will not be just one quantum, but it will be kind of a fraction of the magnetic flux. So if you will, fractional magnetic flux is a way which allows kind of experimentals to see that they are doing this structure. But experimentals build ultra-cold atoms are supposed to see something in the core. Of course, it's not the magnetic, but you want to see something, some deficiency of some components and stuff. But kind of addressing the core, you can get an experimental kind of evidence of what's going on. In the case of a superconductor, it's very easy. You just observe the magnetic flux. Oh, it's not equal to the magnetic flux quantum. Wow.
Everybody is hungry. Okay, if no more questions, let's thank Boris again.
This microphone. Okay, let's go.
Okay.
So,
Okay, so maybe mine should be me.
Unless you like, no, just
Okay.
Okay. Yeah, the other perspective is just a 2D square lattice, bosons are hopping on a lattice, but you erased all the horizontal bonds except on this backbone. One of the perspectives I'm gonna take is that, you know, you have a system and it's coupled to a bath, but the bath is kind of funny. It's has this kind of larger liquid flavor. So now this screwed up my. It was working. Sorry, I'd like to be able to change slides. Yeah. Okay, so yeah, so some of the motivation and other systems that this is related to, so that's at least that's one perspective, is that systems where you have a surface coupled to a bulk. So, you know, maybe the interesting thing is the surface phenomena, like for example, surface of some CFT that was recently studied by Max Mitlitsky, trying to understand critical phenomena in the surface, critical boundary phenomena, or an SPT where you have all the physics gapless modes are confined to a surface, or some of the systems that I studied for quite some time where you have Goldstone modes in the presence of disorder, but the disorder is localized on the boundary, as happens quite regularly and standardly for liquid crystal systems where all your quench disorders on the boundary. And so then the bulk is fairly uninteresting, except it's gapless. And so then one can reduce a problem to a surface problem, but then there's a non-trivial effect of gapless modes, bulk modes onto the surface. The other motivation that's quite relevant to what I'm going to talk about is actually thinking about a dislocation in the crystal. And this dislocation, you can think of it as its core is just a amorphous, you know, so dislocation of helium-4, for example, and this dislocation is just amorphous liquid of helium atoms. And so, but it's coupled to the surrounding crystal, three-dimensional crystal. And so the way I actually got into this work with my colleagues at UMass is thinking about the sort of quantum nature of bosons sitting in this core of a dislocation. And I'll talk a little bit more about the other related problem is the Kane-Fisher problem that's quite familiar to many people. And of course, you know, the general genre of this, what I'm going to talk about, has this Caldera-Leggett flavor where you have a system coupled to some harmonic oscillators. And finally, a sort of a Polaron physics. Again, there's some system and then there's some gapless modes that are coupled to it. So let me spend a little bit of time telling you about this interesting system, which is not the main focus of my talk, but we spent some time working on this. So the motivation was to understand supersolids or some phenomena in supersolids where you actually, the idea is quite old. And the idea is that some of the phenomena of supersolidity is due to a network of dislocations that can carry superflow through the solid. So it's not really an intrinsic phenomenon, it's really due to a network of dislocations that are inevitably there in any crystal. And so then the superflow that one may observe is really a consequence of a flow through a core dislocation. And so then the natural question arose is, what is the nature of a quantum fluid that's on this core of dislocations? So naively, you would say, well, this is just a one-dimensional bosons. So it's a Lagrange liquid of bosons, and there's nothing more to say about it for a fixed configuration. But the arguments that we made in these papers is that in fact it's a funny kind of a one-dimensional quantum fluid, and it's not a Lagrange liquid. Or you can say it's a Lagrange liquid with infinite compressibility. And the idea is that just has to do with the coupling between the, bosonic degrees of freedom on this dislocation core and the motion of that dislocation, the climb motion of the dislocation. So you can sort of see it here. When the dislocation climbs, this is a side perspective, when it climbs along this blue direction, it actually changes the density of atoms along the dislocation. So the way you should think of it is there's some superfluid density or kinetic energy of the bosons on the dislocation, that's the defined EX squared. But then it's coupled, this density fluctuations are coupled to the displacement H of the dislocation. So when you move when a core dislocation moves in the climb direction, then you're increasing or decreasing the number of atoms on the dislocation. And as a result, so there's this coupling between the displacement and the dislocation density. But the displacement, if you ignore Peierls potentials, is a Goldstone mode. So then that goes as dH dx. There's no H squared term if you ignore the pinning by the Peierls potential. And so then there's this, if you at low energies, then delta H is coupled, just gets locked to delta N. And so you can see here, if there was no H, if you lock the H, then this would be the standard XY model, a standard model of a one-dimensional superfluid, lunge liquid. But once you have this additional degree of freedom H, you can change the density by climbing in this direction. And so as a result, this guy at low energies looks like something like this. So there's no familiar N squared term, there's just dN dx squared term. And so this model we studied, we call the transverse quantum fluid, because it's a quantum fluid coupled to transverse degrees of freedom of the three-dimensional crystal. And it has interesting behavior. For example, phi and N, although they're canonically conjugate, they now appear on equal footing. So there's a duality between N and phi. So there's a long, and what you discover is, not surprisingly, phi is much stiffer than it is in the lunge liquid.
Is N phi dot?
Exactly. Well, no, so N is canonically adjacent to phi, so N is phi dot. But it has much softer, so the way you should think of it is, instead of N squared, you have the N squared coefficient vanishes. That's the infinite compressibility. Because it's infinitely compressible, because if you try to compress it in one dimension, it can shift up and down. Dislocation could just climb and absorb those bosons arbitrarily. And because H, it costs no energy to shift, because of that, it's incompressible. It's infinitely compressible, infinite compressibility. So then N is much softer. Because N is much softer, phi can be more ordered than you were used to for a lunge liquid. So in 1+1 dimension, it actually exhibits long-range superfluid order.
Okay. N can appear without gradient. Sorry, H can appear without gradient.
It cannot appear without, well, it can, you're right. So there's a principle of Peierls potential. It's a periodic potential, which I included the slide, but I hid it just for the interest of time. There's a potential cosine 2 pi H, or cosine H over A times 2 pi. And so in principle, dislocation is thin. So at long enough scales, this will cross over to a lunge liquid. But but if that potential is sufficiently weak, as it often is, then this will be the model at a large range of scales. Okay.
And the scale at which it crosses over to the integer is linked to kappa or to the trade?
It's linked to the strength of the Peierls potential. And also, a parameter here. Yeah, and kappa. Yeah. So this is the model. So we studied this model extensively. Maybe I'm not gonna, in the interest of time, I'll just highlight some things. That's quadratic dispersion rather than linear dispersion. It's a dual to a Lifshitz symmetric-like model. If you dualize this and go to a theta variable, we studied its IV characteristics as 1D off diagonal range order. Instantons are confined as a square root of tau or as x rather than logarithmically, the way lunge liquid is. We computed IV characteristics here, and this is a attempt to try to compare to some experiments on supersolids. et cetera, et cetera. So there's some interesting phenomena for this toy model. It's a quadratic model. There's nothing, it's interesting, somewhat interesting, but it's easy to analyze. But we studied it quite thoroughly. But that made us think about other models that are maybe in this kind of a genre, where you have some low dimensional object, one-dimensional object coupled to the environment. But the environment is not just some Caldera-legged isolators. They are morally, but maybe there could be a phase transition in the bath itself. So the transverse degrees of freedom or the bath degrees of freedom are correlated as well. And that's what I'm going to talk about. So that's what brings me to this so-called incoherent superfluid, which we studied with our friends here. So that's the lattice, that's the cone lattice. Again, one-dimensional backbone. That's the, described by some Lagrangian LB for backbone. In the original paper called it L system. And then there's L perp are these whiskers or the teeth of the cone that are coming off. Equivalently, I like to think of it as, if you want to think about this for simulation purposes, this is some periodic boundary condition of the backbone, and you just have some whiskers coming off. This is quite natural because, as they come off radially, then you naturally, as a function of R, you're hopping, these points get further and further apart, so the hopping gets weaker and weaker. And so even if you had the hopping, it would vanish as you go out radially. So that's a model we considered. So you can think of a phase phi and a script phi. Phase phi lives on the backbone here, and the script phi lives on these whiskers. These are transverse chains. So there are two Longe-liquid-like degrees of freedom. And then you couple them together. And so one thing that we did is we integrated out, it's a quadratic theory, so you can exactly integrate out the whiskers. And lo and behold, what you get is a model that looks like this. To integrate bulk degrees of freedom, you have an effective backbone model that has this z equals to dynamical exponent 2 diffusive in imaginary time like dynamics. So that's nothing surprising. So we call this incoherent transverse quantum fluid. Here, I'll just call it incoherent superfluid. And it has very similar properties that dislocation that I mentioned. It has a long-range superfluid order. And so we studied this extensively. One point about this is, one point of connection that I didn't mention is that it actually, you can think of this thing as, if you think of one of these guys, it's really, you can think of it as just a Kane-Fisher dot. This is the impurity, and this is the Longe-liquid. And so this is just the generalization of Kane-Fisher to a chain. I now just made a chain of Kane-Fisher dots. Okay, so, so if it was Kane-Fisher, it would be like this, and now I allow hopping. Okay, so it's very simple. So we studied this extensively. It has many, properties quite similar to the dislocations, long-range order, incoherent, on the incoherent superfluid on the backbone, but it's quasi-long-range order still on these whiskers. It has confined instantons and divergent compressibility with a z equals to dynamical exponent. So it's kind of a, it's a Gaussian model, so in a continuum and zero temperature for an infant system, it's trivial. Yeah.
You kept saying instantons, and I just realized that I don't know, what are the vacua here of the instantons? You mean face?
Well, in space-time, so I should call it, that's why I'm calling them instantons. I just mean in space, it's a vortex configuration in space-time. If you think of this as 1 + 1, two-dimensional system, just think of vortex configurations of phi.
For this,
and that's what controls the phase slips into the.
So for this anisotropic action, the vortices are deformed, right?
Well, you have to find the vortex configuration. That's why it scales as square root of tau. The energy grows as square root of tau.
Is phi compact?
Phi is compact, of course. It's a superfluid phase. So so you just need to generalize what you normally do, this arctangent solution for ordinary XY model here, because it's an isotropic, you have to find you have to solve an appropriate Euler-Lagrange equation in space in 1 + 1 dimensional space-time that has this non-trivial curl in space-time, curl of a gradient in space-time. But you can do it, and then you get these results.
Do you get this exponential factors of xi minus xt with expected action?
Say it again?
there should be some, once you integrate all the parts, it should know about the positions of its, points, right, the Kingfisher points.
Well, it does, that's the KX. In momentum space, that's the hopping. In the X direction, yeah, so you know, you have a Kingfisher dot here, but it has, it's Josephson coupled to the adjacent one.
You can only hop with Y.
Huh?
Like in space, I'm trying to ask if you can only hop with Y equal to 0.
Yeah, you can only hop at Y equals
There's
zero.
some constraint that it's just not obvious how to see it in your interaction. I think that's your question.
Should be Xi minus Xj tables, right?
Well, there's no Y space anymore. I've integrated it out, that's how. But, you know, you can reconstruct it because I know what the original fields are, so I can calculate, you know, correlation function between this point and that point. You know,
But in the
quite-
Kingfisher case, the points were cosines, right, so you are not using cosines.
I'm not using cosine,
Okay.
so in this work, that's really kind of a, you know, what the new work is. This is the old work here where we just try to understand the phase. We're deep in the phase, it's a superfluid phase, we study its properties. And, you know, part of the message is, it's extremely well described by this model, where, you know, in this model, at finite temperature and at finite system size, you can, you know, do pretty non-trivial, I mean, conceptually trivial calculation, because it's still a Gaussian model, but, you know, technically it's slightly non-trivial. You can do all those calculations, you can predict the, you know, calculate the Green's function, and it has this one parameter scaling of tau over x squared, and you can go and compare it to Monte Carlo, that my colleagues have done, and you have, you know, you can determine, there's just two parameters. Diffusion coefficient, which is the ratio of kappa over ns, and superfluid density. And well, I call it kappa over s, we just see, it's k over ns.
Actually, there is the third parameter, condensate density, but this one is unused.
Sure, that's, yeah, so that's in here. So anyway, so you get this perfect agreement with these two fitting parameters, and also temperature and the size of the system, you can perfectly fit this form. And then once you fit that form, you can then go and change the system size, temperature, and it's like pretty still impressive agreement, parameter-free agreement with Monte Carlo. And in Monte Carlo, you really have a, you know, you can, of course, jump in at any time you want, but it's just a popping of bosons on that funny lattice. Yeah. Okay, so that's, you know, that's pretty impressive. On the other hand, it's a Gaussian model, but still, in, you know, in one case it's a field theory, in the other case it's really just a hopping model.
The microscopic model is not Gaussian, it's full.
No, I understand, that's why I said it's, and you know, here's the density matrix, so it's kind of amazing. You can now, in a parameter-free fits, you're now getting this amazing agreement with different temperatures, different system sizes. So another way to think of it, in the microscopic model, you can think of it as, there are two types of bosons. There are bosons that live in the backbone, there are bosons that hop along the whiskers, and then they're just hybridized by some coupling C. So and then these are hardcore bosons.
Sir, ask you a question. If I look at the snapshot of the original field H, it looks like a disorder potential basically for every realization, right? Can I think about it in this language? And there are some rare events.
I don't really want to think of it that way, because I want to think of it as a quantum variable.
But if you're at finite temperature, then it's classical fluctuation. So you have just basically a bunch of snapshots.
Okay, let me think of it as a zero temperature. I mean, the question you're asking is pretty
It's
interesting.
microscopically low, it's important that temperature is finite, but.
It's very small, yeah, it's a low temperature. The question you're asking is actually a general, very interesting question that you can also ask for this system. I don't want to, but you know, it's subtle, and I want to.
So there's no localization business
No.
here, and there's no rare events where you just cut things into pieces or something.
No, not here. Temperature is low enough, so you should think of it as quantum plus a little bit of temperature. Okay, so the thing that was left undone, of course, is this is just a piece of the system. This is just the one phase. This is the superfluid phase when everything's well ordered. You know, your low temperatures, hopping is very large, interaction is very small, or maybe you're incommensurate with the lattice. So, you know, you're just describing an interesting superfluid phase. But, you know, it's very natural to ask what other phases are around in this model. Okay, so then what you do is you write down a Hubbard model, but Hubbard model on that lattice, So notice it has, usual chemical potential, repulsion, on-site repulsion, which can be generalized to next nearest neighbor and higher repulsion. And then you have, these are the funny objects. You have J hopping along the backbone at y equals to 0. And then you have the hopping along the whiskers at fixed x, but along y. So that's the only funny thing about it. Otherwise, it just looks like a Hubbard model, Bose-Hubbard model that we know all about. So I just wanted to understand, it's natural to ask, and it's, it's not very complicated, but it's natural to ask, what are the phases of this model? Nearby phases.
And Leo, the teeth of the cones are infinite.
Well, it's up to you, but that just say they're infinite for field theory, and then you can cut it off with L and try to understand how.
The transport on the structure is going to be very interesting.
That's what that's actually going to be the final message of my.
Classical diffusion is non-Brownian.
That's
along the X direction.
I think so, yes.
We proved that many years ago.
Okay, well, we should talk, because
So,
I have not studied transport, but maybe you already have, so then there's.
Well, classically.
Huh?
We looked at that classically.
Okay.
In quantum,
R is everywhere or on the back?
R is everywhere.
Everywhere, okay.
Yeah, so R is everywhere because they're repelled everywhere. So you can get monotonic even on the whiskers, and that's the point. So it's not just some featureless bath, which is just harmonic oscillators and boring harmonic oscillators. The bath can undergo phase transition. That's going to be the message.
Any intuition for how the whiskers can couple to each other by integrating out the backbone?
That's a good question. No, I didn't do that. Yeah, that's you could ask that. I mean, what it looks like is it looks like a boundary critical system. So it's coupled for the boundary.
But you can ask the opposite question by integrating out the teeth.
Well, that's what we did before.
Yeah.
That's what we did before, and you get this model, right? You get this model. You need to have a teeth.
I see, so it's basically, you can do a folding trick on the backbone and then let the liquids on top, with some comments on the.
That's right, that's right. But the point is, it doesn't have to be a large liquid in a backbone.
Oh, okay.
That's just one phase.
But you see, sorry to interrupt again, but you have these scaling ansatz just before. X squared of tau, yes, tau over X squared. Yes, these guys.
Yeah.
So does that apply when the teeth in the y direction are
Infinite.
That's interesting because.
I mean, there'll be additional scaling with L.
Because diffusion will not be like this. If the teeth are classical diffusion around X, will not be of the form X squared of tau. It's gonna be, I can retreat, but.
Okay, so maybe.
Well, is it a linear diffusion or non-linear?
What diffusion are you talking about? Because it's a superfluid.
Right, because
This
it's
is
still
a
linear
diffusion
here.
panel, d tau of X.
Just like diffusion and matching time.
But this is a linear system, so this is
there will be a
rigorous.
diffusive model.
is Gaussian analysis.
Yeah,
This is a rigorous
But
statement.
it's a relation statement, it's a linear problem. It's a rigorous.
No.
But your problem is not.
What I'm saying is that if you take the classical Brownian Walker on a comb, and you look at the diffusion along X and the teeth have infinite width in the Y direction, the diffusion along X is not Brownian. It's not X squared root of T, it's subdiffusive. So this scaling problem.
Okay, let's discuss this after,
Yeah.
okay? 'Cause
Yeah,
that's-
sorry.
That's very interesting, so, okay, so what do? Well, you do the standard things, you go to coherent states. You introduce Hubbard-Lagrange field to decouple the hopping. What's cute here is that you can decouple the hopping along the backbone and along the teeth with two different Hubbard-Lagrange fields. So it looks like two superfluids, little psi and big psi. Then you integrate out the bosons because they're not quadratic, so that's the standard thing. And you derive some field theory as a function of capital psi and little psi. And not surprisingly, they're coupled together by some kernel C of tau minus tau prime. And then there's interactions, nonlinearities. So now you can go to low energies and long wavelength. And lo and behold, you get basically two coupled superfluids. Superfluids that's living in the backbone, here it is. It has some Berry phase-like terms, second derivative terms, standard lambda form. And then there's the same thing on the teeth. Sorry, on the backbone, these are the teeth. The backbone, not surprisingly, as it should be, is only sitting at y equals 0. So that's like, it looks like a boundary for this guy. And, you know, the strange thing or an unusual thing is there's no X derivative in this guy. Which I may have to restore if I'm really want to understand some of the phases. So, and then, you know, the crucial parameter as always, as in Ginsburg-Landau theory, this is sort of quantum, but is just these quadratic coefficients, and you can derive them, and they have a form 1 over j minus 1 over u. And so that, you know, when j is order u times the coordination number, that's the phase transition. So that's a critical parameter, and there's an expression for chi. You can derive it. You can look it up in Subir's book. Okay, so what's the phase diagram? Well, it's pretty simple. There are two order parameters. So naively, you would say there's a phase, mod insulating phase, where both of them. So this is mean field. Both of them are 0. That's the mod insulator. One backbone is non-zero, but the teeth are 0. That's the superfluid backbone. Then there's the counterpart, superfluid perpendicular one, and then there's the one where they're both non-zero. That's the I superfluid. However, of course, that's, you know, wrong. You know, this phase and this phase are the same phase because they're hybridized. So it's really a boson from the tooth can hop over to the backbone. So it's really the same field. They have a Josephson coupling, non-frustrated Josephson coupling. So there's no really a phase boundary between these. These are the same phase. Okay, so there's nothing strange here, just kind of organizing principle. But then, you know, okay, so that's what would happen in high dimensions where it's all mean field and you plus mean field. But now, you know, we want to go a little further. So you want to ask what happens if you're in 2 + 1 dimension where there's strong quantum fluctuations and each of these, both the backbone and the teeth, if they were decoupled, they would be Lunge liquids. So this is kind of a schematic phase diagram, and you know what one would really want is some Monte Carlo to study this phase diagram. So how do you think of it? Well, now think of, you know, now you think of a lattice model where, and I'm going to look at the commensurate case. So there's commensuration between the bosons on the chains and on the backbone, and it doesn't have to be the same because the system is not translation invariant in the y direction. So, but still, I can consider phase where I tune the chemical potential or filling such that, you know, this filling is commensurate and this filling is commensurate. So you'll have a mod insulating phase everywhere. So there's short range order both on the teeth and on the backbone. And then you can start increasing the hopping, for example, in this direction, increasing J. And so what will happen is you'll still have short range order on the backbone, on the teeth, but you'll now get a Lunge liquid. And so this will be the standard mod insulated Lunge liquid phase transition because these degrees of freedom on the teeth are gapped. And so then it's just a standard XY transition to Lunge from a mod insulated to Lunge liquid. On the other hand, you can go in this direction where I want to think about the coupling between the adjacent Kane-Fisher dots to be very weak. And so then what can happen is you get Lunge, these guys go from insulating to Lunge liquid, but this cosine for sufficiently large or sufficiently low commensability or sufficiently low filling, you can make this hopping irrelevant. And so then you go from this mod insulating state, fully mod insulating state, to mod insulating along the backbone, but Lunge liquid along the teeth. And then finally, you can transition either from here to here to the what I called, you know, I superfluid, this incoherent superfluid that I started to talk with. On the other hand, if the commensability is high, for example, filling 1 or 2, then this phase diagram or this phase boundary disappears, and really this phase and this phase are the same. So there's no more boundary here. Once you're in here, it's the same as that. And that's what we saw in mean field theory as well. So, you know, I can discuss. I don't know how much time do I have? Okay, so let me just take a couple more minutes. But so, now you can actually in more detail discuss these transitions. So modern Seleucus LL Langer liquid, perpendicular Langer liquid, is controlled by this Lagrangian, the usual Sine-Gordon model, where this guy's relevant or irrelevant, so it's a KT type. And then from here to here, from at high commensability, you go directly to here, and that's it's determined by irrelevance or relevance of this hopping between chains, between these Kane-Fisher dots. Okay, and then this transition is controlled similarly along the backbone by the Sine-Gordon model, where this cosine becomes relevant, commensability parameter becomes relevant or irrelevant. And then there's a possibility of this, because you have quasi long range order, there's a possibility of the capital psi and the backbone psi and the teeth psi being relevant or irrelevant. And the critical value of the Langer parameter is given here. And so if P perp is sufficiently large, then this guy can be made sufficiently large. So then there's a critical value of JC, which is this GC, where below it, on this side, the coupling between, the hybridization between backbone and the teeth is irrelevant. So that means, so what's really happening here is a boundary critical phenomena. You've become already a Langer liquid on the surface, and now your bulk is trying to undergo a phase transition. And then there's two possibilities. One possibility is that the coupling between them is irrelevant, then the bulk ordering is happening independent and not affected by the surface being critical. The other possibility is they're relevant, and so that's what Max Smelitsky called extraordinary Langer liquid. It's just undergoing a mod insulated to Langer liquid transition here. On the other hand, beyond this critical value, it is relevant. So now when this bulk is trying to order, it's ordering in the presence of a gapless Langer, a quasi long range ordered backbone, as illustrated here. And so that's now a non-trivial, now surface or this backbone has non-trivial impact on the critical correlation functions at the critical point into this phase. And Max predicted that for his system, he studied ON models, that there's this log-like extraordinary transition where correlations go as 1 over log to a power. And so
GC the same as JC? It's just a typo?
yeah, no, it's not a typo. This is like some effective Langer parameter, and this is like J in a microscopic model. They're related to each other, but they do the same thing. No, sorry. Sorry. So J is actually a microscopic parameter. It's a hopping along the backbone. G is the Langer parameter. So they're related, but they're not. There's some complicated relation between them that involves on-site interaction as well.
And what is P perp?
Where's T perp?
P perp, like P perpendicular.
It's the filling along the back. The thing is not translationary along Y. So the filling along the backbone doesn't have to be the same as the preferred filling. So P perp is the filling along the
whiskers.
Along the whiskers, exactly. Anyway, let me not, since I'm out of time, okay, there are a few other details about the phase diagram that are interesting. Let me just close with summary. I talked about low dimensional system coupled to a bulk. That's the motivation. Talked about incoherent 1D superfluid that appears in this Kane-Fisher chain with, long range superfluid order along the backbone, but a quasi long range order along these whiskers. And I discussed phases in the phase diagram that is quite rich, in this system. And I also talked about how Monte Carlo are quite good in describing at least the superfluid phase, this incoherent superfluid phase. And it would be interesting to study many other things, but in particular, study this phase diagram, extend this quantum Monte Carlo to study the phase diagram, open questions theoretically that are, echoed in the audience is that looking at transport and entanglement along this chain. And in fact, Stephen White studied a spin model version, spin 1/2 model on this kind of a cone lattice, and has, numerically using DMRG, and found kind of similar phases that are kind of counterparts of these bosonic phases. So with this, I'll close and thank you for your attention.
Very interesting talk. Do you know if there's Anderson localization ever been studied on these kind of lattices?
Well, I would venture no, because,
Like, I mean, Max's stuff is all 5-4 theories, as far as I understand, where he's thinking about bulk boundary criticality, 5-4. I'm just curious.
yeah, no, I would say no, because, even this is first study on this lattice of even the simplest thing, like the modulating, like the superfluid transition or longitudinal transition. So I don't think disorder has been added to it, but, that's another direction.
And is there an intermediate region between upper diagram and the lower one? Let's say upper, you
The
have
insect,
one
you mean?
bicritical point, and
Yeah.
below tetracritical, it's like 2 bicritical points.
Absolutely, yeah. So this is one version, I didn't want to put 10 different, so one possibility is this guy is split.
Splits into
And then there's a
bicritical.
first order transition here. The other possibility is there's a line here and these guys connect to these lines. So there are other topologies that are less generic maybe. But yeah. But this tetracritical point is the one that's kind of naturally comes out from mean field theory.
I think the last question.
I don't know, intuitive picture of why you have the long range order, I mean, like.
Well, you can think of it as like, effective dot, that the Kingfisher dot is really infinite, it has an infinite, compressible. So it's infinitely compressible, it's like its effective coefficient part of n is 0, basically. So then it just has a super, it has no counter term. Well, yeah, so that's another way to think of it. It's being ordered by the bath. The bath is Josephsonly coupled, so it's measuring the cube.
Oh,
It's measuring
okay,
the-
okay, I got you. So you have.
That's another way to
Just like
think
in
of
the
it.
classical model of the long range interacting.
That's right.
Classical.
That's right.
Okay,
That's right.
that's what I wanted to say.
That's another way. I mean, there's like 5 different ways.
Thank you very much.
Yeah, thank you.
Next speaker is Jeff Bixley from Rutgers, and I think we're running 40 minutes late, but I guess it's okay.
Are you on Zoom?
I'm not on anything.
Go to Zoom.
Okay.
No, go through is in your mind.
Where's the caffeine?
No, when we
Not in his body.
I'll give him a drink coffee. We can catch up.
So there's an email from you with the Zoom link?
No, just go to the website. Oh, sorry. Yes. Just go, don't worry about music.
Okay.
It's so much faster.
Well, there's no simple, it's just, yeah, it's just, yeah.
Okay.
Bullseye.
.org.
So Matthew Fisher had this story about back when people were using many body localization, heavy particles.
Yeah.
Which kind of provide the
Yeah.
localization sort of landscape and light particles moving around.
Yeah.
So isn't it like a little bit? So if
Just
you
Yeah,
make
don't,
this-
that's part of the
don't join
motivation.
audio, is that all the like echoes?
Kind of quantum version of quantum biology has that.
Get rid of.
Hot here in the basement, you know.
Collect chicken eggs.
My daughter's sure, but I've always ended up. Actually,
Yeah.
winter they stop laying. Yeah, it's too cold.
No, but
Bring-
maybe it's related to what
Heated the coop.
Stephen White found.
Okay, sure.
Oh, I need to get out of here. You probably can.
Okay. All right.
Is there a stick?
There's a stick. We have.
Okay. Are we good?
Sure.
Oh, well, I already introduced the distinguished
Ah.
Professor Pixley, who's from Rutgers.
Ah, sorry. Thank you. All right, thanks for putting on this nice conference. It's always good to be back. every season. It's just as chaotic as the last round. I made it here on time. I'm happy that I was at the right place. So, all right, here we go. So, yeah, this is a collection of work, and if I don't cover everything, that's okay. I can maybe cut a little bit out if it's a little too long. But let me just start by thanking the. Is there a lag on the Zoom?
There was some people. I'm not sure why.
So the slides are changing on my screen, but they're not changing on my computer.
Can you go out of full? I don't know. Let's see. I'm not doing anything. Okay.
I think that was.
Can you go left, right with your thing? So your slides are changing, but these are not,
Yeah.
right? Well, that's a new one. Oh, it's a Mac problem. This is really stuck. I don't know. Okay. Okay, try changing slides.
That's not even my screen that I'm sharing right now. Let me stop sharing. Yeah,
Wait, you're not sharing your screen?
I was sharing. No, I'm just saying that's not the screen I'm seeing.
Okay. Try to go full screen, I guess.
That's working.
I have no idea.
Great, okay.
Okay.
So yeah, I'm gonna tell you about a collection of work where we're basically taking ideas from disordered magnets and realized how you can basically classify relevant and irrelevant perturbations to entanglement phase transitions where we I naively didn't think such scaling theory could potentially hold in the beginning. And then I'll take advantage of that and do a space-time rotation to find, instead of an ultra slow dynamics, I can find an infinitely fast dynamics where the dynamic exponent actually goes to 0 as opposed to infinity. And so hopefully I can close with that. Okay, so this work was done by my student, Eden Zaballo, in collaboration with Michael and Sarong and David, and then and my postdoc, Justin, and I'll be collaborating with Snir Gazit, and then he had a visiting student in my group, Dahl, who's been carrying this work on as well. And so this actually did appear. I should have updated that. This was an archive link for that paper in case you're interested in the last part. Okay, so I think this is probably the first talk on measurement transitions roughly that I saw. So I'll try to give you an introduction, but I'm going to start by asking a kind of a general question. Okay, so hopefully it's not too confusing, but if it is, I can go back and forth. And then I'll talk about how we have the notion of infinite randomness in quantum circuits, and idea of Griffiths physics and this notion of infinite randomness criticality. As I said, I can then do a space-time rotation of that problem. So Z being infinite now goes to 0. That's still a well-defined model in a quantum circuit. And so we'll talk about rare regions in time as opposed to space. And this has very interesting consequences on teleportation. Okay. So here's the general question I'd like to start from. So I can't really see my screen. So the general question I want to ask is, in entanglement transitions, are there universal guiding principles to the notion of relevance and irrelevance? And it's not so easy because we don't have a notion of RG or adding a relevant and irrelevant operator necessarily to any type of field theory. So we're not even close to this level of understanding. And so you could ask this hypothesis, can I use scaling theory to understand relevance and irrelevance? The answer will be yes, okay? It's going to be all the power that we have from scaling theory will hold as long as we ask the question in the right way. And so to ask the question, I do not have a frozen computer.
Because it's running out of juice.
My computer?
Yeah.
No, it's full.
Yeah.
Okay, so to orient everybody, and what I'm going to use, basically, it's basically a spatiotemporal Harris type of argument. So to orient that, let's remind ourselves of the quantum critical fan for ground state quantum phase transitions that we all know and love, all right? Or maybe not all love, some do. But, and when you learn this, the difference between the classical phase transition at dimensions D and the quantum phase transition that lives at a higher dimension D plus Z is the dynamic exponent, which characterizes the quantum dynamics and relates energy and length, okay? And for example, for the Trenz-Ising model, we know that has a Lorentz invariance, where Z is, for example, equal to 1. So here's an example. And so you want to now ask, if I now add a random perturbation to this critical point, is this transition stable? This is just the standard Harris criterion, okay? So you can add such a perturbation, and this allows you to write down a Harris criterion whether or not such a transition is stable to the presence of disorder. You can then ask if I have not disorder in space, but temporally random, okay? And it turns out for instead of D, you enter Z, okay? So the dynamic exponent is now dictating the stability, and you can put it all together for a completely space-time random perturbation, where the stability now is listed here, okay? And this is a statement about ground state phase diagrams, and I'd like to bring this perspective to show how we can understand measurement-induced criticality in this slide, okay? That's the idea. And so basically by looking at the measurement-induced phase transition, which will fit into something like this, I'm going to be able to add disorder or temporally random perturbations and change the fixed point dramatically following this underlying notion of relevance, okay? So I'll find things that are relevant, add it and change the fixed point. That's that kind of the idea. So let's get there, okay? And if it's not clear, please just stop me.
But
So-
can I just, so this is kind of a little bit heuristic, right? It's not a-
Absolutely heuristic.
Yeah, okay, thank
Absolutely.
you. But at least it's a guiding principle.
It's a guiding principle that I'll show you will work
Okay,
to a T.
wow, okay.
Yeah, basically. So, but there's some guidance from percolation as well, is all that I'll give you. So, okay. So I'm gonna move away from order parameters to entanglement, which is why it's so heuristic and we don't have any rigor behind what I'm saying except for particular limits, okay? And what we're gonna think about now is instead of classifying phases based on an order parameter, we're gonna think about the scaling of the entanglement entropy having a particular property. So if I'm highly entangled, I have a volume law-like scaling. Weakly entangled, I have an area law-like scaling, okay? And as we now know, if we have random measurements, we can drive transitions basically between highly entangled states and weakly entangled states. And you actually do have universal properties in the entanglement across such a phase transition. Okay, so let me just write down these models to put us all on the same page because of different backgrounds. So we're gonna think about quantum circuits. So we have qubits, no energy conservation, and we have time. Okay, and we're gonna think 2 qubit gates, everything's gonna be local operations. And the most interesting problem, the one we want to solve, the physically relevant one, has spin-half qubits. And so we have so-called Haar random gates. This is the most generic quantum problem. As I said, there's analytic tractability. So if we take that local Hilbert space to infinity, you can take a basically semi-classical limit, in which you can map this problem to various different kind of StatMech models. And then you also have basically a numerical tractability, which is kind of like an integrable point of the problem, the so-called stabilizer limit. You take a special class of gates and you work on this class of states and operators, it can be simulated with classical efficiency. Okay, and so these are kind of 3 different types of models we're going to consider, all right, as I go through the talk. Okay, and now I'm going to add measurements to this problem to drive a transition out of something highly entangled to something weakly entangled. And I don't measure every site. Obviously, this is disentangle everything. What the green dot is saying is I measure that site with a probability P. So if P is small, I don't measure very often. If P is large, I measure often. So here's an example. I threw my dice and I measured at these sites. And so now my dynamics is no longer unitary and it's interspersed with various Krauss operators. And I know the outcome of the measurement, which is fundamental to the problem. It's not dissipation. Okay, so I don't know the measurement. It's very different. Knowing the measurement allows me to form nonlinear averages. It's fundamental to the problem to know the outcome. Okay. And so now you can take this limit where it maps to a Q-state Potts model, and you take this Q to infinity, it basically goes exactly to percolation. Okay. And so how do you see this heuristically? So heuristically, you can view the unitaries as forming a network, and the measurements is cutting that network apart, and the entanglement in this picture is just counting how many bonds in that network you have the half cut. Okay, this is space and time. Whereas if I measure a lot, I completely disconnect the network, and there's basically just coupled clusters that are all local. Okay, so my entanglement is going to be basically area log 1D or constant. Yeah.
In this business, are you interested in thermodynamic limit? Or
Yes.
But in all real circuits, it's very much not thermodynamic limit.
By what do you mean by real, like physical world?
Yeah, I mean.
Or do you mean like a simulation?
Whatever, so I mean-
Well, if you simulate stabilizer circuits, you can get really big sizes. It's classical efficiency.
Yeah, and also, sorry, are you interested in averages or typical? Because
That's what we'll We'll get into all this. So the typical and the mean will be basically the same until I add static disorder and we get rare events and all these things will die after physics and then those things will matter. So yes, please.
Why does the connection with calculation require the large Q limit? Is it because if Q is finite?
You can't, the mapping is, so the mapping is not, so if Q is finite, you have a really complicated step mech model that you don't know how to solve. And if you take Q to infinity, it's like a saddle point and you get a Q state Potts model. That Q goes to 1, basically in this Q doing, so this little Q going to infinity is equivalent in that mapping to a Q state Potts model, Q going to 1.
Which is perfect.
Exactly. And so you would predict it should be bond percolation universality class, which tells you that the growth of a cut would grow logarithmically. Okay, and it actually tells you the coefficient also is universal, and it tells you the critical exponents are also known exactly. Okay, so this is like, you know, the Lorentz invariant example, and we also have complete control over this, so we don't understand this, and it maps percolation. There's a transition. Okay, so you want to solve the completely quantum problem. As I said, I could also have done stabilizers. But to do the quantum problem is large finite size effects, so you have to be clever. And so to get rid of the logarithm in the entanglement, which is going to spoil any kind of scaling you can do, we took inspiration from Kitaev and Krestel or Levin and Wen, which constructs a so-called tripartite mutual information, which subtracts the log. Okay, and so as a result, if you just plot the data for different system sizes, they cross at one common point, and that's where you can estimate the transition to be. And you can then worry about finite size effects. So now you can test this idea on stabilizer circuits, where you can go to 500 qubits. So you know this answer already on large sizes, and you can then test how well we get it, and you would just increase one more digit of accuracy by going to larger sizes. So this quantity has very weak finite size effects. It's a very nice quantity to look at. Subtracts a lot of the subleading terms. Yes, please.
When you go to stabilizer circuits, they're supposed to be the same universality class?
No. I'll get to that. No. So there could be other corrections on the HAR that could maybe be, yes, so.
But maybe in Q.
That's a very good point. So we don't actually know if the finite size corrections are the same, but we're using it as an anchoring point to test the quantity. We looked at several different quantities, and then you can find the ones here that have large finite size effects on these sizes. So like
still for large Q or not? You're doing.
So stabilizers is a different limit than, so large Q is analytic, stabilizers is the different limit.
Okay.
That's numerical.
Okay, thank you.
Yeah, yeah. But you can think of it as a different semi-classical limit.
Thank you.
Yeah. And so here's convincing you that there's actually a phase transition. You have very nice scaling, data collapse, but you have an exponent which is hard to discern. Okay, so whether these are 3 different universality classes, percolation, quantum, and Clifford, took us actually a lot of work. And when we first finished this paper, we didn't know. And this is a whole other talk. I just want to kind of set the stage. But you can, using methods from conformal field theory, particularly percolation, borrowed to quantum circuits, you can compute the so-called effective central charge of the logarithmic conformal field theory, and you can really discern that the HAR problem is different than the Clifford and different than percolation with numeric accuracy. Okay, so now you can ask, why did I tell you about this Harris criteria in the beginning? Let's make sure this is stable within my context, okay? So nu is 1.3. So the space-time dependent Harris criteria says that it's stable as long as nu is bigger than 1. So, okay, we're good. Okay, so now I'm going to start playing with this idea, okay? So I'm going to first ask, now, is this transition stable to static perturbations? And I'm going to show you it's not, and it's going to allow me to manipulate it and find a completely different type of phase transition that I have never really encountered in my life yet. So it's quite interesting. And if you have encountered an example, please point me to some literature. Okay. So I'm going to shift gears to the motivation and hop into this whole idea of now adding static disorder. This is experimentally relevant. You're thinking about qubits. Of course, we're not getting to the thermodynamic limit anytime soon, but if you're thinking about actually, solid state based quantum computing, you're going to have intrinsic disorder. And so you can ask, is any of this stuff stable? And you know right away that it's not, because nu is 1.3, it has to be bigger than the 2. And so it should be unstable. And it's actually known that percolation is also unstable, the static disorder. Yes.
Random locations of the measurements are not disorder already? Or?
So that's space-time disorder.
Oh, I see.
because in space and time it's random.
Right, I see.
So I want to introduce static disorder,
Oh, I see.
okay? And I'm expecting rare regions, so I'm gonna utilize these Clifford circuits, so I can simulate very large sizes.
But it's kind of extended in time, right? If you put, like in, there was this real space RG business, I think.
It's like Collinger disorder
Yeah, so basically.
in imaginary time, yeah,
So is it equivalent in a sense?
it is. And we can do RSRG with Collinger disorder, and that's like our large Q limit in this model. Yeah. But, okay, so you can do this several ways. You could put the static disorder in the gates. We put it in the choice of P's. We make them static, and they're different in space, but be uniform in time. So the value of the P is what's fixed, but whether I measure or not, it's different every time. So there is disorder here. Okay, and you can then amplify rare events by choosing distributions that have a tail. Okay, and you can then vary that power law. And here's just an example of that distribution with a very, very large tail. So you can see that even if I'm at small p, I can have a tail towards large P, putting me locally in the wrong phase. And as Victor already pointed out, do I need to worry about means, you know, and typical values? And in the standard LIPT, where you have space-time randomness, it turns out that's not a relevant issue. But now when we go to the spatially disordered problem, you get very broad distributions, as you would expect of Griffiths physics. And so here I'm showing you as we move through this phase transition, which I haven't told you yet there is one. But we're gonna have two different phases. The volume law like phase is very broad, and area law phase like this is exponential. And this is this I3 quantity, this tripartite reduced information I introduced earlier. And what we realized is that there's a strong finite size dependence to these distributions at small I3. And if you think about it, if I'm in a volume law phase, what that really means is my entanglement is always connected. Okay, that's what volume law means. So I can never find a sample where that's zero. So the probability of finding this equal to zero is zero. It's a little convoluted way of saying something.
So you have two.
So this is going through the transition. So let me show you this data. Okay, so this is this value, like integrating that first bin of the distribution. And you see a very beautiful crossing in the data. We had several different probes. This is the most clearest one. We had several different ways of diagnosing the transition. They were all consistent. And what you see here is that nu saturates the bound. And this is why I'm saying it's not just heuristic. So nu flows to the value of 2, which is the value is basically, it has to be at least. Okay. And we're going to see that's going to be consistent as they start varying other things. Okay. So now I want to show you what rare regions look like in these problems. So what is a rare region? So we have two different phases in disorder. So locally, we're in the wrong phase. Okay. So what does that mean here? So what I'm showing you here is an entanglement versus space, and each different line is a different time trace, a different point in time, and the color is the value of the measurement rate. So you can see here that the measurement very close to 1, measurement very close to 1, it creates a so-called entanglement bottleneck where the little local region that looks like it's in the area law phase. And so entanglement has trouble spreading through that region, and what that does, if you average over these bottlenecks, it's going to give you a power law growth that's no longer ballistic in the so-called volume law region with the dynamic exponent that's continuously varying. So it's a way of probing the dynamic exponent, which you see here, whenever z is going to 0, so z is going to infinity. Please.
So it's a region where, let's say, you're measuring a lot, but then inside that region, you're almost not measuring or something.
Yeah, so like you measured a lot here, you measured a lot here. Like in this region, you measured a lot, so it's very disentangled. So that's the rare region.
Right, okay, good.
And there's a couple of those in this particular.
Even though you would say you're in the phase, if it was not disorder, you would say you're in the phase that's entangling phase, that's spreading.
Holistically, that's right, exactly, for the whole phase.
So there's something like evidence of the tracking this
Yes,
and what would help.
that's correct. This just goes to linear growth.
And if you replace it by quasi-periodic, it goes.
So I'm gonna get to quasi-periodic soon. And yes, there are no Griffiths effects. I'm not gonna get into that in the talk, but yes, in the quasi-periodic case, it's a bit weird. So there's Z is basically only infinite at the transition, which I can, yeah. You said it. Wait. Okay, so now you come to the area law side, and you can ask, how do I determine a Z? So you can't do the same trick because it's just area law. But you can stare at this and you can say, well, look, I have a region. Now what's a rare region on the area law side? It's going to be a region where I don't measure very often. And that's the region right here, which is highly entangled. And so the idea is I'm going to now bring in my own ancillary qubit, and I'm going to couple to the system and ask, how long does that take to purify? It's that ancilla-qubit is gonna couple to the most entangled region. So the most entangled region is take the longest to purify, and I can then probe that. I can probe this so-called tightly entangled bubble by adding this qubit. So these are the words I was just saying. So this is this lifetime to purify, and you can then pull out a z, and you see this 1 over z is going to 0. Okay. So we have signatures on both sides of Griffith's physics, and in the transition, and then you can try to basically guide yourself with real space RG, which dictates this root L growth at the transition, which we find to be consistent with a logarithmic growth at the transition. So this log t and root L is very different than a Lorentz invariant transition, which would be log, and log is this conventional case. The root L means that I have a exponentially long relaxation time, right? So the time to relax is exponentially long in the system size, and that's the ramification of z going to infinity.
Yeah, so this is my question. So we used to do this for wines and metals, and then the Griffith case would do a avoided crossing.
Okay, sure, yeah.
Similar physics that happens here.
Well, there you have like a transition that is destroyed by the Griffiths effect, and it doesn't fit into the Harris classification. With that, yeah, that's an example of a problem that you try to do Harris, and it seems to be stable.
Oh, okay.
But you have Griffiths effects that are beyond the Harris argument that destroy that. Yeah, which is, yeah, but that's beyond it's beyond anything I'm talking about here again.
Harris stable, but Griffith's unstable.
Yeah, I don't know. Yeah, I don't know the other examples, but yeah. Okay, so the last thing we want to do is probe this dynamic exponent z directly in a computation. And so this ancilla qubit, you can actually do that by just letting it relax at the transition. And if you remember activated dynamical scaling for infinite randomness, it follows this particular form with the so-called activation exponent psi. Okay, so we get these two exponents that are supposedly universal, and now we can do this large Q limit, which maps this to basically a Q-state Potts model with columnar disorder, which you can apply real space RG arguments to, and you can analytically compute these exponents, and you find amazing agreement with the numerics. Okay, so this is very satisfying, but we then wanted to play with this a little bit, and this is when Sriram's question about quasi-periodicity comes in. You can now ask, well, can I vary my universality by hand? Okay, so I now want to introduce this notion of the Luck criteria, which is the stability to a quasi-periodic perturbation. And there's a so-called wandering exponent, which I bet everybody in the room has no idea what it is, but unless you've heard me talk about this already. But it's a notion really from mathematics, and it's basically how much this wanders, these quantities wander, you average them over a bin, and everything we're used to, like cosines, they have no wandering exponent. They don't grow when you average them over a bin. And so if you add this perturbation beta 0, the transition should just be stable. It should be the standard measurement induced transition. So very good.
Luck is like lucky, or is the name of something?
This guy's name. You're studying 5-4 with quasi-periodicity. I know, it's not Lucky, his name's Luck, yeah. And he knew about this number theory. So we wanted to play with this, and so we kind of dived into a bit of number theory. We wanted to vary this wandering exponent. So how do you do this? So let's move away from a smooth structure and think about Fibonacci words, for example. So the Fibonacci substitution rules to build Fibonacci words, 0 goes to 0 and 1, and 1 goes to 0. So you can build up words, okay? And if you do a Fibonacci, you can then think about these so-called substitution matrices, which are how these words map to each other. And you get these eigenvalues, and these eigenvalues of these matrices basically tell you the fluctuations of the word and how much they grow, okay? And so we want to control the fluctuation, which is this eigenvalue. So a non-P-Zot word in mathematics, if this eigenvalue of this matrix is larger than 1. What that means is that if I compute a variance of the length of a word over some size s, it actually grows with the size L to the beta being the wandering exponent. Okay, so this is, this is true for example, disorder, a random walk, beta is a half, right? And so I'm finding quasi-periodic structures that grow as you change the size. There's no Griffiths effects, but it's still changing how large the fluctuations are. I can control this by hand, and the data looks very similar, so I'm not going to show you any data, I'm just going to show you the conclusion. And the conclusion is you get a whole class of fixed points, as long as betas makes it relevant, and you get a whole class of fixed points controlled by this wandering exponent. And these exponent, the critical exponents are then completely controlled by the wandering exponent. And the random one is just beta is a half. We get a whole family of fixed points, and we can put this together in terms of like an RG flow picture. And here's your measurement induced transition, fuzzy periodicity, which is then irrelevant, which is then perturbed to this infinite random fixed point. Okay, so I don't know how much time I have left, but in the last bit of time, we're gonna move to
5 minutes.
perfect. I can do this pretty quickly. We can just skip over some stuff here. So, okay, so there's these two papers that actually give me a bit of inspiration about thinking about defining a model and doing a space-time rotation. And if you view the gates as a tensor network, that rotation is well defined. Okay, so I want to think about doing a rotation on my circuit, space-time rotation. And if I do that, then x maps to t. Okay, t goes to minus x, which basically means the dynamic exponent has to become inverse itself. And so I can now define a model where instead of measurements being random in space, they're random in time but uniform in space. Okay, and when I do this, yeah, so okay, let me just say, if you are worried about this rotation, which you're welcome to be, there's a so-called dual unitary limit where this rotation I can show is innocuous. I can prove graphically it doesn't do anything, though I have not solved that problem. Okay, so I right now feel that the universal properties will be independent of such a rotation, but I have not explicitly checked that yet. Okay, so here's just the argument that something that was going to infinity should now be going to 0. I want to try to show you that I can actually find critical points where z goes to 0, which means things move infinitely fast, as opposed to very slow. Okay, so it's the opposite of infinite randomness. Okay, and so this is then brings us to this generalized notion of Harris. So now we have disorder in time. Okay, now we can ask, is this stable? And again, no, it's not. That's a flow to a new fixed point. Okay, and so I'm going to convince you now it's going to flow to the z going to 0. And actually, what are the phases of the model now? So in one of these first space-time rotation papers, they realized that if you rotated these rare regions from that volume law phase, you could actually get something that grows sub-volume law. Okay, and that's exactly what we see here. So the volume law phase is not really a volume law phase anymore. And the reason is temporal rare regions, which I'll talk about in a little bit. But you can clearly see a transition from sub-volume law to area law. And why do I have a sub-volume law? Here's a snapshot, one sample, okay? And you can see, so the green are the measurement value, and the red is the entanglement. So I'm highly entangled, and I get a very large measurement, but it's not above PC, so I get a little bit of a drop. But if I get an event where it's larger than the critical value, I get a huge drop of the entanglement. And you can see it doesn't happen to get measured again for a long time. I can go all the way back. So the averaging of this sawtooth-like structure gives you a sub-extensive growth. Okay, so you can then estimate the z going to 0 from this power law. Getting z from the other side is a bit non-trivial. I'm going to kind of skim over this just for sake of time. Okay, and then I want to show you that now if I use the same criteria, I still have broad distributions in space-time. I now look at temporal exponent, okay? And I can then verify all of this scaling. So you're going to have another bound. So this new tau being, the value is going to be related to a bound. I'm going to tell you in a second. And then I can use the same methods of this ancilla qubit and watching it relax to get this activation exponent. And indeed, you get basically 2, which is that bound 2 over z, where z was 1. So it's again saturating the bound that is dictated in the beginning. Okay. And there's something rather interesting with these exponents. This is related to nu times tau. And nu goes to infinity because z goes to 0. In case I think Kuhn's probably thinking about that, I can see him. So that nu actually goes to infinity as z goes to 0. It's actually natural if you think about it a bit. And so you have to define some sort of nu tau, which has to go to a finite value, which actually has to be bigger than or equal to 2 based on this criteria. So it's a very interesting application of the spatiotemporal Harris criterion. I'll just end with this rather interesting application, which you can now ask, how does information spread as I change this dynamic exponent? So if I inject an ancilla qubit, so I can couple a qubit in here, I can then now ask, what is the mutual information with this guy after it's spread a distance x, okay? So if it's 0 over here, that's gonna be the boundary of how far it's spread. It's like measuring a light cone, but you don't have unitary dynamics, so you can't actually define operator growth because you don't have Heisenberg evolution. And so this is how we get around this. We measure the so-called mutual information in this region and then see where it's, X is basically where it becomes zero. Okay, we call this Xi, and you can see from these three classes of transitions, Z going to infinity, Z is 1, and Z going to 0, you can send quantum information at different rates.
So what is B?
Where? Oh, B would be this Ancilla qubit.
Its location or just or?
It's just this site, you just trade.
Okay, that's I see.
Yeah, it's like the mutual information between the Ancilla qubit and that region.
And then you track where the end of it boundary vanishes.
Exactly.
Okay.
Exactly. It's actually considered in Andy's work, your colleague
Yeah.
has feedback and he gets around Lee Robinson. So here we're very much violating Lee Robinson to the measurements. But we don't design any feedback to choose, yeah, so
Okay.
we don't have any feedback. It's very much connected, but, okay. But here's you showing you that even though there's a parametric difference, it's actually sending it infinitely fast. The velocity is going to infinity. And you see this beautiful collapse, and you can then just look at all three. And so you can send information very fast. You can actually look at teleportation events. I didn't get into any of that. Here's static disorder where it's very slow, and here's Lorentz invariant. So I'll just end right here. Okay. Thank you for your questions. Yeah.
Okay, I have a quick question. So in this measurement of this transition, so where is it going in terms of like experimental realization? Is there any hope to actually see any of this stuff?
So what I've been doing is, when I think about experiment, I think about bringing in feedback. And when you bring in feedback, you don't require any post-selection to see a lot of the physics. And so in terms of measurement only, there is no way around the post-selection problem. It's fundamental to the problem. So I don't think
What's the
there-
problem actually? Can you explain? Like,
So-
why can't they just do it like, I don't know, in Google or wherever? So what's required? What's the dream scenario like?
So I mean, okay, so if you want to measure any entanglement, it's exponentially hard.
Is it the only proxy to
No,
measure
so it's
it?
not. So I don't think I have a slide on this in this talk. Yeah, I don't have a slide on this, but do it. Where, right?
Oh, well, there's nothing to write.
Basically, you want anything nonlinear, okay, anything nonlinear in the density matrix. So to form a nonlinear average of the density matrix, you have to either post-select under the same measurement outcome or keep all of those events, able to do a nonlinear average. So to do a linear average, it's not exponentially difficult. Okay? So anything linear in the density matrix is not exponentially hard. So you want to try to get this transition to be visible in things that are linear in the density matrix, which is fundamentally really not possible.
But if you, for instance, if you map it back into this real space RG, I think it started with Daniel Fisher and Gil Raphael and others. They were doing it in 1D chains, then there was Matronic and Hughes.
Yes.
They did it in 2D, similar to what you're doing. But they had real spin systems with some order parameters and all that stuff.
Yeah.
Is there an analog of this where you can just measure some sort of analogs of whatever they were measuring in these sort of spin chains?
And that's what we did here with mutual information. So the correlation functions become useful information in the measurement induced transitions, but in doing that in experiment
Oh, they can do it?
is exponentially difficult. And so if you have feedback though, then it becomes linear in the density matrix. And with Srirang, we have found transitions where the measurement induced transition coincides with the transition that you can see that with the quantity linear in the density matrix. So that's the angle.
Just a little bit along those lines, you mentioned feedback. Feedback sounds like post-selection.
No, so what I mean is like, let's say you measure it up, you make it, then you add a unitary and you flip it down. So you didn't get rid of that, you kept that run, but you changed it based on the outcome of the measurement.
Is that the same as heralding?
But then
Yeah, whatever the name you wanna.
But when you flip that, you are affecting the other. When you measured it, even though you flipped it, the measurement affected other
Yes,
qubits.
absolutely.
So it's not. Right, so it's not.
No,
It's
no,
not also, right.
post-selection means that I
throw it
measure,
up,
I only,
throw it.
let's say I only keep runs that get me up, down. I measure 3 spins, if I get up, down, I keep it. If I didn't, then I throw it out. That's what we mean by post-selection.
But I guess what I mean is flipping by unitary because you measure it to be the wrong side. It's not really fixing it. It's not really, because there are other qubits than.
So that's, okay, that's what these so-called control transitions that we've discovered, and you have transitions, so you have chaotic dynamics, and you can overcome it with this.
I see.
And there's a phase transition between phases where you overcome it and phases you don't.
Good, good, okay,
And
thank
there's
you.
classical limits where you can do this, where
Thank
you
you.
have chaotic transitions in classical models. They're really cool, actually.
Okay, wow.
The classical problems are very interesting as well.
Thank you very much. Suggested that we have break until 3:30.
Yeah, let's just have a bathroom break and, that we catch up on time. The bathrooms are, toilets were,
Yeah, I was trying to recall.
Where do you see it? It's already decided.
No, I mean, yeah.
So there are three more people, there's Cheryl.
Yeah,
and,
so we're working, yeah, we have like data on 40 units.
Negotiate with Cheryl. You might have to test with Cheryl.
You really have some time. Yeah, because there are some people who are going to come to this issue.
You can finish in 15 minutes.
I can. Okay, I'm going to speak extremely fast. Catch up. Okay, so I'm going to talk about fluid dynamics approach to topological quantum field theories, and then the example that I'm going to consider is fractional quantum Hall effect. So I'm going to use 200-year-old fluid dynamics techniques to derive things about topological aspects of fractional quantum Hall effect. Okay, so and these are the collaborators. My student Dylan Reynolds, Gustavo, who is in the audience, and Parmeshwaran Nair. Okay, so let me start with Hall effect and I will quickly rush through. So there is a famous paper by Hall in 1879. So I kind of read this paper and I realized that the motivation of this paper was to disprove Maxwell. So Maxwell thought that if you have a conductor, the electromagnetic forces cannot deflect a conductor, so that means that the currents are not getting deflected. So Hall kind of used his Hall effect to prove Maxwell wrong, that actually there are currents inside these are pre-electron days. So Maxwell thought that there are no microscopic things underneath a conductor, so nothing is to deflect. But then Hall showed that there are these microscopic entities that are carrying current, and the Hall voltage is an impedance of that. So that was this experiment. And if you do a simple Drude model of this, you kind of apply this Newton's laws to this average quantities in some stochastic way subject to Lorentz force. Then what we see is that there is this rho xy, which is a linear function of the magnetic field with some almost, it depends on the carrier density and the electronic charge, that's it. So it doesn't depend on this tau or all the non-universal parameters. So this 100 years, almost 100 years later, this was taken into extreme quantum limits by von Klitzing, where the classical limit is still hiding in this corner, but if you jack up the magnetic field and lower the temperature sufficiently, you got these beautiful plateaus. And I don't need to go deeper into the importance of this for condensed matter. And then further cleaning up the sample and further jacking up the magnetic field and lowering the temperatures, you got what is known as this famous fractional quantum Hall effect, where this in the integer quantum Hall case, nu is the number of filled Landau levels, but fractional quantum Hall effect is a purely strongly interacting phenomena where even the partially filled Landau levels kind of end up in some kind of an incompressible state. And the best attempt at solving this problem is to guess the answer, and Laughlin actually guessed the answer. So this is the answer. It is such a good guess that you don't even need to know how to improve it, which will give you some understanding of it. And so Laughlin state is one of the approaches. Outside of that, there are some effective field theory approaches of composite bosons, which is going to be the focus of my talk. And then there are composite fermions, which is not I'm going to talk about. And then I'm going to kind of say that more recently, lot of kind of energy and smartness has been devoted into using topological quantum field theory which is made use by Venn. But the motivation of this talk is basically, if you want to understand human anatomy, you cannot be happy by looking at the skeleton of the body. You have to study the flesh and all the organs of the body, how they attach to the skeleton. So the TQFT is like the skeleton of the human body. And what I'm going to do is I'm going to add some flesh to that skeleton and see how the dynamics of this matter rides on the underlying topological aspects of this theory.
So that's what I'm going to do. I'm going to kind of go beyond this TQFT and then consider composite bosons, which is matter coupled to the topological theory. Okay, so one of the important things about this theory that I want you to pick up, forget about everything, but remember this, that the electrodynamics of a quantum Hall liquid can be summarized in these two equations, that the density is pinned to the magnetic field via the sigma xy term, and the current is the proportional to this skew Z cross E basically, okay? So the consequence of this is that if you put a boundary in the theory, then what happens is that if you apply a tangent electric field, and so then the charge kind of goes to the boundary and then moves along the edge. So this is the aspect of the theory which is going to be crucial for the rest of my talk. And all this nice electrodynamics can be written as an effective action to this Chern-Simons theory. Okay, and as the one way to understand for more mathematically minded people is that Chern-Simons theory is not gauge invariant with boundaries. So to make it gauge invariant, you need to add some gapless degrees of freedom, which is kind of this gapless dynamics that I showed in this animation. Okay, and for more experimental minded people, there is this picture of skipping orbits, where at a very strong magnetic field, you have these cyclotron orbits which are tighter and tighter, but then as they go towards the edge, they cannot complete, so they kind of skip around and go as a chiral edge. So all this can be is an essential feature that I'm going to use later on.
Your EX here is perpendicular to the boundary.
EX is tangential to the boundary.
No.
EX is a tangent electric.
Well, okay, to get the inflow,
Yeah,
but then,
something should happen to.
I mean, E cross B drift if the.
Yeah.
Perpendicular to the boundary.
Yeah, but then the question is that what happens at the boundary?
Right, okay.
Right, so at the boundary, something has to, either you constantly accumulate charges infinitely at the boundary, or they are carried along with a chiral edge dynamics, which is what we see in this.
Right.
So any theory should have this chiral edge dynamics so that there is no singular deposition of charge at this point, as a function of this tangent. Okay, also known as gauge anomaly. Okay, so let me write down how to write a higher. So as I said, I will use a fluid dynamics approach to this problem. And the way to write a fluid dynamics theory of this problem is that consider this Laughlin wave function. So if you try to break it into pieces, this piece, the exponential of Z square piece, is a bosonic piece, because if you exchange I and J, nothing changes. And then this particular piece is the singular gauge transformation piece, which kind of attaches statistics to it. So in an effective action way, this exponential part can be written as a bosonic matter, and the singular gauge transformation piece, which gives a statistic, can be written as a Chern-Simons term. So this is a matter, Ginzburg-Landau matter that is coupled to a background Chern-Simons term. And if you study the density fluctuations of this theory, you will get back Laughlin state. And this was done by Zhang, Hansen, and Kivelson. And the original superfluid, this is what is also known as the superfluid interpretation of fractional quantum Hall effect. This is different from the composite fermion picture, which has no superfluid interpretation. So I'm not going to consider that. Yeah.
The relation between M and mu?
Yes. Yeah, so M is basically some odd integer and mu is like 1 over the odd integer. 1 over M.
So your bosonic field is not residing on any topological M.
Sorry, what?
So you're assuming that bosonic field is not residing on a topological M.
There is no band in my.
Well, you have kinetic energy for far field.
Yeah, so the question is that how do you add kinetic energy to this Laughlin state? So the way to give that kinetic energy to the Laughlin state is that these are some kind of a condensate degrees of freedom. Think of it as a superfluid, but then I'm attaching them to statistical gauge fields, which will convert these bosons into composite bosons. Okay. So the vortex excitations of this theory are the anyons of the fractional quantum Hall effect. So a simple prescription to convert this action into hydrodynamics is that take what is known as Madelung transformation. So you take this condensate and split it into any complex function can be written as this, the real function times the phase, and then identify a superfluid velocity, which is like almost like the gradients of this theta. But I'm going to use a slightly different definition where I will subtract it from some divergence-less gradients of density, and then write the hydrodynamic equations in terms of V and N. Okay.
So is that piece arising from derivative of square root of n?
Yeah, so this is what is known as quantum pressure term. I'm trying to subtract off the quantum pressure term. So there are this d square term.
Right.
So it hits twice on the square root of n. So it gives you this ugly di dj log rho type terms. But and then that's the two derivatives of density.
Right.
So what I do is that I absorb that one of the derivatives into v in a way that I don't change the continuity equation. But at the same time, I get some single gradients of v in my Euler.
But why is there an epsilon symbol there? Like, where did that come from?
I can shift my velocity by any divergence-less currents,
Oh, I see.
and it does not change the continuity equation.
Just a pure.
Yeah. The d star law,
You're just saying it's just convenience.
convenience
Okay.
for now, but it will give you, it will allow us to bring some intuition from some other fluid dynamics approaches. So one of the conveniences that you can immediately see is that, believe me, that these are the equations of motion that you get from that action. So this is the continuity equation, and see that you can shift anything by this di star and it will be still okay.
Right.
And then the advantage is basically that the Euler equation is the first order hydrodynamics basically. So it can be organized in gradient expansion up to the first order terms. And the first order term has the stress tensor, which is where this is the interaction induced pressure term. And then there is this nice looking red term. So if you track the red term that I shifted in V, this is what it leads to in this Euler equation.
So you get all viscosity.
Exactly. So this is true for not for fractional, any nonlinear Schrodinger equation. So
Any magnetized plasma.
yeah, exactly. So this is basically the diamagnetic term, which is kind of doesn't make any difference in the bulk, but it makes important intuitive directions to the boundary effects, basically.
So this guy doesn't affect the divergence of T, that's what you're saying.
Yeah, exactly. No, sorry, it takes the divergence of T, but it doesn't change the continuity equation, if I put it or not put it.
It's the real.
Yeah, it changes the Euler equation, but it doesn't change the dispersion. If I study the modes of this problem, the dispersions are same whether I write V with the red term or without the red term. But then, see, this is almost like a full derivative type term that I use to shift. The boundary conditions will be more intuitive in this velocity rather than the other. And then this is also known as the quantum Hall constraint. Where it comes from is that if you look at it, there is a A0 term in this Chern-Simons term, which is linear.
Right.
And it appears here in this inside this dt, and it appears here.
Right.
So that's like a Lagrange multiplier of my theory. So if you vary over that Lagrange multiplier, it gives this quantum Hall constraint, which is in superfluids, vorticity equal to 0 is one such example of this. But in fractional quantum Hall effect, it's a bit more general, where the vorticity instead of being 0, it's pinned to the density.
You mean it's modified by this n term or not?
It is. The definition of vorticity is modified because if you take a curl, the curl of this d star is Laplace. So it does modify the definition of vorticity. Yeah, so you see, this is also, the red term also appears here. So the quantum Hall constraint is modified here.
But so that's not a problem?
That's not a problem for the bulk or anything. Yeah, it's just it's a choice, right? The action didn't prescribe me what velocity to choose. It's up to me to choose some convenient velocity.
Definition of velocity.
Yeah, and make sure that the bulk physics is retained, but then the boundary physics, when I try to study that, it guides me, because first order, another thing is that the first order hydrodynamics has well-named boundary conditions called no slip or no stress. If you have some crazy gradient derivation, they are unnamed boundary conditions, which I don't know how to import some intuition from fluid dynamics. Yeah.
If I integrate all the bosonic field.
Yes.
My mind.
Yes.
You generate Maxwell term, right?
There are various ways to do that.
The action that you took on.
No, I think that's not how the way, there is a dual theory to that. So you can identify a magnetic field term in terms of density of the matter and the electric field of the matter and write a dual Maxwell-Chern-Simons theory. Yeah, but it's not like integrating out. It's like dual.
Equations of motion.
Yeah, on the equations of motion.
But you could just integrate, like take the functional integral. From your generation should be not there.
It is Maxwell in some capacity, but the way I view it is that
My earlier question is a political background, no, because just quadratic dispersion, right?
yeah, it's just there is. Yeah, exactly. I will come to that. This is a very subtle point. It's important. I will come to that. I will show you the linear theory fully.
Just make question, so when we do kind of, those things quantum mechanically, we attach flux to particles.
Yes.
And it looks like you are attaching fictitious flux to density, right? Is that correct? Is there something beyond that?
Yeah, there's an effective theory, so I don't have a microscopic particle.
Right, you do not need that, so
Yeah.
you have to just have a one-to-one correspondence
Yes.
between the density and.
Yeah, this is like flux attachment procedure, yeah.
Fictitious magnetic, I'm just trying to understand.
Yeah, so and then what I'm going to do is that I'm going to study the saddle point equations classically about some mean field background, which is where the density will be pinned to that magnetic field, basically. Okay, and then the fluctuations about them, which is like the RPA type fluctuations. Okay. Okay, so then let me find out the boundary conditions of the problem. So remember that the one of the criteria for this boundary condition is that I want to determine the boundary conditions variationally. Okay, in typically fluid dynamics, you have shear viscosity and that plays an important role at the boundary, but those are not variationally determined. But in a superfluid system, then I can determine these boundary conditions variationally. And so if you try to vary the whole action in the presence of a hard wall boundary, like a half plane problem below this, then the first boundary condition that you get is that NVY is equal to EX, basically. This is like the anomaly equation. So just infinitesimally below this wall, there is a current that is flowing into the wall. And then there are few possibilities for the second boundary condition because it has this first order hydrodynamics. The first possibility is that you have no slip boundary condition, variationally determined. Then let's see what happens if you do no slip. So as you do no slip, you keep on turning on the tangent electric field, the charges flow to the boundary and just stay there. Okay, this is the scenario that you're talking about, that there is no movement allowed because of this second boundary condition. So I need to find a boundary condition that is compatible with this first anomaly equation such that there is no singular accumulation of the charge. And it turns out that the fluid dynamics knows about this. And then this boundary condition is the second possibility, which is the no stress boundary condition, TXY. Remember the odd viscosity TXY that I had? And the odd viscosity TXY, what happens is that it goes to the boundary, but then it moves along the edge because I have animated it that way.
So the boundary conditions, don't you have to basically derive it in some way? Put
So,
some complex.
In hydrodynamics, nobody derives boundary conditions.
Oh, come on, we do it in operational principle too, right?
No, but then it's all possibilities, right? We don't know exactly which one to choose from.
Depends on maximum.
Exactly. So you kind of derive, so this is what we are doing.
My fluid could be in contact with solid or with vacuum. One gives me no slip, another no stress.
But then this is and then there can be classical fluids and quantum fluids. So in quantum fluids, the no stress is the dominant type boundary condition. And so there is like a physically motivated choices you have to make among possibilities. Yeah.
But I mean, in principle, there is some microscopic theory which knows about smaller length scales and hydrodynamics, and it contains information about potentially more complicated.
Yeah, so I think in hydrodynamics, the microscopics are packed into the gradients of the theory in some magical way. Like for example, you don't need to run to daddy and abandon the force grain theory as soon as you hit some singularity, the gradients will rescue you. So then what happens here is that this is TXY is a no stress boundary condition which brings a length scale. Actually, that length scale is a magnetic length scale. So it kind of knows about this through the gradients of the problem. So you don't need to go to the microscopic theory to determine them in fluid dynamics.
I think that the point is like you can also obtain this variationally.
Yeah,
This
this
is
is
a question.
That's the starting point, but variational. So if you call the Chern-Simons-Ginsburg-Landau theory microscopically, we are deriving it microscopically.
Yeah. Can you just ask, can you go back? You keep calling that term Hall viscosity, but I think of Hall viscosity as at the level of the force, it's Z cross Laplacian of V.
Yeah, that's for incompressible fluids, but this is a compressible fluid with constraint. So that's how it shows up.
So you're saying your red terms become that?
Yeah, so if you take a del dot.
Looks like a gradient of divergence and the.
Yeah, but then there is an N here sitting.
And then what?
And then, so if you take N to be constant, then you get that Laplacian of theta.
Yeah, it's div N graphs.
Yeah.
No, I get gradient of curl V and I get.
Yeah, so you kind of, you will get it.
Okay.
Trust me. Yeah.
It's
You will get it.
divergence of a flux. And
Yeah.
flux is the rho times.
So you will get Laplacian of V star if you assume constant density.
Okay.
I can show you later.
Okay.
This is the one thing I'm not doubtful about.
Just one.
Yeah.
One derivative.
The animation, they're not solving the equations.
Huh? No, I'm going to show you why that is animation, what is behind the animation. So if you open the hood and see what is inside this TXY, so what you see is that this TXY in the presence of the tangent electric field looks like this. This is the boundary condition that I'm imposing variationally. And magically what happens is that if you use the bulk continuity equation, this identically maps onto a edge continuity equation, but for square root of n, which is like the dimensionally roughly the edge density. And then you see that there is an anomaly equation that emerges at the boundary. So there is an additional UN symmetry that magically appears at the boundary, which is packed into this. So basically 150-year-old hydrodynamics knows about anomaly equation in exactly this form. And then you can identify the square root of n as edge density and square root of n times Vx as edge current, basically. And this is basically the bosonization.
It's only 2D trick, right?
It's a 1D boundary of
Essentially
it.
1D, the
Yeah.
boundary in 2D.
Exactly, boundary in 2D.
Yeah.
And because odd viscosity can only appear in 2D.
Yeah.
So it kind of knows all this.
But this only happened if you included this modification of what you meant by B?
It's more obvious here, but then if I can shift it back, it will have two derivatives of density lurking around in some pesky way, which
You will correct the right hand side, the anomaly will.
it won't correct the right hand side. See, you can shift it here.
Okay.
So you can shift V back to some U, which is shifted by di star rho, and then you will see that there are two derivatives of density that are sitting there, which happens to be important at the boundary, but in terms of this velocity, it's just an anomaly equation, basically. Or you write it as this plus some diamagnetic.
That's what I'm saying.
Yeah, you can go back. And then even more magically, what you see is that if you ask what is the variational completion of this boundary, it turns out there is nothing but the chiral boson action that you need to add to your edge bulk physics to get this boundary condition fully variationally. So the variational completion of this anomaly equation of this no stress boundary condition is the chiral boson action. So this is like a 1850s derivation of chiral boson action because Clebsch derived this variation in 1850. So next year you could have derived this. Yeah. Okay, Gustav, you had a comment?
No, just that if you put electric field equals to 0, the no stress condition is a dynamical equation.
That's a key point. See, the TXY before like usually it's a shear viscosity term, so there is no hope for writing a variational action for that. But this TXY, because it's like a quantum fluid and odd viscosity, which is dissipationless, maps onto a dynamical equation. And then you can ask what is the effective action, boundary action for this dynamics is just the chiral boson action. That's it. So that's why I animated it that way.
So I missed, how do you go from left equation to right equation?
Yeah, so you use the bulk continuity equation. So TXY is basically dy Vy minus dx Vx. So you eliminate, and then this is all defined at boundary. So you need to use two things, the no penetration condition, modified no penetration condition, and the bulk continuity equation. You can exactly get that. Okay, so now let me do the linearized modes of this problem. So now we can kind of allow for some background plus fluctuations and absorb this Ey by B, Ex by B into this, and then write this effective. See, the reason I'm doing all this red will become clear because these are this extra things that not extra things, but I shifted terms, which are gradients basically. Okay. And then there are two boundary conditions, and this boundary condition I've written in a dynamical form because I know that now it's a dynamical equation. So let's study the modes of this problem. So if you kind of solve for the linear modes of the problem, then what you see is that there are actually two modes. And what is the upsetting thing about this story at the first look is that there are two modes going in the same direction. But we know that for Laughlin state, there should be only one mode at the edge of this. So what's going on here? And so one of the modes is basically this Kelvin mode, which is just C times K. And the C parameter is the interaction. It's a parameter that parameterizes V of n, the potential at the Ginzburg-Landau. I use the short range interaction, so it's the sound velocity equivalent of this interaction. And then the second is the chiral boson term, which is like 2ck minus, it has this gradient expansion at the surface. These are the surface modes of the problem. Okay. And
it's not negative, right? The chiral boson excitation is positive.
What is positive?
Masking, sorry. The omega chiral boson. You minus CK cubed, or just
it's small
It's a correction.
It's a correction, small correction. And see, the thing is that if you are condensed matter aficionados, you could immediately rule out this mode as a condensed matter mode, which captures bulk boundary correspondence. Remember that Hofstadter spectrum that we have? So if you put Hofstadter simulation with a boundary, the mid-gap states will always deform away from the bulk band and then go up and then merge into the higher band. So you have to disperse at some point to merge with the bulk bands. And the Kelvin mode never merges. It's almost like a zero sound mode, which is, and okay, so at this point, I have to tell you another paper that was written in 1879 by Kelvin, who was kind of trying to understand why English Channel was dumping more water on the French coast than on the British coast. And then what he took is that he took Laplace's tidal equations and put it in a channel and was studying precisely this problem that we are studying here. And he actually solved for the Kelvin mode of the problem exactly in the year 1879 as Hall effect. So my greatest achievement is to connect these two papers.
So far.
Yeah. And then because of this, and then you can get this chiral mode which depends on the sign of f, which is the Coriolis parameter. And Coriolis parameter is positive in the northern hemisphere, is negative in the southern hemisphere due to the projection of the spin along some normal. And what you see is that the ocean currents go one way in the northern hemisphere and go other way in the southern hemisphere. Not the reason why toilets flush in the opposite direction in the northern hemisphere and the southern hemisphere, which is probably fake. Okay, so now the question is that how do you rule out one of the modes, basically, okay? Because we need only one mode for Laughlin state, otherwise we are violating some serious central charge issues associated with the fractional Van Hall effect. So now I'm going to do the same toy experiment that test. See, when people study chiral dispersion, they always look at something moving chirally and call it chiral, but then they never look at the eigenvector associated with that mode. So the eigenvector associated with that mode actually tells you how the mode responds to the fields, basically. So if you see what happens to this mode as a function of this electric field, it responds, it goes up, but then it gets stuck there. There are no gradients. There are no higher powers of k for this mode to move around in the Kelvin. But that's why we kind of rule out, and then there is an additional artifact that this rho, the density fluctuations actually vanish at the boundary for this Kelvin mode problem. So that means that it does not lead to anomalous edge dynamics. So then we rule out that mode as anything to do with topological system. It's just some artifact of some fluid dynamics lurking underneath the theory. But then what you see is that the correct chiral boson mode actually does this thing because of the fact that it has this dispersive corrections there. So that's the story. And then you can actually study this chiral boson mode, solve this full inhomogeneous problem in the presence of electric field that is linear in T plus some homogeneous piece, which is satisfied by this. And then what we have done is that now we have taken fluid dynamics a bit more seriously. There is a powerful technique in fluid dynamics called method of multiple scales. The beating heart of fluid dynamics, I'm teaching a course here, and I learned that the beating heart of fluid dynamics is singular perturbation theory, both in the spatial and the temporal direction. And we kind of took this effective boundary equation and looked at this Vx, and Vx is like almost like a constitutive equation, which is a function of n and dxn and the gradients. This almost looks like a generalized hydrodynamics in some sense, where this V in that case is determined by Bethe-Ansatz solution. But here, V is determined order by solving the bulk equation. So there is a bulk and boundary system that you have to solve. And then you kind of precisely do the calculation that Korteweg and De Vries did for shallow channel by expanding this. But now it's a much more complicated fluid system. It's a compressible fluid with a Hall constraint. And then what you see is that you actually get a KdV equation at the edge of a quantum Hall system. So the weakly nonlinear theory of a Laughlin state is actually Korteweg-De Vries equation. And it's a generalization of chiral Luttinger liquid because what we have shown in this paper is that if you write a Hamiltonian of corresponding to this, then you actually get the Kac-Moody algebra associated with the density and density thing. So in this paper, we actually followed Korteweg and De Vries, started from this equation, systematically solved the bulk constitutive equation, and then plug it back in, and then you get this nonlinear term with this KdV equation. I will say one more thing and I will stop. Okay, so then what you can ask is that, okay, So this is KdV without any dissipation, but then in quantum Hall systems, the bulk boundary can have some dissipations in the realistic experimental system. So let's say what we have is that we want to ask this question, we want to preserve the edge U1 symmetry, the emergent edge U1 symmetry, but introduce some dissipation at the edge. That means we want to study some, if you can have charge diffusion along the edge. So what you can do is that you can add some additional term, which does not break the U1 symmetry, but also satisfies second law of thermodynamics. If you do that, the only term that you can add is this diffusion term with a complex number. And then if you do the non-weakly nonlinear limit of this, what you see is the KPZ equation basically. So without dissipation, it is KdV. With boundary dissipation, without breaking the U1 at the edge, you get actually KPZ dynamics.
KdV Burger's called.
Yeah, on noisy burgers. And so then actually there was an experimental paper in 94. Those days where experiments were published in PRB. And in that paper, what they kind of showed is that if you look at the dissipative scaling at the boundary, then you actually have a power law that is between 1 and 2. And between 1 and 2, it's 1.5. So perhaps the KPZ universality can be probed in some of the more modern setups in graphene, which is actually a unique signature of nonlinear effects on the edge of the quantum Hall system. Okay, so I will stop, but then I'm going to show that we kind of generalize this hydrodynamics for SPT phasors, which is the integer quantum Hall effect of bosons. This problem is basically where you have two component of the same theory as before, but then the Chern-Simons term is written in a way that the flux of one is pinned to the density of the other and vice versa. So that is given by this two component Chern's K matrix, which is 0, 1, 1, 0. So what we did with my student Dylan and Gustavo is that we mapped this onto the two fluid model basically. And then we want to study in two fluid model, there are more possibilities for boundary conditions now. So now if you want to study what are the non-dissipative boundary conditions that you can get, there are like various possibilities. Like you can get no slip, like before 2 copies of no slip. You can get partial slip where a slip in one component generates stress in other, and vice versa. And then you can match the velocities on one component and the stresses of the two components. So these are additional possibilities which are not there in the Laughlin state, single component Laughlin state. And all these are variationally aligned. And then now we can ask what are these possible cases. And I will just tell you the most interesting case. What it turns out is that if you look at this case 3, where you have no penetration with 2 velocities matching of the 2 layers and 2 stresses matching, under these boundary conditions, what happens is that, let's say gamma equal to 0 is the case when it's basically the old case where you have Bx, Txy equal to 0 condition. Then you have this 2 boundary modes that are connecting to the bulk bands. But as soon as you turn on gamma, then what you see is that these edge states are actually decoupled from the bulk bands. So this is what is known as the fragile surface states, in which what you are able to do is that you can actually not kill the U1 symmetry at the boundary, but because there are 2 of them present, you can rotate them in a way that they are incommensurate with the bulk U1 symmetry. So the edge states can live on their own, and hence they are not that protected as they were thought before. So this physics was completely missed in TQFT because there is no bulk matter. You only have Chern-Simons with some chiral Luttinger liquid. But once you put the bulk matter in it and see what are the boundaries at the end of it, there are more possibilities. And then in those possibilities, you see that there is a possibility that the edge states can live on its own without talking to the bulk in these SPT phases. And this is kind of also seen in some other approaches by Matt Foster and Alexander Artland, where they showed that in non-Wigner Dyson-able classes, you can get fragile states like that. So this is a hydrodynamic version of that. Okay, I will stop here.
You're not missing your train, you have those super burden questions. The next one. Well, Vladimir is setting up.
I'm not asking out of respect, but I have a question.
Yeah,
Go ahead.
I mean, can you apply some of these things like helical edge modes to TIs and things like that?
Yeah, so this is like a TI, but since we are applying hydrodynamics, I wanted an interacting system to
right,
kind of
right.
justify that, so it's
Yeah,
like a.
you have some sort of plot, you know, what Leo's thought about this, if not, I mean, you know, you can break kind of risk in the edge.
But you need some kind of a bulk matter to see that effect, basically, because
Yeah,
you
yeah,
want.
you need the bulk.
Yeah,
Oh, okay.
yeah.
Okay.
So how do you, so because we have both bulk and boundaries, our whole theory emanates from the bulk. And then the edge symmetries are emergent, not the other way around, like in Ven's theory, where the edge symmetries are kind of put by hand due to some gauge invariance requirement and the bulk has no matter. So when you have both of them, then you see that you need to have some bulk band to see that they're not touching the bulk band. So that's how you see that.
Thank you.
Yeah.
But if you look at this from the point of view of lattice,
Yes. Yeah, good.
lattice, it will think of it.
Yeah, so then that's an interesting one. This is something that we are thinking with my collaborator, Shubro. So what he has done is that they have done this SPT phases on a Kagome lattice with some different spin interaction terms. And then they can actually do some kind of a spin boundary condition which preserves U1 symmetry, but not the U1 that is associated with the bulk. So that you can have a microscopic description in the SPT case for many of these things. But then in the Laughlin case, it's a bit harder because there is no clear microscopic model there with lattice-like model there.
Vladimir Ordenhouse is next.
I don't need to plug in the phone.
I don't think so. You're good to go. Look on the screen.
Can I use the mic? No.
I think it's open. Well, if somebody wants to complain.
No,
you
it's a
can.
joke. It just seems like. Okay, thank you.
You start again.
It's fine. I'll use the, So here are my collaborators, Mishra Smolkin, Grisha who's here, postdocs Daniel Schubring and Shayo Hu, and Shai Kot, whose picture I don't have, but he's sitting back there. So to remind you, in statistical physics, the thing we normally study is the thermal state, and the reason for that is if you take a generic system with generic initial conditions in a box, and you wait until late times, for most purposes, the state you'll get at the end will look close to thermal, unless you start measuring too carefully. Nevertheless, there's a large range of contexts in which you want to study not very late times when the state is thermal, but you want to consider the system that's far from equilibrium. One can, for example, a context relevant in high energy physics is if you collide two protons in a hadron collision, then the state you get is very far from equilibrium, and then it eventually equilibrates. And so, or you could do any nonlinear system you like, just pick initial conditions and ask about times that aren't very late where it thermalizes, and ask how you would describe this. And this now seems challenging because it's unclear what you're supposed to replace the thermal state with, because there's no clear universal state. So it seems that you have to study everything on a case-by-case basis, depending on your initial conditions. Good, so that's the problem. Well, no problem. However, the last part is too pessimistic, because one expects that if you take, for instance, initial conditions in which most of the energy is localized in the IR modes, then you would expect over a range of scales and a range of times, you have a somewhat universal state in a cascade that moves from the IR to the UV. In other words, over this range of scales and range of times, you can forget about the fact that you
you actually have a closed system. So this goes under the name of pre-thermalization, or alternatively, non-thermal fixed point, or it's also the same as freely decaying turbulence. And so the way out of this problem that it seems like the only state you can get as the thermal state is to change your boundary conditions. So instead of having closed boundary conditions, we change the boundary conditions so that we allow flux to pass through at low K and at high K. So for analytic studies, it's a little difficult to say, take some initial conditions which are far from equilibrium. There's going to be a range of times and scales over which I can pretend like there's a flux traveling through. So I'm going to slightly change the problem by just putting in boundary conditions at low and high K. And doing this will allow one to obtain states that are stationary but far from equilibrium. So we'll allow analytic study of something that's not the thermal, that's perturbations of not the thermal state. And this is wave turbulence.
Sorry.
Yeah.
The dimension specific.
No.
But, you know, if you use the word turbulent, again,
Yeah. The word turbulence is not very, so the word turbulence evokes many emotions. Here.
Like, I'm talking about inverse versus direct, for instance. That's
Yeah,
what it's-
I'll discuss both. Welcome. But yeah, here wave turbulence just means take any nonlinear system and set up these conditions where you have flux at where your boundary conditions at low and high K either are absorbing and emitting flux, and then you can set up a stationary state, which is a good approximation to if you had a closed system and have some intermediate range of scales and times. That's what's meant.
It's a rotational invariance stationary state.
Not necessarily.
Not for me, yes, but
For you.
in general. The context that is that's pictorially nice to visualize is waves in the ocean. So instead of having to go through this language for closed states about justifying why this freely decaying turbulence or pre-thermalization is a good approximation, one can just look at systems like in the ocean where there is actual forcing like wind, and then it just sets up a stationary state. And so the picture on the left is waves in the ocean, and the distribution for the number of waves of some momentum K goes like a power law. And that's been known for a long time. As the wind gets stronger, then the power law, then it stops being a power law eventually, and it's believed that it becomes a different power law, which is the critical balance, which I'll discuss later. Equivalently, one could say if one looks on the picture at the left, it's a power law. It's a power law in the IR or large scales, and as you go into the UV, the interaction is relevant in this state, and then one stops knowing what it is because it stops being weakly coupled. And so what we're going to try to do is find analytic contexts in which we can have a flow from an occupation number n of k that's a power law k to the minus gamma in the UV, and the different power k to the minus gamma tilde in the IR, which is like flowing between two critical points. But here it's not literally critical points, it's just scale invariant behavior. So that's going to be the goal, to find contexts in which we can analytically do this. This won't be the actual ocean because obviously that's too hard, but other contexts. So we're going to do two things. The first is I'll remind you of the kinetic equation for waves. It's the analog of the Boltzmann equation, and how from that one can see that there's weak wave turbulence. And then we're going to derive kinetic equations in contexts that are not just weakly coupled. So to go beyond weak coupling, I'll take a theory that has large n, a large number of fields, and then we can derive a kinetic equation that is valid at all couplings, like one normally does with large n. So that will be part two. Part three, I'll simplify the problem further, and in addition to large n, so a theory with a large number of fields, I'll take very special interactions. I'll take interactions that are strongly local in momentum space. And this will simplify the kinetic equation even further, and then it will be easy to find solutions of this kinetic equation And then I can find solutions which go from one power law in the UV to a different power law in the IR. And I know N of K, the occupation number for all modes. The fourth part will be the epsilon expansion. So this will be an analog of the epsilon expansion. So I'll work exclusively at weak coupling, and within weak coupling, I'm going to tune the dispersion relation and the scaling of the interaction so that the interaction in this state, in this turbulent state, in this far from equilibrium state, is close to marginal, like we do in the epsilon expansion. And then one can flow from one scaling in the UV to a different scaling in the IR, where the scaling exponent differs by an amount of order epsilon. So it's again like the Wilson-Fishner fixed point, but heuristic. Good. So this is the kinetic equation for waves. So I wrote a general Hamiltonian with some dispersion relation omega of p. A of p is a complex field. It's like the creation operator in the harmonic oscillator. And lambda is some interaction that depends on four momenta if you want. And so this is the kinetic equation. So it goes like lambda squared. It has some powers of n and conservation of frequency and conservation of momentum. It's similar to the Boltzmann equation, but it's for waves instead of particles. Yes?
So how many constants of motion do you have?
Two, energy and particle number. And so in this case, there can be both a direct and there's both a direct and an inverse cascade. Yes. Huh? Yeah, this one. Yeah, momentum is concerned. Yeah, it's so like with the Boltzmann equation, it's obvious to see that the thermal solution is stationary. So the thermal solution in this case is Rayleigh-Jeans, which is just the high temperature limit of the Bose-Einstein distribution. I know it's a little odd getting classical results from quantum mechanics, but it's easier. And so if you plug in n as t over omega, here you get a omega 1 plus omega 2 minus omega 3 minus omega 4, which is canceled by the delta function. So perhaps I should have mentioned this equation, like the Boltzmann equation, is sort of obvious. You're asking for the occupation number of mode 1. So it scatters off mode 2 and makes mode 3 and mode 4. So that decreases the occupation number. And then the inverse process, the time reverse process can happen, and that's the term with the opposite sign. And so in thermal equilibrium, these two cancel. Good. The part that I found surprising when I learned about this is that there's another stationary solution that's not thermal equilibrium, which Zakharov found in the 60s. So so to establish notation, take the interaction to be scale invariant with some scaling exponent beta. And what Zakharov showed is that if you plug in nk as k to the minus gamma, where gamma is b plus 2/3 beta, b is the spatial dimension. If you plug that into here, you get 0 on the right-hand side. And that's also a stationary solution. And this state is far from equilibrium because k to the minus gamma looks nothing like the thermal solution, which was 1 over omega. Good. So you might ask how this is possible, because the thing one always learns in statistical mechanics is the only late time stationary state is the thermal state. That's why we study it. The reason it's possible is because this is not actually a solution at k equals 0. So there's a problem at k equals 0, which is consistent with the fact that to actually physically realize this as a solution, we need to put boundary conditions at k equals 0 and infinity, have the flux flow in. Okay, and the last point to emphasize is that all of this is at weak coupling. So we're doing far from equilibrium physics, but at weak coupling, because this equation is only valid at weak coupling. And I'll describe how one derives. Just like the Boltzmann equation is only valid if the density is small, the wave kinetic equation is only valid if the coupling is weak. So, good questions. So one can ask how the kinetic equation is derived. And in principle, it's straightforward. So we're going to assume that our state is close to Gaussian, e to the minus ak squared over n of k. So if you took n of k to be t over omega k, this would be the thermal state. And then pretend we're doing quantum mechanics, if that's easier. since we need to compute in this state, we do quantum field theory on the Keldysh contour, and then you can follow the standard procedure of deriving kinetic equations in quantum mechanics, of writing down the Schwinger-Dyson equations on the Keldysh contour and so forth, although those are faster methods. But in principle, it's straightforward. We're just computing correlation functions in a state that's this Gaussian state, close to this Gaussian state, but it's not the thermal state, but it's still Gaussian.
So what do we do if k equals 0 to stabilize this solution?
Nothing. I just don't look at K.
No, you put that function of k at the right-hand side.
Oh, you mean in the kinetic equation previously? Yeah, you just have, you enforce that the flux, so you know the flux at all the other cases, so you just place that flux there.
Inject something in k equals 0?
Or absorb, depending on which way. Like to imitate dissipation in the real thing.
Two solutions are equivalent,
Which two solutions?
positive and negative delta.
Well,
What's
you need,
the amplitude of the delta?
well, you have forcing on one side and dissipation on the other side. Okay, and so if you do this procedure, you can derive the kinetic equation that I showed previously, and you can also derive higher order corrections to the kinetic equation, which are perturbative in lambda. Yeah.
You say you derive from where? What's your equation number one? Like, what are you actually studying? Is it Bossis, comparisons? What is this thing?
So I take this Hamiltonian.
Oh, that's your starting.
Yeah, so it's a general Hamiltonian with a choroidic interaction, and then I derive, this is the kinetic equation at order lambda squared, and then we can compute terms order lambda cubed, order lambda to the fourth, and so on. It just consists of perturbatively computing correlation functions on the Keldysh contour in this state.
So the Hamiltonian number one describes interacting bosons, correct?
Yes.
So and they don't, so you're not in the condensate, you're in the normal classical state.
Yeah, you can do this in, you can quantize the Hamiltonian if you like.
It's not that.
You can do quantum or classical if you like, you can do quantum. But then to see the nk is k to the minus gamma, the cascade state, you're going to have to take large occupation numbers to get it to be scale invariant, so it's your choice. Yes?
The Bose-Einstein condensate, which is essentially classical field phenomenon, will probably bilinearize your Hamiltonian and just bilinearize Hamiltonian, take into account non-bilinear terms and kind of repeat the whole procedure.
Yeah, but for now, forget about condensates. Let's not have condensates. Just think of this as the Hamiltonian for surface gravity waves. Lambda is some complicated function.
Question whether the system is both condensed or not.
No Bose-Einstein condensation.
So to go from the first line to the second line.
Yes.
You use some kind of resonance approximation, or what do you?
To go from the first line to the second line, really just put it on the Keldysh. Just the only approximation is that you're weak coupling and that the state is close to Gaussian. That's really the only approximation.
The first line is Hamiltonian.
Yeah.
And the second line is already the
kinetic equation.
So what do you get from it?
But the non-stationary solution is not close to Gauss.
The stationary solution. So
non-stationary.
What is this?
That's out of it.
Huh? That's not on my computer.
That isn't. That's an Apple thing.
Quit. Press the quit. No, it's not here.
It's not here?
Oh,
Maybe it is. No. Sorry, I apologize.
So the state is close to Gaussian, but it's not a thermal state. So this is Gaussian, but NK is whatever you want.
And it's not T over omega.
Correct. Yes?
So one detail which you probably did mention, people are asking, you assume that your occupation numbers are large.
He
Not
said
just
that.
Yes, that's right.
That's important because it's probably was the question, whether it's a condensate, it's not a condensate, but it's a classical.
Well, to derive the kinetic equation, so I can derive the kinetic equations in the quantum case with small or large occupation numbers. To get the wave turbulence, you'll take them large.
Neglect spontaneous scattering against the background of stimulated. You don't have n+1, and then you say, I will.
Okay, so this equation, you're correct. This is already the classical equation where I dropped the one, but we can write down the quantum equation and so on.
Right, but the question was
Yeah.
answering. So
Yes.
it's ones are neglected, so
Yeah, in this equation, yeah, the ones
It's a degenerate.
yeah, this equation is for the classical case, but
Okay,
No spontaneous process.
yes,
Can you just go back, next slide? I just wanted to ask, no, one more?
Yes.
Yeah, so this P of A, how is that put in, you say close to that solution,
yes,
you expand around that solution?
yes.
Or-
So I take that as like the initial conditions.
That's an initial condition.
Yeah, you could say that's the initial condition. Yeah,
Okay. And there's no space, right?
there's space, that's why I have K. It's just some, I just wrote the, it's, I'm.
But there's no space in the sense of like, there's no convective terms in your,
That's right, because one is assuming homogeneity. That's why.
That's what I mean,
But
there's
you,
no-
yeah, but you could add it if you wanted to, but. Okay, let me proceed. So, so in these papers with Misha, we went beyond leading order in the kinetic equation, which I'll describe later. But the thing that's more interesting is to go to strong coupling. So we'd like a kinetic equation that's valid, not just a weak coupling, but a strong coupling. So we want to study far from equilibrium, it's strong coupling. So to do strong coupling, I'll change the theory and make the field a vector and then do large N. So a physical case would be spins and then take them to be in a high dimension. In particular, the simplest case would be the large N nonlinear Schrodinger equation. So take the interaction to just be a constant. So in this case, we can write down, and this was written earlier by the Heidelberg group, a kinetic equation, which is shown here in the bottom. This is a kinetic equation valid at large N, but for any coupling. And roughly, like as usual for large N, since I said that we get the kinetic equation by just computing correlation functions on the Keldysh contour in the state. So it's sort of obvious that if you know how to solve large N in the vacuum, you can do it here, though it's slightly more challenging. So we sum bubble diagrams. Roughly, each bubble diagram gives a loop factor, which is whatever in here. N is the occupation number. It appears inside the loop because our propagator is state dependent, because everything is state dependent here. And so you get a geometric sum of 1 plus L squared plus L to the third for the number of loops, which turn into 1 minus L squared is a numerator. So the large N kinetic equation is like the tree level kinetic equation, all that stuff, but with this factor of 1 minus L squared. It would seem that it should be possible to likewise write down a large N kinetic equation for the Boltzmann case, but I've never seen that done. Okay, and so now we can study strong coupling. So Grisha is going to discuss this equation. This equation is somewhat difficult to find stationary solutions of because there's an integral here, so it's even harder than the tree level kinetic equation. So I'm going to simplify further. As I mentioned, so again, the goal is to first obtain the kinetic equation, which I did at large N. The second goal is to find stationary solutions of the kinetic equation, which was somewhat difficult for me for nonlinear Schrodinger. So I'll simplify further by taking an interaction, lambda, that's strongly peaked around nearly equal momenta. And the way this works for the standard kinetic equation is that it turns the kinetic equation, which is an integral equation, into a differential equation. For reasons that are somewhat obvious, it's just because if you take the interaction to be localized around momenta that are nearly equal, this gets rid of the integral. So naively, it should give 0 because there's no momentum to sum over. But since there are differences here, which would give 0, you have to Taylor expand, and that's why you end up with some derivatives. So the standard kinetic equation becomes a differential equation, which looks like a diffusion equation, but a somewhat fancier diffusion equation. Yes?
What happens when this L minus is close to 1?
Ah, excellent question. Grisha will address that. That's where you get critical balance.
I'll talk about it.
That's Grisha's stuff.
So how do you get the second derivative, the fourth derivative?
Excellent. That's why. So in this paper, it's not explained very well. So this derivative, the d squared, the omega squared is obvious. It's from this term,
right? Because
they're almost 0. This one comes from these Kronecker delta functions because in the previous way I wrote the kinetic equation, I didn't have a sum over P1. It was just this P1 was the same as here, but you can symmetrize it and write these Kronecker deltas in the symmetrized form, and then if you Taylor expand the Kronecker deltas, you get this derivative.
Because constellations.
I see, so naively, that's just zero.
Yeah, exactly.
So then-
Yeah, and then you tailor. Okay, so the thing we did with Daniel is we did strongly local interactions and large N, the kinetic equation. So again, we sum bubble diagrams. Each bubble diagram gives this factor. We do the sum that appears in the denominator. So this is analogous to the equation I showed previously for large N, but with a constant interaction. Now it's with the strongly local. And again, the point is the kinetic equation is now a differential equation. Good. So to summarize, we took a theory in which there is a large number of fields and in which the interaction is strongly local in momentum space, and we obtained a kinetic equation that's a differential equation, and now we can look for solutions. So now I'm going to look for stationary solutions. Questions?
What physical system are you trying to describe?
Here?
Like, I don't understand what this thing. Like, let's go a name or something. Like, what is this thing? The strongly interacting water. Like Hamiltonian equals to what?
Oh,
It's boson.
yeah. Good. Hamiltonian is,
Say Hamiltonian.
this is Hamiltonian, but put a dot product, make A a vector and put a dot product between this. Actually, I wrote here. So this Hamiltonian, and take lambda that's strongly localized around P1 is almost P2, is close to P3, close to P4.
And it does break translation.
No, it's fine. Yeah, you can lambda can be anything you want as long as you conserve momentum. So I'm
So
still
the motivation for considering this Hamiltonian.
so that I can
does this
solve.
thing actually exist, or just like
No. It's just to be. It's just like large N. It's just a trick to be able to solve analysis.
Actually, I think it does exist, but let's discuss.
I think in the literature for surface gravity waves, Hasselmann used this as an approximation for actual surface gravity waves, and it worked sort of well. But I'm not using it as an approximation. I just want to model I can solve. Which, given my background in high energy, this is a very mild direction in terms of I'm physicalness. I'm still at 3 dimensions. There's no supersymmetry. I think
Energy is called engineering.
It's a dense quark gluon plasma.
Sorry?
Dense quark gluon plasma.
What about it?
This is the Hamiltonian.
With strongly local interaction? In momentum space? No.
Yes.
Okay, you'll tell me after that. So now I look for stationary solutions. So this is trivial. I set this equal to a constant. And there are 3 stationary solutions. The first one is the Kolmogorov-Zakharov solution, the k to the minus d minus 2/3 beta power that I wrote before. And then there are 2 more, which I'm out of time. I won't discuss them in detail, but it's just k to different powers. Because, there's only, so omega scales like k to the alpha, the dispersion, lambda, the interaction scales like k to the beta. The powers have to be some combination of alpha, beta, and d. And if we solve on Mathematica for stationary solutions, it flows from one exponent to the other. So we have the stationary solution for all k. So if we could do this for surface gravity waves and not this somewhat contrived model, we would have solved the problem I posed in the beginning.
And why this bifurcation?
I don't have much time, so let me ignore it. Just focus on this. Let me mention one last thing. If we just work at weak coupling and want to ask how to flow from one scaling in the UV to a different scaling in the IR, we'll do as analogous to Wilson-Fisher. So I'll pick a special dispersion relation in which the scaling of the interaction goes like p to the beta, scaling of omega k, the dispersion goes like k to the alpha. I'm going to work with beta close to 3 alpha, which has the effect of making the interaction close to marginal. So the dimension of the interaction is state dependent. Normally the dimension of the interaction is just something. But here it's state dependent because the state explicitly enters into our propagators. And so if I take beta to be close to 3 alpha, but differing by epsilon, I'm making the interaction slightly relevant or slightly irrelevant. And so this gives a large range of scales over which I have perturbative control, just like in the epsilon expansion.
And so we can compute n of k both in the UV and in the IR, and the scaling exponent differs by an amount that's of order epsilon. There's many additional details to this, which I won't describe. Okay, so that concludes my talk. So to summarize, we want to study states that are far from equilibrium. One can do this even for theories that weak coupling, perturbatively in the coupling, and we can also do this at strong coupling in large N theories, and obtain solutions that where there's one scaling, which is Sakharov scaling in the UV-IR flowing to a different scaling in the other direction. And so Grisha is going to now discuss this for, well, I'll discuss. Yeah, okay, so I'm done.
Now, I'll try to just make it another continuation of the previous talk. So what I push here to move, push here, and the pointer. No, it's what we want. What here? Yeah. Okay, good. Thanks.
You probably want presentation.
Yeah, making presentation.
I don't know how. I don't use PowerPoint. So I don't know.
Or F5 or full slide. I mean, if you go to view, under view.
Yeah, here is a slideshow from beginning, no?
Oh, I see. Play from start.
Play
from start. Yeah.
Thanks. Okay, good. So I'll try to be short because we're well past all the time. So again, the problem is kind of very generally. So I wanna somehow go from weak turbulence, which Zakharov, Hasselmann, and all this they described more or less completely. This is just a solution of a kinetic equation, which very well describe reality, measurement, satellite measurement of a spectrum of waves. We also actually have data for this state, which show different spectrum. Nobody ever derived this spectrum from any consistent theory, the solution of any equation, but there is a very good argument made by Phillips even long ago, Hasselmann and Zakharov, is that this main thing which dominates the spectrum, at least is large K, are just these cusps over here, so something like this. And again, if you just Fourier transform a cusp, you get 1 over K for the surface, and when you make a square, make it 1 over K squared. So we know spectra here, we know spectra here. We have equation for which this spectrum is a solution, that's Zakharov's PhD, and we don't have any equation for which this is a solution. In a sense, this is more or less kind of basic geophysical motivation for this work. But on the way, we also discuss some other system, and particularly Gross-Petaevsky and linear Schrödinger, where is the same situation. You have a weakly interacting weak coupling state, and we have strong coupling state, and we want to somehow get something to describe them together. And again, this is what
spectrum. Sorry.
By spectrum, I mean in a moment will be clear. Occupation numbers.
Wave dispersion.
No. By spectrum, I mean the mean value, this nk, which is the mean value of ak modulo squared, and my ak will be what you call boson field. It's just a classical limit of a boson field. This is just amplitude of a surface taken Fourier transform. So this ak for water waves is just a Fourier transform of a surface of the perturbed C. Okay. So by spectrum, I mean dependence of its on k.
What's the dispersion? What's the mean guard?
For gravity waves on the water, it will be square root of p. For Gross-Petaevsky, this would be p squared. For capillary waves, they will be p3/2. That's what Vladimir called alpha. So I will be at this moment treating this is just as something. But if first of all, let me just maybe say a few words. So what I'm looking for, I'm essentially asking the following question. So if I have this Hamiltonian, and whatever is omega and whatever is lambda, I mean, I can always, I mean, for me, I'm not doing effective field theory. I know exactly what is omega for gravity waves. It's the square root of g times k. I know exactly what is lambda. I mean, Zakharov computed it long ago. So I'm not asking how to relate something, I mean, effectively. I'm asking what will be omega if my wave with a vector k propagates in a stormy sea. So what would be the contribution of multi-wave interaction into a given frequency? At the same token, I will be asking what will be the contribution of multiple interactions into my interaction of four waves. And in a sense that we not only can compute this, for example, lambda, but we really did experiments, so you can take two wave makers, make K1, K2, measure all K3, K4, and just measure this quantity. If there are no other waves present. Now we want to renormalize it. And what we learn from field theory is that, for example, with lambda, there are two ways to renormalize lambda, and one is what is called screening, and another is what is called anti-screening or enhancement or confinement. There are many names for it. So what I want to focus on this work is more on the qualitative aspects of higher nonlinearity, and namely that what actually is an effect of multiple multi-wave interaction on the basic interaction. But technically that would be correction, yeah.
Yeah, just want to ask, so I can see how just the bosonic field describing the height fluctuation, but where's the velocity here? Fluid velocity?
There is no velocity here, just forget, no velocity. There are modes.
Huh?
There are modes, okay? So this AK, for example, there are spin waves, okay? And I put it in a strong magnetic field oscillating with some frequency. So I'll get parametric resonance, so I exact spin waves. This I call turbulence, okay? This will be spin wave turbulence.
But the velocity of the.
No velocity.
No, you can say no velocity, can you just answer, but, I'm saying, is it just the model? Or it has no relation to a fluid?
Yeah, what
Or
are
there's some-
spin waves? What are the velocity of a spin wave? There is no velocity. There is a speed of wave here, omega is ck. Turbulence is not about fluids. Turbulence for us is a state of highly non-equilibrium state of matter. In this matter, there could be excitation. Some excitations has a hydrodynamic nature.
Sure, I'm saying
And
as a
some
model, I understand, there's some interest in studying turbulence in this model. Does it have any relation to a fluid where there's a velocity field and there's maybe a height field?
It's terminology. For me, turbulence is a state of any system with many degrees of freedom deviated from equilibrium. There is nothing fluid mechanical about it. That's why I said about spin waves. Think about it as spin
Sure.
waves.
No, I accept that.
Or plasma waves.
But so,
But
But
if
if it
you are
was real
interested
fluid-
in a particular case of highly non-equilibrium state of matter, which is called Kolmogorov turbulence, namely state of incompressible fluid, etc., there will be at the end one slide pointing some analogies. But I'm not a fluid mechanicist at this moment of my life. At this moment of my life, I'm a statistical
but if
physicist.
this was a real fluid, you would have another equation for D coupled to the A's.
Or if it would be a real fluid, for example, and you would like to describe it in this form,
Yeah.
then your
that's it.
Hamiltonian would be such that omega would be 0 and lambda would be k in the first power. So you would have also this problem, but with omega equal to 0. If you write fluid mechanics and Clebsch variables. So this is a particular case of this Hamiltonian. Okay. If you like to do fluid mechanics of gravity waves, so this is also fluid mechanics. Then your omega will be square root of p. Okay.
Okay.
But at the moment, I want to take this Hamiltonian and give me this equation. Those equations are nonlinear. Okay, I will consider it in the limit of field coupling, and I'll try to get beyond this limit. Okay, it's a very general physical problem. So
Okay.
imagine you never heard about Kolmogorov. So you first time heard the turbulence
just to-
from Vladimir Khabarovich.
But just, if these were classical, if these are compressible classical fluids, then I know what A and A dagger are. I know the density is. A
It would be
dagger,
sound
right?
waves, yeah.
So if I look, I'm thinking about like physical correspondence of what A, like how do I think of A and A daggers in different examples? Or for gravity, what is it the height of the fluid?
Yeah, I already said it, let me
Right.
repeat it. So for gravity waves, those are Fourier transform of a fluid surface. So you take a scalar variable, function of x and
No,
y,
I got it.
Fourier
You
transform it, and that's your AK. That's it. And we derive this figure.
Yeah, so the physics is in the A's.
Yeah, so this is just,
No, I wanted
this
to-
is just a classical normal amplitude. Yeah. So in a sense, what I'm just look at it, and I mean, you have a set of oscillators. Now you have a set of waves. Now these waves start interacting. That's a Hamiltonian, which is the most general nonlinear Hamiltonian. Again, as I said, if you assume that those waves are close to a set of weakly correlated waves with regard to this, you can do perturbation theory. So essentially, most of this talk will be computing this quantity which means if you take this equation, multiply it by AK complex integrated, you have what is called kinetic equation. The derivative of your equation number will be just, this is an exact equation, it's your force order formula. So everything will be about computing this force order formula, okay, from now on. And of course, you can do it perturbatively, and Vladimir does it its own way. I do it the way I learned it 40 years ago with, this wild diagram technique. It doesn't matter. So for the first order, you get what we already seen is the kinetic equation, which means that it's just something. What is important, it has lambda squared. Namely, at this point, weakly interaction waves don't care which sign of interaction. Attraction or repulsion, positive lambda, negative lambda, you don't care. Turbulence in the weak coupling limit doesn't know about sign of lambda. I will be interested in the sign of lambda, and now I'll be going and looking at the correction and see how all the terms. And again, as you already seen in the Vladstock, Zakharov got this solution, etc. It's to show that essentially this kinetic equation, you can say that this is just this three-level diagram for your 4-point moment. You can check its convergence, then you can compute the first correction in lambda, which is just a correction to the frequency. It is not that important, and particularly for energy cascade, is just unimportant. So here is one loop correction. That's interesting things start already here. So what will is just for any lambda, any omega, a first order correction to the kinetic, to this force order cumulant. They look like this. This is what you had before with this factor. So you have lambda, this factor, omega, and two extra n's over here. Again, this is kind of you added this extra loop. So now it's a very natural question to ask. Now you have a lambda cube. It's apparent you can have a sign. The lambda squared is always positive, but now you
So
start.
The thing you showed on the previous slide, that was the first diagram? Was it
Yes,
always-
this is added to it. In a moment, it will be clear. So you will write, well, this is something that adds next term to the previous term. Okay? So you had this three contribution from kinetic equation, and then you add to this thing. That's just addition. It's a one loop addition to the force cumulant. You plug it into the integral, and you get correction to kinetic equation. And now we'll start to asking, and you see there are two kinds, one with errors in the same direction, another with other direction. And here is Natalia Vladimirovna sitting over here. This is computation of this term for gravity wave, for true lambda taken is with all bells and whistles. And this is not to give you any analysis, it's just to scare you, to show how damn complicated it is. What you have here is just, you have interaction of four waves, so you fixed one, so you have three left. Your delta, your conservation of momentum fixes another, so you have two left. So you have one fixed, and then you plot it as a function of x and y component of one vector. So in a sense, this is the part, this is a projection of lambda dependence. So what you have in an upper row is a bare vertex as lambda itself. You see that it changes sign. The black lines is where it changes sign and its magnitude in a complicated ways, and correction to it change sign in even more complicated. Which means at the moment you really try to describe any real physical system like waves, and we'll doing it and we'll finish it at some point. Well, I'm just showing it how damn complicated it is, because it's not something where you can simply say, okay, well, this is attraction. For some directions, waves are attracting each other. For some directions, they are repelling each other, and corrections are also very strongly dependent on the geometry of wave. And this mess we are going to analyze, but first I'll show you simplest. Yes.
This is first order loop corrections.
This is the first one loop correction.
Okay.
So this is bare, and overall it's a one loop correction
How
to
many loops do you like? What is the furthest figure given?
infinite number of loops if we consider large n limit. So, but let me get it.
So
So-
it's controlled by 1 over n? Or
Wait a second. So far that was just honest to God, straightforward calculation.
perturbation theory you use?
Just one loop correction computed for equation of gravity waves on the surface of the water. No approximation. Now, what I'm showing you, when lambda is complicated, correction to lambda even more complicated.
What I'll show you is simplest system, which is also very physically interesting. It describes any, spectral narrow packet, cold atoms, many other things. So this is just what we call nonlinear Schrodinger. So now my omega is just k squared, and my lambda is just a constant. Very simple. Nice. Now, again, we do this one loop correction, but now we can compute it analytically. Again, it's a functional of your spectrum. So you really can do it. You can do it for example, for thermal equilibrium and compute correction to your interaction, which is kind of straightforward. Or you can plug here Zakharov solution, and you can compute this as a for Zakharov solution. So you do it, and again you discover that even in this simple case, what you find out that here are the two terms which change sign. Here is one term change sign, another doesn't change sign. Again, you find out the following things: that depending on the angle between wave vectors, your interaction changes sign. And somehow it took some time to understood a kind of trivial physics behind it. In a sense, this changing angle is the following thing. So it's how this frequency, combined frequency of this is related to the sum of frequencies of what it. You can think about this as an intermediate state, which is 1 and 2 create this intermediate state, and it's a force with some frequencies, they all are waves, which drives this thing. And then looking at our formula, you realize what you essentially see is the following things. If you have an oscillator, now I mean this 3 and 4, and the force which drives has a frequency which is less than its resonant frequency, that they are in phase. If you have a force which drives an oscillator, it's just a simple mechanical analogy from our first undergrad year. If you have force which has a frequency which is higher than the requisite frequency of my oscillator, I have them in antiphase. So essentially what we observed here is precisely the thing, that one loop correction give you a contribution to this depending on whether the intermediate state has a frequency higher or lower. Then you ask, okay, but is there any way to say what would be the integral effect of this renormalization of the vertex? And then we realize that to look at it, we really need to ask about how it influences the overall interaction between waves and overall interaction of the wave. Its main effect is carrying the flux. As Vladimir said, what we describe are states in which we have at one end of K space pumping, and another is dumping. In this M and Q, our solution, which we already substituted, provides the cascade. So now we can ask, what is this correction if I integrate over all possible interactions between waves, whether it enhances the flux or suppresses. Because if it enhances the flux, then the result of it will be that it would lower occupation number. You would real less occupation number, less turbulence to carry the same flux. Right? If we enhance the flux, then you suppress wave numbers. If you suppress the flux, you enhance wave number. It's a simple logic. So you compute this integral, which is again straightforward. For nonlinear Schrodinger, it's straightforward thing. And for gravity wave, we did not do it even numerically yet. And you find out very interesting things for Schrodinger, that the overall sign is minus lambda, which essentially tells you that attraction is enhanced, repulsion is suppressed. Positive lambda give you negative delta lambda. And that's an answer. Again, in terms of carrying cascade. That's very simple statement. And also, again, this we have not proved. I just checked it in one particular degenerate case. That if you, this is a case where omega is k squared, right? So for omega k squared, omega 2 prime is just 2. It's a positive number. But for gravity waves, omega is square root of k. And second derivative of omega would be negative. So what I believe, and this is a hypothesis not proved for any omega, is that in the general case, instead of this, you get this. And this is something which must ring a bell for each one of you, because this is something which you already seen in Bogolyubov spectrum. So if now, and this is something not about turbulence, it's about just a condensate or monochromatic wave. So if you have a wave with a wave number k and its amplitude is 8, and you impose on it a very long perturbation with a wave with number q, which is much less than k. And you ask what would be the omega of such perturbation. So you have a very spectrally narrow packet, you make an envelope with a very long and slow modulation, then Bogoliubov computed it that this would be this thing. And now you find out this lambda omega 2 prime factor standing over here. And of course, for, okay, Bogoliubov did not write it this way because what's standing for here, what omega or epsilon energy was p squared, this was just a factor, but Lighthill several years later realized that the moment if you treat other waves, this could be negative, right? For example, gravity waves, it's negative. And then you would have an instability. It's called modulation instability. That's what we all can observe on a beach when we have every 10th wave stronger than the previous 9. That's the result of this modulation instability. So what now we found, and it's called Lighthill criterion, lambda omega 2 prime less than 0. Physics of it is, I believe, is very transparent. And there are like 5 ways to explain because it's a very basic physical phenomenon. You can look at omega of a given, let's say, wave as a function of k and as a function of amplitude. Because as you increase the amplitude, you renormalize the frequency. So lambda is essentially a second derivative of omega with respect to wave amplitude. And omega 2 prime is a second derivative of omega with respect to k. What Lighthill tells us is that if your omega as a function of k and amplitude, and you are at k close to 0 and amplitude close to 0, your long wave limit, weakly nonlinear. If it's concave or convex, your wave is stable. If it's a saddle, your wave is unstable. That's essentially the message. So if you have a saddle in omega dependence on k, modulation and stability, and of course another way of it is a spectral, because this wave you can consider that it interacts with 2 sidebands, and these 2 sidebands provide you dispersion, which is governed by omega 2 prime, but it's also this lambda. So these 2 sidebands must be in the resonance with the band. And for this, you need a saddle. You need in one direction goes up, another direction goes down. What I found, yes.
Can you spot any difference in the 2 cases? For instance, if I have a wave that's about to break and a wave that it's actually will become a solid time.
Well, this is a statement about spectrally narrow thing. And soliton is not a spectrally narrow thing, right? So this soliton is a highly, and I'll talk a little bit how soliton can appear in this picture. But this is just what Lighthill and Bogoliubov did was just quasi-monochromatic. What we found with Vladimir, to much our surprise, that in our case, the same criterion in some kind of integral sense works for turbulence. So in a sense, what we're trying to do, we try to do first simple classification of universality classes of turbulence. And one of them is essentially we're trying to, see what would be like electrodynamics, namely multi-particle effects would suppress the interaction between 2, or it will be more like chromodynamics, in which these collective effects would enhance the interaction. So what we find out that this criterion, which I would call by our names, but most likely it will be also called turbulent Lighthill criterion, unfortunately or fortunately, it has a similar nature, lambda omega 2 prime. I find it extremely beautiful. Yes.
Something while you have the page here. So when you're doing perturbations here, you're changing lambda, looking for directions to lambda.
Yes.
Right? And is it the same lambda as in the first line and the third line?
What do you mean? That I'm looking. This lambda is bare lambda, is what comes from my equation.
So you're looking for corrections to lambda.
I'm looking for one thing. I'm renormalizing kinetic equation. So when I'm speaking about renormalization of lambda, it's kind of my way of saying that I'm looking for what is the real value of a 4-point cumulant, which determines my right-hand side.
So when you're renormalizing the equation, you're renormalizing lambda.
Yes.
Right. And the same lambda as the first line.
Yes. Yes, absolutely.
Why,
So what?
Why don't you do anything to collective mode dispersion?
Yes, of course I need to do. What I've shown you in the kind of one loop approximation, that first you renormalize omega, and omega gets shifted by nonlinear shift. And then you do one loop correction to lambda. That was all kosher, and you can include omega into this delta function of omega. You can write here a renormalized omega. This you definitely need to do, and we do it. Now, when you try to go beyond one loop, all hell breaks loose. So you have correction to omega and correction to lambda and all the things which you. So what we now are going to show is what Vladimir already mentioned. I want to treat a vector model. And what is beautiful about this vector model, that this omega renormalization is trivial. It just adds a constant to omegas, and constants drop out of this data. So in this large N vector model, I won't need to bother with frequency renormalization. In a real nonlinear Schrödinger equation, of course I need, and I don't know how to do it.
Yes, so the reason I ask is that I want to ask the same question as Leo asked you, maybe in a more
Where is fluid?
slightly different way. In turbulence, as far as I remember, fluid has a lot of energy. And the energy, I think, in your Hamiltonian is the kinetic energy. So it's not in lambda, it's in the amplitudes of the waves and in collective mode destruction.
Yeah, in a sense, when I yeah, it's
that with what you're.
it's essentially the same. When I'm saying that I'm considering a limit of small nonlinearity, small lambda, it's the same as I'm saying that I'm considering a small psi. Psi is again the amplitude of my waves on the surface, right? So what I'm actually doing, I'm doing a limit of small psi. But technically, I can say that I'm considering a limit of lambda very small, and I'm trying to renormalize, right? And if we're talking about waves on the water.
So where's kinetic energy?
Oh yeah, kinetic energy, of course, if you ask that I derive this Hamiltonian, so what is exactly this energy? It has two parts. One of it is not rho, eta. Eta is a surface elevation. So you take this elevation, multiply it by v squared, which is velocity, and you also take potential energy, which is eta squared times gravity. And then you expand it into normal canonical variables, and you get this Hamiltonian. So both your kinetic and potential contribute this term and contribute this. Okay, so that's how it gets done. And again, you can open our book with Zaharov, but there is all the derivation. Of course, it's kinetic plus potential energy. There's nothing else here. Okay, so now what I want to spend maybe last 5 minutes, because it's really is that this is the question that Vladimir already have shown you. What I want to just make you look in here. So when you consider this vector model and you sum all the bubble diagrams, what you find out is that it essentially gives you a very simple statement. Instead of lambda squared, you have this renormalization. Of course, it's now two coupled nonlinear integral equation, because your L, which is over here, is itself depends on n, but still, I mean, it's close. Okay, and now you will find out, and somebody already asked, what happens and how it actually depends on whether this you can get a zero in this denominator, right? And then you realize that L is generally a complex number. This is a complex value. It's actually a function of wave movement. And then what you immediately start thinking that it could be that this real part is always negative. So you can always have here something which is larger than unity. And so what actually happens is that when you increase the amplitude of your spectrum, then you would be suppressing your interaction because this is a denominator. Okay, and as we already discussed, this is what you will get in the defocusing media when you have a repulsion between waves, and then you go and consider it, and I won't go much into the details, but what really is important is that lambda, bare lambda, disappears from this limit. So if you look at this renormalization and you say that my L is negative and L is itself proportional to lambda, and you assume that your L is much larger than unity, bare coupling disappears. Whatever turbulence you would have would be independent of your initial bare interaction. That's a prediction. It's made out not of a real Hamiltonian, but in a Hamiltonian considered as a large vector model. But this is something which is for people now to check. And now the last thing that and I skip unfortunately analogy with Kolmogorov turbulence, you may ask me about it. What will happen in the opposite case of focusing case? We know what physically happens. There happens wave collapses. So you have many waves which actually interact sometimes so strongly that they create collapses. Or if you are describing light in nonlinear dielectrics, they just self-focus and blow up a crystal or just melt it locally. It's very, very strong physical effect. So we're now talking about focusing medium, which means that the real part of this L is positive. But then you say, okay, no, you still not necessarily would have here a pole because you have an imaginary part of the pole. Then you ask if you can have a solution in which the imaginary part, and that I guess, Leo, you ask what happens when you approach the pole, that you find out that if you look for this quantity being equal to unity, that this quantity in 2 dimensions disappears. Which means that now you can say that in the first approximation, my solution must be given by the condition that L is equal to unity, but L is something which expressed in terms of my wave amplitude and my interaction, it does not depend on the flux which it carries. It's a very interesting turbulence in this case, which value would not depend on how much you steer. Whatever is your wind doing over there is only important by setting a boundary wave number where this universal spectrum starts. And of course, the scaling is what Phillips suggested 70 years ago, which means that this is, again, not the equation for water waves because we use a high vector model, but at least this equation has a solution, which is the Phillips. And in particularly for nonlinear Schrödinger equation, and that's the last thing that I want to show, and this again data of Vladimirova. So what we see here essentially is a weak turbulence. And this is the focusing case, and that's a defocusing case. So you see that in the weak turbulence, they more or less go parallel to each other because in weak turbulence does not know which sign is your lambda. Traction, repulsion does not matter. And what you find out that in the focusing case, your spectrum getting less steep, which tells you that you enhance your interaction, so you need less turbulence to carry this. Here is a pumping over here. You need less turbulence to carry the same flux. In a defocusing case, you go up, and this is loosely correspond to our prediction. So this is very sensitive to whatever you have condensate or not. And here we assume that we don't have any condensated low K. That's not in a Schrödinger. And this is this universal Phillips type spectrum for which nonlinearity is frozen at a given constant number. So in this is for real nonlinear Schrödinger equation, not for some vector model. So I want to finish here and say that first of all, we did simple, trivial, honest to God one loop correction, which of course people wrote many, many times. What we did, we just plugged the Zakharov solution, and there are interesting conclusions obtained even in this case, and they are non-trivial for real physical system like water waves. And then in the vector model, we can get at last the equation for which 2 asymptotics can be obtained. And one asymptotic is Zakharov weak turbulence solution, and another asymptotic is a strong turbulence solution, which corresponds either to universal equilibrium independent of flux or universal equilibrium independent on lambda. That's the present state of the art, which makes us very excited. Thank you very much. Because the chairman left, so I can take.
Please self-chair.
Yeah, so I'll self-chair myself, which means that I'll cut myself short if I'll be answering very long. Yeah.
So it looks like, I mean, it's described as an equation on motion level, but as a field theory, it looks like it's gapless. So it's critical.
It is.
So as a result, that do you get, you know, like at a critical point of 5-4 theory, that are there divergences that you need to?
It's critical in the sense that it's gapless. Everything is a power law, but not because you tune temperatures, because you have forcing and dissipation, and then you have a flux, and this flux actually sets this highly turbulent state. And that's why it's scale invariant, because if you consider it scales much different from pumping scale and much different from damping scale.
Okay, yeah, so the physics is very different, but I'm wondering at a technical level, do you have breakdown of perturbation theory because of these infrared divergences? where the, you know, the coupling effectively, it's not the 40
There
coupling.
is a whole zoo. There are cases in which you're exactly right, that we do that perturbation field actually is broken because of infrared divergence. In this case of nonlinear Schrödinger, which have shown, it's free of such divergences. So your one loop correction, you plug there your three-level solution, everything converges. So in this case, that's why it's interesting to go beyond and see what happens. But there are other cases, it's a whole zoo. There are many turbulences.
What distinguishes two cases?
Huh?
What distinguishes cases where it doesn't converge from cases?
Good question. I don't know qualitative answer.
No, no,
Just
two different models or two?
yeah, two different omegas and lambdas. You could,
Oh, I see.
You know, the method of convergence, it depends not only on scale and exponent. It depends on asymptotic of lambda when two wave vectors much less than other two.
Right.
And this is something for which in different physical systems there are very different things.
So you say for shallow waves, there are no infrared divergences?
No, for nonlinear Schrödinger. But for example, for spin waves, there are huge divergences. And we did not even start to analyze it because it seems like there are divergences on both ends.
Okay.
Yes.
If you want to just run some safety checks, for example, Edgar on work spectrum or something, can you do it with this method?
No, Colombo spectrum is for completely different system, for which Hamiltonian does not have a quadratic part. And everything we have in here, I thought absolutely unapplicable.
But is there analog of this?
There are no waves in incompressible fluid, which means that all my motions are, I mean, my kinetic energy is V squared, right? If I want to write it in canonical rails, it will be a to the 4, no quadratic term. So it could not be applied, but it could be applied to compressible turbulence. Acoustic turbulence, for example, it could be applied, sure.
For example, I mean, you should, I mean, there are many models. Let's look at this gross AFC model. Right? So it's a well-defined model. It's dimension 2 or 3, which dimension is this? Or you don't?
Both 2 and 3.
So, okay, what's your prediction? So,
We made a prediction as a following thing, and we already seen it observed numerically. That you start, for example, steering at large k. So you have an inverse cascade. Okay, it goes initially at low amplitudes, which means that it's big turbulence. It's independent. It's the same for focusing and defocusing, attractive and repulsive. At some low k, it leads. It hits the point where nonlinearity is a photouric. Then it splits. Focusing case goes down, and defocusing case goes up relatively to the R of solution. That's our prediction already confirmed. Now we also confirm to which asymptotics it goes in a strong turbulence limit. This asymptotics we take from large N series.
so confirm meaning you solve numerically differential equations?
Oh, numerically, it's a direct numerical simulation of initial dynamical equation. There's even not a kinetic equation. It's just honest to God solving dynamical equation. You know, it's a complicated task. Yes.
Very basic question. So when you do a nonlinear Schrödinger over this, you pump energy or matter?
We pump both, because when you do it at a finite k, you cannot avoid pumping both. So one goes in the direct cascade, in this case it's there, and then in numerics, directly scale off with it. And but action number of it goes in the inverse. So you cannot avoid. You always pump both in them. But theoretically, of course, you can simplify one. Okay, as the chairman, I will be starting short. I thank everyone for huge persistence.
Announcement. Tomorrow meeting will be on the 5th floor, not here.
That's where food is.
Yeah, and food is now waiting for you. Please take it. Eat it. In the fridge, yes, it's in the fridge. A lot of food. No, well, we can go to dinner separately, but food left over from.
Like extra.
Yeah.
Turbulence in my, maybe naively associated with singularity, what should be there in evolution?
Because you have power laws. If you look at singularity, of different quantities, either